So good morning, everyone, and welcome to Friday morning's session. So Friday is the last day of the meeting, unfortunately, but nevertheless, we've got a series of really exciting talks, and the first will be given by Professor Wei Xu, tuning thermoelectricity via nanoscale phase separation in tin selenide. So over to you, Wei Xu.
Okay, thank you for this nice conference, and I cannot attend in person, but I can only attend by this remote way. And I'm talking about, I'm Wei Xu from the Beijing Synchrotron Radiation Facility, and I'm talking on behalf of this collaborative work between the Pengpeng Shang, August Marcelli from Italy, and Giantonio from Diamond Light Source, and Jinfeng Li from Tsinghua University, and Yuri Shed from Beisi. So let me, I will talk about the several topics. Firstly, I will introduce about the thermoelectric materials, as it is just related to these major topics of this conference about the topological insulators and superconductors. And then I will focus on this rising star as the thermoelectric materials, the tin selenide. And then I will discuss about our new discovery of these materials, and then I will present some conclusions and perspectives. For the thermoelectric effects, the most important thing is that this effect was discovered about 200 years ago by the German physicist and as well as the French physicist. And also it was discovered that these thermoelectric effects was discovered in much earlier by the Italian physicist. And also, so we can call these thermoelectric effects if we can hit the hot side here and then from the cold side here, and then we can observe a thermoelectric voltage. This is a simplistic picture of that. And here you can see that the similar concept was depicted in this way. And so it is important to note that the charges are carried by the electrons or the holes, which carry the different types of charge carriers. And both of them can contribute to the induced thermoelectric voltages. It depends on which one is dominant. So we call it, say, majority carriers or the minority carriers. So when it can be put into devices, it can consist of the N-type thermoelectric materials as well as the P-type thermoelectric materials. From this application, it is called the power generation. From this side, this is the heat source, and the other side is the cool source. And the flow of these charges will carry some charges, voltage will produce some electric power. And you can put into use with in a reverse way. You can put the voltage here, apply the voltage here, then the heat from here will be pumped to this side, and then you can cool some stuff. And it was also found in the real practical applications like the radioisotope thermoelectric generators for the Curiosity mission or other space shuttles travels. The most important contribution of this thermoelectric generator is that it can provide the electrical power by converting the heat generated from the decay of the radioactive sources. And this, in principle, can sustain over a long period of time, about 300 years. Maybe you don't need that long time, but it is quite a unique application of these thermoelectric devices. The second kind of application is the Peltier cooler, which was widely used in the electrical detectors. This is the commercial one. I took the pictures from the website, and you can see the silicon sensors are here, and in the electronic part, you have this Peltier cooler to cool the temperature of the sensors and the electronics. And this cooling is quite important because if you cool the temperatures down to some temperature, some degree, and then you can get this very high energy resolution with a very high peaking time. That is to say, the saturation flux. So how can we define this thermoelectric figure of merit? Simply, we can just put it here into this is called a ZT value. And this ZT value is related to three thermoelectric parameters. One of them is the Seebeck effect, or the thermal power itself. And the other one is the electrical conductivity. And the rest one is the thermal conductivity. And all these are related with the temperature. So we just multiply the temperature, then this will give you a dimensionless figure of merit. And all these parameters are related also to the carrier concentrations here. So you can mainly find the ZT highest ZT value over this charge carrier concentration range. And usually you can consisting the thermoelectric materials into devices. If you make them into devices, you can describe the device's figure of merit as the power conversion efficiency, which is related to the temperature difference as well as the ZT value of the materials. And here there is also a deduced thermoelectric quality factor, which can be divided into two parts. One of them is related to the electronic parts, which is related to the mobility of the charge carriers. And the other one is mainly related to these phonon parts related to the thermal conductivity. So from the materials catalog, there are a lot of materials that can be applied in the different temperature range, as well as the different charge with different charge carriers as the majority of the charges. Here you can find that there are some low temperature applications and also some high temperature applications. And there are also some materials can provide both type, but some material, for example, this one can provide the P type and also the N type, but the others may only have one type of the ZT value. So this is for selection of them. So in last year, there was a very nice review of these materials and thermoelectric materials and thermoelectrical community of this community is that from this plot, you can see that over the years, the ZT value of the materials side was improved very much, especially in the past 2 decades. And most of the materials in this part are discovered in the 1960s, before the 1970s. And then there was a long pause. And after that, there was a huge breakthrough over the years. Those breakthroughs are related to the different kinds of knowledge based on the electronic structure as well as the nanostructures. So the efficiency of the first generation materials is about 3 to 6% over the over room temperature up to the 1000 degree. And in the new materials, those PCEs can be improved about 10%. So during the courses of this development, it is realized that from the materials itself, from the electronic structure, you need to improve the multi-band convergence, which will make you good materials with high power factors, which is good for the electric part. And if you want to reduce the thermal conductivity, you need to introduce some atomic scale defects that can scatter the heat carrying phonons, and especially to reduce the thermal conductivity as a result. So there are many kinds of defects from the point of view of the size. You can have the atomic substitution and also the dislocations, and you can also introduce some nanoscale precipitations and some grain boundaries, which can also contribute to the reduction of the thermal conductivity. From this same paper, it was said that the thermoelectric materials are having a good improvement over the years, and you have this ZT value in this tin selenide based materials, which is the king of this material side, and it has a ZT value up to above 2.5, almost 3. And but if you compare the other parameters, the linear thermal expansion on the also Baker hardness and fracture toughness, then this will lie in this lower side. If we want to make those materials into devices, we need more parameters to consider if it is suitable for certain applications. So in 2014, there was a paper that reported this tin selenide as has a huge thermoelectric figure of merit. Here you can see this in this plot. Along this B-axis, you have a ZT value about 900K. It's about 2.6. From this plot, you can see that this lattice thermal conductivity is extremely low, lower than 1. And this is another famous thermoelectric materials. And from that on, and there is a new break, also another paper published by the same community that they have this device ZT value, which is also high, and you can get this very high efficiency above 10%, about 10% in also at the high temperature range. And over the past several years, there were a lot of breakthroughs made in these materials, so this is quite interesting to check why these materials has so much high performance in the thermoelectrical figure of merit. One of the controversy in this field is that the lower lattice thermal conductivity, is it intrinsic or not intrinsic? In 2016, there is a debate publication that is said that they have made this single crystalline, they have compared the density, mass density of the materials with its theoretical values, and it said that this single crystal that was synthesized in the 2014 paper was not actually 100% a single crystal, because the density is much lower. It claimed that it says that the tin selenide sample cannot be classified as a single crystalline. So that is not intrinsic to the single crystalline tin selenide. And also in its reply, it says that there are different kinds of reports. Some of them are reporting that the thermal conductivity of the single crystalline is lower than is higher than the polycrystalline, and the others reported a reverse situation. So they just raised up another question, is that must the intrinsic value refer to ideal materials? So that means the material itself is not ideal, but what is the ideal thing? What is the intrinsic origin of this material, this lower lattice thermal conductivity? In this paper, they have used the inelastic neutron scattering to observe the phonon dispersions in these materials, and they also found that the phonon dispersion is strongly anisotropic, and also over the increase in temperature, the phonons will soften with the increase in temperature, and also because this is a layer, simply a layered structure, so the anisotropy is quite easily understandable. But these materials exhibit a giant anharmonicity of the lattice. So, and this soft mode lattice instability is related to the stereochemically active tin lone pairs. That is electronically related thermal conductivity. So this is the harmonicity of this trend. You can see that. And in the following year, they have this phonon dose, which is also obtained from the neutron-weighted phonon doses. And you can find that they have this single crystalline, and they can heat this materials heat up. And because they have the different energy resolution with different incident energy. So for these two types of measurements, you can focus on this different region. And findings are quite, it's a small shift. The lower and high energy phonon peaks are softened by 0.3 millieV to 1 millieV as the temperature increases from lower to the 700 K. And then in the meantime, they have done this tin nuclear resonant inelastic scattering measured at the room temperature to find also this anisotropy of this tin phonon dose. And also they have compared those with the DFT calculations. Last year, there was another paper. They used the same technique, nuclear resonant inelastic scattering, but they heat this sample up and they used the polycrystalline materials. And they found this is the spectrum itself. You can find that there were some phonon doses here. And at the high temperature, because the Lamb-Mossbauer factor is decreasing too much, so the signal to noise ratio is not that good. But then they can still achieve this acquired F factors as well as the third moment versus the temperature. They found that this anharmonicity of this lattice anharmonicity was not appear at the lower temperature, but they appear at the high temperature above around 300 K, and it also lasts until the high temperature, because they stopped here of this lower temperature range. And another study is is performed using the Mossbauer spectroscopy for the tin isotopes. They have measured these single crystalline materials, and it was crystallized in a very pure single crystal. You can see this rocking curve has a very sharp feature, and the single crystalline is very good. And but they still they found that although there is no amount of detectable tin oxide, but they have a minority component, which is not the 2+ tin selenide, but there are a small amount of tin 4+ in these materials. It was found. And also in the past year, they have also found that there are on the surface of these materials, on the tin cylinder, on the surface of the materials, there are a lot of oxygen on the surface. So they just reduce this amount of the oxygen on the grains of the materials, and then they can get the ZT value up to 2.5 of this in these polycrystalline materials. Last year, they also have made a huge breakthrough by observing more carefully about the presence of the oxygen in these materials. They found that the oxygen was existing in these grain boundaries, and they are more abundant in these grain boundaries. And you can see these grain boundaries. And if you introduce some reduction hydrogen gas and to reduce the amount of oxygens, and you can get improved. The ZT value can be improved up to 3. So this is another feature that can be found, that the tin selenide has a very high ZT value, and also there are some peculiar phase separations. So we have done this experiment at the diamond light source at B18 with the temperature-dependent exhaust measurements. We heat this sample from room temperature to 800 K, and we use different monochrometers for different energies. And also all these materials, because they are only two, tin and the selenide are 1:1 ratio. So we have the transmission mode, and we have performed these measurements on different kinds of doped systems. We have the tin sufficient, tin deficient, and tin abundant, as well as some bromium doped samples. Here are the major findings. At the tin KH, we found that at the lower temperature, you have observed a small energy shift, only a small energy shift up to 600 K. And then if you increase the temperature much more about that, you can observe some two isobestic points, which may hint there are some coexistence of different phases. Here we also plot this plot in this for this selenide KH. You can also find different kinds of isobestic points. And if we focus on this high temperature range, you can see this spectral shape changes very much. There is a detailed quantitative explanation in this paper. And we have found that from the EXAFS measurements, we just plot the experimental data, and you can find that this at a lower temperature, the tin oxygen bond was existing in these materials, and maybe it is smaller in these materials. And then if you heat them up, and then the oxygen bonding is increasing very much. And even for the other bromium doped systems with different textures, you can observe the different phases in these materials. And previously, we also have performed similar measurements in a single crystalline tin selenide samples. And for these materials, we have used this infrared synchronous radiation source with this far infrared range. The far infrared range, we can use this quasi-normal incidence reflectance spectra, and we hit these samples up to also 800 K. And we also, I just forgot to mention in the previous version, we also purged the nitrogen in the system to protect the oxidization or decomposition of the materials. And here is the sample itself. It's quite a smaller one, and it is okay. So this is a major picture of the major information of this this finding, that we also observed for this in-plane normal reflectance and also this out-of-plane reflectance. You can also observe different kinds of isobestic points, and also this you can see this is a layered structure, and from these measurements, the thermal conductivity measurements, the thermal conductivity along this axis. The A axis is along the out plane axis is quite smaller. So I need to mention that some curves might be shifted due to the experimental uncertainties, and that the reflectivity values shown are connected with these complex reflection absorption values. And also we have observed these isobestic points at different directions, and also this the behavior is different, but and also the crossing points are different in the wave numbers. So this is our major propose that for these materials, maybe there are some small amount of nanophases existing in these materials. And when you hit them up, you will find that there emerges a lot of nanophases during the heating process. And maybe those nanophases may play an important role to control the thermal conductivity, and so to improve the thermoelectric performance of these materials. Maybe this is not just a stop line, but it means that these materials is surprising, and we need more techniques to prove these materials. So in 2012, there is a famous paper that they construct these materials with different hierarchical structures to improve the ZT value. And
Wei Xu, you've got less than 1 minute left.
Okay, I'm almost down. Okay, so that means that the materials itself is quite complex, and we can maybe probe those within different techniques to make sure that we study these phase separations into different details, and different techniques will provide different perspectives. So this is the major conclusion of these materials. I just leave it here. And for this, I think the next question is what is the driving force of the nanophase formations? And also can the nanophase formations themselves can be self-assembled as nanoscale PNT devices? And I think this is quite interesting. And maybe we need more conceptual development or more knowledge to guide the new generation of TE materials, devices, etc. So with that, I will go to my acknowledgement. I acknowledge the Natural Science Foundation for the funding, and also the beam time from different light sources. And thank you for your listening.
Excellent talk. Thank you very much, Wei Xu. Do we have any questions from the audience, please? We have probably enough time for one question. So,
thank you.
Keijin Zhao, I think you have a question, or is that your clapping? Okay, any questions?
Yes, yeah, it's very nice talk. Yeah, Wei. Yeah, thanks. Just a very quick question. So you observed the change dramatically in your exhaust data around 400 degrees C. And earlier you mentioned about some phonon and harmonicity. Is any information you can extract from your exhaust data to correlate with phonon change?
We plan to, because previously we planned to extract these Debye-Waller factors, but here we found that there are many nanophases. Maybe in the next plan we can just try to measure this at a lower temperature and with a different kind of sample environment, like helium, not the nitrogen, and then we can deduce some also the lattice also the lattice dynamics from exhaust measurements. From here now, we didn't have this yet.
Okay. Fantastic.
Thanks.
I have a question.
Okay.
Can you try to apply strain in your materials? So if
that's one of idea. Yeah, that's a wonderful idea. Yes. We are trying to
create the next generation of electric materials to froze the nanoscale phase separation. I think strain is an essential parameter.
Thank you. Yes, thank you.
Thank you very much, Wei Xu. I'm afraid now on to the next speaker, but excellent talk.
Thank you.
Is Shibauchi Mishra online and able to share your slides, please? I think you just have to put it into presentation mode, please. Excellent, thank you. So our next speaker is Shibauchi Mishra, who will be talking about where is your closer view of quantum critical point in heavy fermion selenide cobalt indium. Thank you very much.
Yeah, thanks a lot. I hope I'm audible enough and my slides is visible.
Yes, your slides are clear.
Good. So first of all, good morning to all of you and other people, greeting of the day. So first of all, I would like to thanks to the organizing committee for providing me this opportunity to present our work on this very important topic of heavy fermion. So I have planned this presentation in a certain way that we should first try to see that what actually have been done on this particular topic and what are the missing information that we can try to fill those gaps. So we will try to begin with the introduction part, and then we will try to see some very characteristic feature of the heavy fermions, and we will select some particular material to deal this unattended topic, and we will try to explore that how this various interaction coming together to give the some exact feature in this heavy fermions material. So ultimately, we are going to see that how soft X-ray can be used to explore the quantum critical point in a very element specific way. So we will try to use the certain benefit of the soft X-ray to explore the quantum critical point, which is kind of really a missing field in this area. So get going with the heavy fermion. So we have normally selected the CeCO ion 5, which is kind of most popular and heavily studied heavy fermion material. So this is a S electron system where initially have been predicted that specific heat should follow linear with the temperature, but as of now, we have found that specific heat somehow is not linear in temperature, but it has the T square component. And the specific mass of the electron is also changes due to the presence of the certain interaction. So the interesting property will be trying to find that in this material, what is the behavior of non-Fermi liquid, and what is the main source of the unconventional superconductivity. So these materials are also known to be display one of the burning topic of the superconductivity, that's unconventional superconductivity, means the superconductivity along with some finite magnetism. So when we try to describe this, so there are certain terms essential to get aware ourselves. That one is like Pauli limiting criteria. So this criteria imposes certain kind of boundary condition or certain essential approach that one must have to have in this kind of material. So one of them is like the Pauli limiting criteria suppresses the superconductivity, and also it will show the variation of the superconductivity across the critical field. So this have been formulated and calculated for this particular material, that this HP field will be across 4.2. And if you apply the VCS coupling formalism, then this parameter that have been shown in this formalism, it can be calculated easily. So the main objection then is finding the G value of the two that has somehow is not consistent with the theoretical prediction. So if you try to see the specific heat, so as initially proposed that it should vary with the linear to the temperature, but there are some experimental observation in long back that have proposed that it's not, but there are certain another factor, especially the T square term will be also present in the specific heat contribution. So thermal conductivity is the another important factor that we must try to explore this behavior that will give you the another probing scale for this material and the functionality of the heavy fermionic system. So this system have been explored by various people. So this is the one example, and it's a very popular paper where the observation they have predicted of the presence of the non-Fermi liquid behavior in the heavy fermion. So if you look the entire spectrum of the heavy fermion as a function of the temperature and other variants such as the doping or temperature and magnetic field, so it exhibits various exotic characteristics such as like a heavy fermion liquid state, are some ordered state also, so like here as antiferromagnetic, and there are some quantum critical reasons, so that depending on what is the parameter that we are adopting. So all these reasons that we are seeing in this phase diagram actually evolve due to the competing interaction that present in the system. The most popular and dominating interaction is the RKKY, and another is there are present interaction. Those are competing and giving the various phases for this. So ordering will compete with this RKKY. So these are giving various exotic features. That's what have been shown here. So that include also the strange metal, heavy fermion, liquid, or even the magnetic order. So to explore this, we will try to find this a systematic approach that what is we can try to capture that what will be the essential parameter that can represent the quantum critical conditions or quantum critical point. So we will try to address those. Never forget that in this kind of lattices, impurities play also a major role to decide that how the conduction are in terms of the superconductivity. You can also find that how the resistivity is changing across the doping as the function of the temperature. So these are the some factors that keeping in mind, we will try to address some of this element specific characterization of the quantum critical point. So we begin with the preparation of the sample. So we grow the single crystal and we try to characterize that what is the simple look like. So it's a very essential to have this confidence prior hand before going to some advanced characterization. So we follow that protocol. So we characterize our sample with the various technique to be sure about that our crystal that we have known is actually belongs to the same material and same composition and the same phase that have been studied before. So we can claim that we have new information on this particular field. So like we also find the presence of the magnetism at the very ultra low temperature. It's around 5K. And we also see the not only the finite magnetism at the low temperature, but also this magnetization is keep changing as a function of the temperature. Not only that, it also has some magnetic history when we change the protocol of the cooling of the sample. So we apply the zero field and field cool condition to monitor that how the magnetization evolve as a function of the temperature. So that was the magnetic component. Now we also try to see that how the conductivity is evolving. So we try to use various methods. So we adopted AC resistivity measurement to confirm that we have the superconductivity in our sample. So we can find the very steep decrease of the resistivity across this at low temperature point. So when we plot this change in magnetization and the change of resistivity, so we can get a sense of the influx point where these two parameters are making a transition. So that's giving a hope that our sample is really belongs to those class of the CeCON5 where this heavy fermionic state would exhibit. Not only that, we also try to measure the resistivity and the magnetoresistance of the sample, and all of them are fulfilling this criteria of this superconductivity. Not only that, we measure the specific heat, and as I mentioned you before, and very similar to the literature, that there are specific heat not only linear to the T, but there are also variation of that indicating the presence of the T square term in the superconductivity. So this characteristic indicating that our compound is exhibiting the unconventional characteristic of the superconductivity across this low temperature region. So we will try to explore our objective which is the a element specific probe of the this quantum critical point. So to adopt that, we simply adopt the X-ray absorption based technique. So we perform this experiment in the absorption mode. So this absorption mode have a sampling depth of the 2 to 100 nanometer, depending on what material and what is their element belong to those particular materials. So we will follow this technique. Not only that, this X-ray absorption technique will provide the local coordination or the information about the balance state of the sample, but also we can utilize this technique to probe the magnetism and also to find what is the contribution that coming from the spin momentum and the orbital momentum. So both contribution can be distinguished with this technique. So we apply this formalism. That's one of the most utilized technique for the probing the magnetism with the soft X-ray. So we perform this our experiment of the X-ray measurement at the P04 beam line at the Petra 3 Deshi. So this chamber look, and these are the really tiny samples that what look like where X-ray will come at the certain angle, and we will try to collect the sample current. And during the experiment, we have the capability, or this chamber have the protocol to apply the magnetic field as high as like a 7 Tesla. And not only that, we can cool the this sample, it's like a 0.1 Kelvin. So it's an extremely low temperature. So when I say it's the 0.1 for X-ray, that's really a significant temperature that one can achieve. So this is a representative curve that we got online representation of the data. So that's what the curve that look like. So this the signal here is for cobalt, and we got the cerium. Not only that, we also have shown the differences of the this two X-ray absorption curve, which is the XAS spectrum recorded for the two different fields, and the we take the differences of these two spectrum that representing this curve. So there are some finite signals. So this is the one direct approach that you can find. So we try to understand more about that how this variation of the balance state of the cerium is evolving in our sample. So as this XAS analysis indicates that there are not only the main peak that what we call the M5 and M4 peak for the cerium, but also we have some satellites peak which present in a very strong intensity, and their number is also very significant. So we will try to confirm that there is not only one particular balance of the cerium present in the crystal, but they are present in the like more than two of them. So it's like a cerium 3 and cerium 4. So these two spectra we try to simulate, and they are fitting well to our observed data. So we have confidence that in our samples, both balance state are present. So we will try to explore their dependency as a function of the temperature and the field. So that will give you the idea that how because this balance fluctuation is the one essential factor that must happen near to or across the quantum critical point. And if we can show that its balance state is fluctuating across the quantum critical point, then we have a certain advantage in this experiment. So we try to find more about this XAS. So this gives information that our crystal have the tetragonal crystal symmetry that belongs to the D4H, and the Kramer doublet are occupied in this various fields. That's like a 3 different Kramer doublet. So we try to analyze our XMCD data to gain the more information about the magnetism. So we simulate our XMCD signal. So that's top one is experimental data, and beneath the solid line is a simulated data. So this simulation give us a hint that the variation of the angular and orbital momentum component for this particular data point is 0.143 and 0.18. So if you take the average of these two, so it's like coming to the -8, and total momentum, which is the sum of these two, is 0.125. So this is the actually the tells us about presence of the finite momentum, and that's what we have confirmed with the magnometry, where we find the hysteresis curve. So that giving a confidence that indeed our data is valid. So not only that, we also try to do the field dependent at very low temperature, which is the 0.01 Tesla. So we try to record this XMCD signal by varying the applied magnetic field, starting from 50 millitesla to the 6 Tesla. And you can see for all the field, there are certain XMCD signals are present. So that data or experiment suggests that it's not just finite moments are there near to the quantum critical point, but they are also have a fluctuating nature. So that you can tune by applying the external variant, which is the field, and keeping the temperature constant. So to understand that how the balance is actually varying in this particular material near to the quantum critical point, we apply this. If you look this curve, so that have been shown for the various magnetic field, and if you zoom into this part that have been shown here, so we try to find the integrated intensity within this curve and to the main curve and take their ratio, so that will give you a sense that how these two valencies are actually varying as a function of the magnetic field. Similar things we can do as a function of the temperature. So we record the for particular field like 6 Tesla and keep changing the temperature and try to plot a similar curve. So we can get that how the balances actually are, you can say the orbital occupancy is get changing across this quantum critical point. So this observation is a kind of first type of observation that we have carried out for this particular material in ultra low temperature condition. So knowing that this doublet, Kramer doublet, we try to find that what are their momentum and what is the average magnetic moment per cerium atom that we can get. So that's a typical value that what we got for this particular single crystal that we have measured in the experiment. So not only that, remember that this compound is also have the cobalt in that. So cobalt, how the cobalt is doing. So that's very essential because this information or average cerium momentum you can calculate by just speed magnometry, but there are no confident confirmation that indeed this magnetic moment belongs to the cerium unless you probe it. So we try to distinguish this gap. So we monitor that how the cobalt is doing in the same fashion. So we can see that here cobalt is almost showing a absolute no ordering. So that could be that for two reasons. It could have the antiferromagnetic order, or it could have the simple a diamagnetic characteristic in that. So we don't find any finite momentum for the cobalt, which is for cerium, we have very good XMCD contrast. So we can summarize our finding in this following way, that we provide a direct spectroscopic evidences for this heavy fermion compound, and we try to correlate this with the quantum critical point, because here we can directly monitor the 4F occupancy of the orbitals. So not only anomalies in both like magnetization and transport measurements suggest a direct link to the Kondo origin, and the significant change in the orbital occupancy at the low temperature that is giving you a direct clue that how the electrical response of the material is behaving. So our result is also providing a direct proof of the quantum criticality in presence of the unconventional superconductivity in the cerium, cobalt, and iron 5. So with this, I would like to acknowledge the people who participated in this experimentation. It's like we have got very nice support from the Stockholm University, and our soft X-ray measurement is performed at the P04 beam line at the Petra, and we have a very nice support from the Deshi people and University of Hamburg. The sample and magnetic characterization have been cross-checked at the multiple places to gain more confidence. And we also have support from Ying Tai Huang from the University of Amsterdam in Netherlands. We got financial support from the Department of Science and Technology, India. With this, I would like to thank you all for your kind attention.
Thank you very much, Shwaran. That was a really interesting, fascinating talk. Do we have any questions from the audience, please? Either in person or online.
I have a question.
Yes, please.
So you mentioned about the low temperature. How did you measure the temperature of the sample?
Yes, so I think in the chamber, we have one probe that directly attached to the sample, and another apart from the cold finger that we commonly use for other experiments.
Okay, thank you.
I have a comment.
Yeah.
So thank you for this beautiful presentation of review and very deep study of these materials. I think these deserve a lot of experiments like and interpretation, because it's a clear, beautiful case of multi-gap superconductivity.
Yes.
And the old 20 years ago interpretation of Fermi liquid now is a very historical part of the history of science. So with modern technology, quantum computer, we can face to calculate a multi-gap, multi-component superconductivity. And your results you have are very useful and can be used
Yes.
for new theoretical scenario in these materials.
Yeah.
Okay,
sure.
I think,
we can contact for this. Yeah, definitely. I'm looking for all help. Yeah.
Any additional questions? I have a quick one, if I may, Shwaran.
Yes, please.
I'm aware that quite a lot of tunneling spectroscopy has been performed on these types of samples before. Has anyone performed that on your specific samples?
Not yet. So actually, our collaborator in Stockholm, they are actually trying to this kind of experiment. But as far as update that what I have, they still haven't done it. Yeah.
Okay, but it's happening, so that would be interesting to see when it comes out.
Yes, sure.
Brilliant. Well, thank you very much, Ryan. As I said, that was really interesting and important talk. Thank you.
It's a pleasure, Jason.
Thank you. Masato, do you want to share your slides, please?
Okay. Can you hear me? And
yes, I can hear you, I can see you, and now I can see your slides. So excellent. So our next speaker is Masato Sakano, speaking about micro-focused RPES study on atomically thin tungsten telluride flakes. So over to you, Masato. Thank you.
Thank you very much for Mr. Chairman. Good morning, everyone. My name is Masato Sakano, an assistant professor of the Ishizaka Group at the University of Tokyo, Japan. At first, I would like to thank the organizers for inviting me to talk about my researches here. And I'm sorry to talk via online this time. I look forward to attending the face-to-face meeting next time. Okay, today I'd like to talk about two papers shown here. Both were recently accepted and will be published soon. So one of them, upper one, we show the microfocus laser-based study on the multi-layer tungsten ditelluride flake samples. We have successfully observed the clear ALPS images and reveal the layer number dependent electronic structure originating from the combination of spin-orbit interaction and structure asymmetry. The other show how to make van der Waals heterostructure samples for ALPS measurement. Here I show the collaborators. I really appreciate for great collaboration. As shown here, the main players of this study are three people. Professor Masubuchi of the Machida group at the University of Tokyo, and my ex-student, Mr. Tanaka, and me. I am an ALPS experimentalist, so I would like to thank Professor Masubuchi for his great contribution to the sample fabrication. Before going to present the study on the tungsten ditelluride flakes, let me briefly introduce my previous researches. Since my student days, I have been studying the spin and electronic structure in the inversion symmetry broken systems and topological materials with strong spin orbit coupling, as well as developing the laser ALPS system in our laboratory. And for the past few years, I have been interested in the electronic structure of exfoliated two-dimensional materials. Here I show a brief summary of my previous ALPS and the spin-resolved ALPS studies on the various non-central symmetric bulk crystals. In the non-central symmetric crystal, the spin degeneration of the band dispersion is lifted in the momentum state, like that. And the spin-orbit interaction is described like this. So very roughly speaking, the electron feels an effective magnetic field perpendicular to its own momentum and the potential gradient. Thus, the spin textures in the non-central symmetric crystal depends on how the potential gradient is formed in the crystal. As far as I know, although there is no spin-resolved ALPS instrument with nano or microfocus light source that can measure small exfoliated flake sample, but actually, thanks to the state-of-the-art ALPS spin-resolved ALPS measurement, we can measure the spin polarization three-dimensionally on the band dispersion, like that. Recently, I'm interested in the special inversion symmetry breaking in atomically thin exfoliated flakes and their heterostructure. In this presentation, I will present how the stacking order in multi-layer tungsten ditelluride breaks the inversion symmetry. And let me start the introduction for tungsten ditelluride. Here I show the basic properties of the TD tungsten ditelluride. The crystal structure shown here is a so-called distorted 1T type structure. The characteristic feature is the distorted 1T type octahedron, like that, networks got stuck with pi rotation around the stacking Z direction. So in this presentation, I call this stacking as antiphase stacking. I'll show the detail in the next slide. And as for the electronic structure, the bulk tungsten ditelluride, which is known as the candidate material for the type 2 wire semi-metal, is a perfectly compensating semi-metal with the hole and the electron surface across the Fermi level. And tungsten ditelluride is also known as a material whose physical properties exhibit distinctive variance from bulk and towards monolayer. The transport measurement revealed that the down to tri-layer show the metallic behavior. In contrast, bilayer and monolayer show the gapped semiconducting behavior. So, and from the viewpoint of the structural symmetry, monolayer has a centrosymmetric structure, but multi-layer and bulk tungsten ditelluride lack the inversion symmetry associated with the antiphase pi-rotation layer stacking. In this slide, I visualize how the antiphase stacking order breaks inversion symmetry in the multi-layer tungsten ditelluride compared to the well-known H-type material, tungsten diselenide. First, we consider a simplified virtual model that the non-distorted T-type layer stacks with antiphase stacking. The black blocks represent single layers of tungsten ditelluride, and the orange triangles represent the orientation of tellurium triangular networks. And the cross markers represent twofold rotational symmetry axis. In this situation, because the YZ plane correspond to the mirror plane, so the presence or absence of cross marker correspond to the presence or absence of the inversion symmetry. The monolayer has a centrosymmetric structure, but you can see the inversion symmetry is lost in the bilayer, and it recovers in trilayer, as shown here. This might remind you that this is the opposite behavior to that of H-type material, such as the 2H tungsten diselenide, as shown here. In the H-type material, the inversion symmetry is broken in the monolayer and recover in the bilayer. Therefore, in the tungsten ditelluride, a different type of even-odd layer number dependence can be expected. In the realistic case, the odd number layer tungsten ditelluride also has the non-centrosymmetric crystal structure because the two-folded rotational axis within each layer are stuck with the alternative shift along the y direction, like that. As a result, all multi-layer tungsten ditelluride belong to the same space group, independent of the even odd number of layers, so non-centrosymmetric crystal structure. But actually, the even odd effects reflecting the structural asymmetry recently theoretically proposed and experimentally confirmed. Thus, we can expect the even odd effect appearing on the electronic band structure in multi-layer tungsten ditelluride. Then the purpose of this study is to investigate the layer number dependence of the electronic structure in multi-layer tungsten ditelluride flakes. As for the sample fabrication, we use the two-dimensional materials manufacturing system developed by Professor Masubuchi. This system can search exfoliated microflakes by image recognition technique based on deep learning and assemble them as van der Waals heterostructures by robotics under the nitrogen gas atmosphere. And the laser ARP system has been developed by myself. experimental conditions are shown here. Currently, the actual spot size is evaluated to be smaller than 20 micrometer. Let me move on to the sample fabrication process. We use the basic mechanical exfoliation and the dry transfer technique. Here, I skip the detailed procedure and introduce only the key point. For the RPS measurement, the sample must satisfy two important conditions. The one is the sample must electrically contact in order to suppress charging due to the photoemission process. In our procedure, the sample must electrically contact, connect the gold electrode via graphite. The second is the topmost layer should be covered by atomically thin material. Here we use the graphene because the RPS is surface sensitive and the tungsten ditelluride is easily oxidized in air. So to require these conditions, we pick up the flakes from the hexagonal bond nitride in order. And once we flip the sample by using another polymer, HBN can stabilize the pickup process. And these procedures are done in the nitrogen grow box. And the samples drops onto the substrate with the gold electrode, and the polymer is removed by chloroform. A fabricated sample is sealed into the vacuum suitcase and transported into the ultra high vacuum RPS chamber. If you're interested in, please refer to the recent accepted our paper for the details fabrication process. Let me show the RPS results. These are obtained RPS images for the 2 to 5 layer tungsten ditelluride along KX direction. The used flakes are shown above the RPS images respectively. The red line segment correspond to the 10 micrometer. For easy viewing, here I show the curvature images, which is show the curvature of the RPS intensity profile. As you can see, we successfully obtained a clear band dispersion. The number of layers were first distinguished by image analysis for the optical microscope image, and further unambiguously determined by the obtained RPS spectra. After the RPS measurement, we also double check them by AFM. The markers represent the intensity peak for the RPS spectra. We can see that the eigenstate increase with the number of layers increasing in the energy region between minus 0.2 to minus 0.5 at the gamma point, where the continuous states appears in the bulk crystal. As for the E-bond effects, we will refer later. Next, I will focus on near film level. We can clearly see the layer number dependent evolution of the hole-like band dispersion around Kx around minus 0.2 angstrom inverse, changing from the being fully occupied for the 2 layer and the nearing touching for the 3 layer, and the 2 apparently crossing film level for the 4 layer. The upper RPS images for a 2-layer tungsten ditelluride were taken at 20 Kelvin and room temperature. With the help of thermal excitation, we can observe the electron-like conduction band above the film level at the room temperature. It indicates that the band structure with a small band gap is realized in the 2-layer. The right panel shows the calculational result. It seems that although GGAPB calculation outputs metallic electronic structure, but the calculation using the HSE hybrid functional method will reproduce the semiconducting electronic structure with the small band gap. As for the 3-layer, we could observe faint but finite RPS intensity for the electron-like band crossing the film level. Thus, we spectroscopically confirmed that the insulator metal transition appears between 2 and 3-layer, which is consistent with the transport measurement. We should note that the direct observation of the electronic band structure by RPS is very important because accurate prediction of the electronic structure by first principle calculation is still difficult, even for such a simple few layer samples. Finally, we focus on the layer number dependence of the spin split band dispersion. As for the 2-layer and the 4-layer, spin split band dispersion are clearly observed in contrast to the 3-layer and the 5-layer. It seems that the energies of the spin splitting show the even the dependence of the number of layers. Lower panels are the DFT calculation images. The DFT calculations are colorized by the in-plane spin Y component for the negative kx and the out-of-plane spin Z component for the positive kx region. These calculations use the atomic coordinates of the bulk crystal. In other words, so any atomic relaxations and reconstructions are ignored. So regardless of such a simple swap calculation, we can also see the even node dependence in the spin component, especially in the 2-layer and the 4-layer with larger spin splitting. The spin Z component are dominant. Considering that the spin-orbit interaction works perpendicular to the momentum of electron and the gradient of potential, so it seems that the in-plane potential gradient can play an important role in this even node effect. The center graph shows the output spectra at kx minus 0.1 angstrom inverse. The circle markers represent the peak positions estimated by assuming a single component, and the end of error bar represent the peak positions estimated by assuming double components. The right graph summarizes the number of layer dependence of the energy of spin splitting for the kx minus 0.1 angstrom inverse. We can see such a zigzag behavior. Considering that the bulk tungsten ditelluride is polar semimetal, so this even node effect merges towards infinity number of layer, and the non-zero spin splitting remains. So this behavior consistent with the schematics which I showed in the introducing part. Thus, we concluded that the even node effect is attributed to the in-plane potential gradient induced by the tellurium triangular networks associated with the antiphase stacking in tungsten ditelluride. In the case of tungsten ditelluride, it becomes clear that the stacking order can control the spin splitting of about 100 milli-electron volts. So this is summary. We successfully developed microfocus output measurement procedure for the isolated atomically thin microflakes, and we could observe the clear band dispersion in 2 to 5 layer tungsten ditelluride flakes, which show the semiconductor semi-metal transition between 2 and 3 layer. And we observed that the spin splitting in the 2 and 4 layer are larger than the ones in the 3 and 5 layer. This even node effect is likely to be attributed to the tellurium triangular networks. The sample fabrication procedure developed in this study can be applied to the various van der Waals stacking structure. So we think now the complicated electronic structure of many other 2D-dimensional flakes, including van der Waals heterostructure and the twisted material, becoming target for the RPS measurement. So as shown in the presentation, since it is difficult to well reproduce the band structure by first principle only by the first principle calculation correctly, so even in such a simple multi-layer material, so I would like to unclear the electronic structure in the more complicated material by micro-focused RPS in future. Thank you very much.
Thank you very much, Masato. That was a brilliant talk. Do we have any questions from the audience, please? So I have a question.
Okay.
Okay, let the audience go first.
It is possible for you to apply strain in your flakes and to see the transition, the effect of insulator metal transition. Because
Sorry,
energy scale between the subbands are very small, so it will be very interesting to study by RPS strain effect in this case.
I think he's asking you if you can change the strain of the sample and do RPS in situ.
It may be difficult, but it is possible. For example, the tension like that.
So I had a question about the spin splitting versus number. Unless I'm misinterpreting your data, there seemed to be some interesting scatter in the values of the spin splitting, and I was wondering, is that a spatial variation effect, or is that an effect due to measuring different samples?
Sorry, one more time, please. I'm sorry. One more time, please.
There was, in your plot of spin splitting against number of layers, I think there was some scatter in the data, and I wanted to ask whether that's a spatial variation effect, or is that just variation due to fabrication? Which leads me on to my next question. How much reproducibility do you get in that spin splitting versus layer number results, which is very interesting, by the way. It's not a criticism by any means.
Currently, spot size of the laser is about 20 micrometer, so it is
it's quite
larger than the flake.
Yeah, okay, yeah, it's larger than the flake. So the variation we're seeing then, is that due to different samples?
Reproducibility is already checked.
Sorry, could you repeat your answer?
We can check the reproducibility.
You mean you haven't done so yet?
Yes.
Okay. Any other questions, please? No, so let's thank our speaker again. Really well done, Masato. Great results. Next speaker, Zurab, do you have your slides?
Yes, yeah, let me share them. Okay. Do you see the slides?
Yes, I can now see your slides in presentation mode. So our next speaker is Zurab Guguchia. Apologies if I'm not pronouncing your name properly.
It's fine. It's correct.
So you're going to be talking about using uniaxial stress to probe the relationship between competing superconducting states in a cuprate with superstripe order. So a very apt title for the conference. Over to you, Zurab. Thank you.
Yeah, thank you very much for the introduction. Good morning, everyone. I'm Zurab Guguchia, Senior Scientist at PSI. And so there I will show you our results on the uniaxial strain effects on superconductivity and stripe ordering in the cuprates and a cuprate compound. I want to start thanking all my collaborators, the muon spin spectroscopy group at PSI. So all the experiments that I'll present to the muon experiments under strain was done at PSI. And I thank my collaborators from the other departments, other labs at PSI, And we did also X-ray diffraction experiments under strain with a group of Mark Janoschek and Johan Chang and Martin von Zimmermann at DESY. And so the collaboration with a group of Hans Henning Klaus and Clifford Hicks, because the strain device at PSI was developed in collaboration between PSI, TU Dresden, and Max Planck with Clifford Hicks. And I thank John Tranquata and this group for a very nice collaboration and very nice crystals also I get from Tadashi Adachi and from Yoshiko Ike's group. So really thank everyone for this wonderful collaboration. So let me start showing the phase diagram of lanthan barium copper oxide. This is, I think, one of the most astonishing manifestation of the competing states in cuprates, which can be seen in one single phase diagram of lanthan barium copper oxide. So here you can see that the superconductivity is strongly suppressed around this 1,8 doping, which is called 1,8 anomaly. And at the same time, there is appearance of spin ordering and charge ordering. And most of you know, this spin and charge ordering is consistent with the so-called stripe model, in which we have this local antiferromagnetic ordering and is separated by these periodically spaced domain walls into which the holes are separated. So we have a spin and spin rich areas and charge rich areas. And so in addition to the spin and charge ordering, there's some particular structural phase transitions from tetragonal to the orthorhombic phase and then into some low temperature tetragonal phase, which is characterized by the tilting of the copper oxide octahedra. And all these structural distortions is believed to pin the stripes around the 1,8 doping. And then there is this particular stacking of the stripes along the C direction. It's kind of orthogonal stacking. So the stripes are changing the direction when you go from one to the other layer. And there's some phase shift as well. So this is quite important in my discussion. The C-axis stacking, because it's that also influences superconductivity. So since we have this quite rich phase diagram in LBCO, this can be used as an advantage of tuning the different states and understanding the interplay between all these different ordering in this compound. So as I told you here, at 1,8 doping, there is a strong suppression of TC, but later on what it was shown is that, in fact, there is a strong suppression of three-dimensional TC, so the TC shifts below 10 Kelvin, while two-dimensional superconductivity is still onsets at 40 Kelvin, which is very close to the magnetic ordering temperature. So depending whether you do, because this configuration, when you apply field along this C-axis, then you have a supercurrents within the plane, and you can screen, if you have the two-dimensional superconducting order, you can screen the currents already below 40 Kelvin. So what these experiments have shown that this three-dimensional superconductivity is much lower than a 2D superconductivity. And it's the big difference between these two temperatures gave evidence or the point to the obvious frustration of the interlayer Josephson coupling between these two layers. And that's why we get a much lower 3D TC than 2D TC. And to understand this obvious frustration of the interlayer Josephson coupling, there's a concept of so-called pure density wave state which was introduced. And so within this picture, there is the superconducting order parameter is not homogeneous, but you have this modulated superconducting order parameter in the form of pure density wave. And just to elaborate a bit more on this, of course, there is a superconducting pairing correlation which should develop within the charge stripes, but you need superconducting phase coherence between the charge stripes. And when you have the spin ordering here, that does not allow the in-phase superconducting ordering. However, the out-of-phase superconducting ordering is allowed according to this PDW theory. And so the PDW is compatible with the magnetic ordering within the plane. But as long as there is a pair density wave or this two-dimensional order within the plane, the combination of PDW or the out-of-phase superconducting order within the plane and the orthogonal stacking of these stripes along the C direction ideally should fully frustrate the interlayer coupling. So TC should go as low as it can go. Within this picture, one can explain why the 3D TC is low, because all this PDW and the interlayer, that's the orthogonal stacking, basically frustrates interlayer coupling. So what you can say, the PDW is good for two-dimensional superconducting order. That's why it onsets at high temperature, but it's bad for a 3D phase coherence. Okay. So what we wanted to understand experimentally to study interplay between the uniform D-wave state, this two-dimensional superconducting order, and the spin stripe order experimentally. So we did a combination of muon spin rotation, X-ray diffraction, and AC and transport measurements. Today I will focus on Mishra and AC measurements on different dopings. And of course, there have been many experiments done tuning these states using magnetic field or hydrostatic pressure or impurity effects. But the uniaxial strain was much less explored. So, for instance, there is this pioneering work back in 2004 where they measure TC as a function of strain, and they see quite sizable effects. But the systematic strain experiments on this LBCO on a stripe state was not really done. So this is basically what we performed. So again, I show this phase diagram. So here we focused on this region around 1.8 doping. So we took these two dopings, one below 1.8 and one higher doping than 1.8. And we used the muon spin spectroscopy, which is highly sensitive magnetic probe that we are sensitive with ordered volume fraction and ordered moment size. And you see that being sensitive to the ordered volume fraction is quite important also in this particular case. So if you take the compound, which is 11% doped here, from MUSR, you see the onset of magnetic transition at about 40 Kelvin. And then this is the magnetic volume fraction that reaches about 85% at base temperature. So when you look with the AC susceptibility, we see the two-step transition. So this is the onset of two-dimensional state, two-dimensional superconducting order. And the bulk superconductivity only starts with the onset of about 10 Kelvin, which is consistent to this phase diagram here. And when we do the transport measurements, so this is in-plane resistivity, we also can see the anomaly of the structural phase transition, which is somewhere here from low temperature orthotropic to the low temperature tetragonal phase. And then this two-dimensional ordering, so the zero resistance that corresponds to this onset and susceptibility, which is about 20 Kelvin. So this is the uniaxial strain sample holder. We use the piezoelectric driven apparatus. So this is just a sample holder where we mount the sample. And it's about 4x4 square millimeter, the surface area, and thickness about 0.6 millimeter. It's quite large crystal, in fact. And we put the ACS coil just below the sample, so we can measure AC susceptibility and the MUSR in the same condition, so in situ. So in first, the experiment that we did, we applied the strain along the 30 degree with respect to the A-axis here. So it is not exactly diagonal or elongate, but it's a 30 degree with respect to 110 direction. And then this strain sample holder is attached to this force generator, which consists of these piezoelectric actuators. We have tension and compression actuators, and by applying voltage on the actuators, we can control the force on this part. So we can compress this part here, and this is fixed, so we can compress the crystal, and we can control these voltages quite precisely. So let me show you first what we get from susceptibility data. So this is the measurements at 0 GPa. So now I define the two temperature here, the onset and the three-dimensional TC I define as a midpoint of the transition. So when we apply a small amount of pressure, 0.01 GPa, you already see a significant change. So the TC onset moves up and the midpoint moves significantly higher to higher temperatures. And then I keep going, increasing the strain and 0.023. So we see also increase of TC, but also it's a broad transition. And finally, we get to very sharp superconducting transition with a single TC, the onset's about 33 Kelvin. So we get the optimal superconductivity at close to 1.8 doping just by applying 1 kilobar uniaxial strain. So being encouraged by such a huge effect on the superconductivity, we of course looked at the spin ordering. So because here you see TC, we can push it up. So we kind of suppress this 1.8 anomaly and we get to this optimal superconducting region. Now what happens if we study the magnetic state. So there we can do two different types of experiment. One where we look at the magnetically ordered volume fractions. Here we apply a small amount of field, and then we look at the muon spin precession. So this is the proportional to the paramagnetic volume. So we have a maximum paramagnetic volume at 45 Kelvin, and then we have this 80% volume fraction. So we lose the paramagnetic fraction at 3 Kelvin. So now if we apply strain, we see that I can recover the paramagnetic volume partly at the maximum applied pressure. At the same time, we can look whether we can keep this oscillation indicates the long range ordering. But when we apply strain, we can still keep the long range ordering with more or less the same internal field. So despite the fact we are reducing the volume fraction, the magnetic ordering, the long range ordering still stays, and with the same amount of internal field. So we still have the magnetic ordering at the highest applied strain, but with a reduced volume. Now, if I follow the magnetic fraction as a function of temperature, as a function of uniaxial strain, you can clearly see that actually onset only slightly goes down, but the ordered volume fraction actually reduced by 50%. But then at low temperature, we have some kind of recovery of the volume fraction. And in other example, I will show you, this is quite interesting. But while the spin ordering temperature does not really go down a lot, the volume fraction we reduce quite substantially. So now to summarize all this in the phase diagram, we see that the three-dimensional TC increases significantly as a function of strain within 0.04 GPa. It's extremely low uniaxial strain. And the spin stripe and then two-dimensional TC actually has a modest increase. But the spin ordering goes down and then it matches TC. So in this strain region beyond the critical strain, they have a similar value. So the magnetic ordering and superconductivity have similar value. But if you look here, the internal field, which is these points here, does not really change. I mean, there's a very small change from 25 to 23 millitesla, but the magnetic volume fraction has a strong effect. I think that the most influence that the strain is influencing is the ordered fraction and beyond the critical strain value. So then we ask question ourselves whether we have the same effect on the other side of the 1/8 anomaly, or if you just go through this phase diagram, which is not so easy, but we at least tried one sample on the right side of the 1/8 anomaly. And in this case, actually, we also did the measurements on the same sample, but with not 30 degree, but exactly we applied along the diagonal to see the effect is the same or not. And we did this experiment for both samples on the left and right side of this phase diagram. And so now again, the 0.115 sample with 45 degree strain, we again see a big effect. So we can push the TC and get this sharp superconducting transition. And also the 0.135, again, we can slowly, smoothly move to the highest TC region of this phase diagram. So basically, for both sides of the 1/8 anomaly, we can fold up this anomaly and get the optimal region, like in the lanthanum-synco peroxide. So we can destroy this with a small amount of strain. And also on the magnetic volume fraction in this 11.5% sample, we see again a tiny reduction of spin ordering, but then temperature, but we see this reduction of the volume fraction. But when you go to the millikelvin, because we went down to 300 millikelvin, we see that we can recover the magnetic volume fraction. Some system was to keep the large magnetic fraction at low temperatures. And also in the 14% sample, we also see the reduction of fraction, but then also kind of recovery towards the low temperatures. So this upturn is actually real because we can see 3 different samples. Again, if I summarize now all the measurements on 2 samples here, again, we see the spin ordering goes down and then it matches TC. We had an enhancement of TC. Here, we don't also change the internal field a lot. We still have long range ordering here. And the magnetic fraction depends whether we are at 10 Kelvin, 5 Kelvin, or at the millikelvin region. We have strong effect only if you're going away from the millikelvin, basically at 5, 10 Kelvin, but at low base temperature, we are recovering the magnetic fraction. The same for the 0.14% dot sample. So all this, the effect is, the critical pressure is very similar. So it is 0.06, 0.08. So everything is happening within 1 kilobar region. And then once we suppress once we achieve this three-dimensional superconductivity, then we don't have any effect on magnetic volume fraction. So we keep this 50% volume fraction all the way up to 0.3 GPa. So the main effect is happening when they are kind of competing or cooperating. And then we can keep both orders all the way up. So now how to interpret? So could be different ways to understand this data. Of course, since we know that interlayer Josephson coupling is frustrated because of the orthogonal stripe ordering, one way to think is when you apply uniaxial strain, we are kind of reorienting the stripes along the same direction. So we have some kind of reorientation, and this can also recover the interlayer coupling. But this is just simple reorientation cannot explain why we are reducing a lot the magnetic volume fraction. So the second way to understand is that when we apply uniaxial strain, we are promoting some kind of the patches of the uniform D waves superconductivity in each layer. And then when these patches grow and they overlap, the projection of different patches overlap along the C direction, then it immediately recovers the interlayer superconducting coupling. So we are destroying locally, let's say, the magnetic regions or the pure density wave regions, and then we are recovering 3D superconductivity. And with X-ray diffraction, we could confirm that actually we are suppressing the LTT phase. And I think the second scenario is more compatible, but there could be both, actually, combination of reorientation and plus the reduction of the volume fraction within the layers. Now let me conclude. So we, using extremely low uniaxial stress of 0.1 GPa, we can induce the big increase of the three-dimensional superconductivity from 11 to the 33 Kelvin factor of 3 increase. So we find that the uniaxial strain actually is highly efficient, way of tuning the scoop rate system. And actually this strain is much lower than 1 GPa, which was found to induce three-dimensional order in 1.8.5 BCO. And obviously at hydrostatic pressure, we actually need about 1 or 2 gigapascal also to do some changes with the ordered fractions, much higher than what we have here. And it seems that the large volume fraction spin ordering is anti-correlated with the 3D superconducting coherence, but the states are very finely balanced. And we see that the onset temperature of 3D superconductivity and spin ordering are very similar beyond the critical pressure, and which points to the similar pairing mechanism for spin order, specially modulated 2D order, and uniform 3D superconducting orders. And this may help, or it may impose some constraint on theoretical models. And with that, I would like to thank you very much for your attention, and I'm open for questions.
Zurab, thank you very much. It's a really interesting presentation on what is frankly quite a complicated material system. So do we have any questions, please, from the audience?
I have a question. Can I ask?
Yes, please go ahead.
So yeah, so can you comment? So yeah, this is quite nice. Could you comment on the possibility of the the competition between the charge order in this case? How much, let's say, when you apply the strain,
yes,
and you recover the 3D superconductivity, but I guess you would have some impact on the charge order and how they kind of cooperate with each other.
Yeah. Thank you. Very good question. Yeah. So of course we try to measure both structural transition, because you have this LTO to LTT transition, right, which is closely linked to the charge ordering. We are also doing measurements directly on charge ordering, but what we see, actually, I want to show you. So we can follow this splitting of the LTT to LTO transition in our crystal. And then what we see when you apply strain, the small amount of strain, we can actually suppress completely the LTT peak. And then we are favoring only the LTO structure. At the highest strain of 0.15 GPa, we have only the low temperature orthomic or less orthomic phase. So we are completely suppressing the LTT phase, and the charge order also, the onset of the charge ordering is not very much influenced like spin ordering, but the intensity of charge ordering is also reduced, which is comparable to the intensity of the magnetic volume fraction that we are. So they are all matches very nicely.
I see.
The charge order is slightly reduced with the onset, like spin ordering, but we still keep them. We still keep it.
That's very interesting. Thank you.
Thank you.
Any further questions? So I have a question, Zura.
Yes.
Right at the beginning of your talk, you showed this very nice plot of susceptibility versus temperature from which you get TC of your sample, I think.
Yes. Yeah.
And that TC was quite broad, which I presume is related to the strain structure of your superconducting state. When you were measuring strain, did you track the transition width as a function of strain as well?
Yeah, that's a good question. I think I don't have the plot here, but it's obvious that at the highest strain, it's very sharp, right? So once it's very sharp, while with the strain, we can evolve from one state. It's still broad in the intermediate region, but finally we get the sharp transition. So because then we have only 3D order, and here we have combination of this 2D and 3D, which makes it broad, right? But once we get 3D order, then it's actually much sharper than in edge-grown LSEO, for instance.
Thank you very much, Rob. That's very nice data.
Thank you. Thank you very much. Interesting questions.
So unless there's any further questions from the audience, I suggest we move on to the next speaker. Thank you very much, Zura. Really
Thank you. Thank you.
Takasada, is your presentation ready, please?
Okay.
Thank you.
Can you see this, right?
Yes, absolutely perfect. Our next speaker, sorry?
I hear the echoes.
I think you're hearing the audience in the background. Augusto, could you please switch off the sound for the audience, please?
Is it okay now?
From my side, it's fine. So our next speaker is Takasada Shibauchi. Sorry if I'm mispronouncing your name. And you'll be speaking about enhanced superconductivity near a nematic quantum critical point in iron selenide-based superconductors. Over to you, Takasaka. Thank you very much.
Okay, thank you very much. So first of all, I would like to thank Antonio for the invitation to this conference. And today I would like to discuss the enhanced superconductivity in nematic quantum critical point in iron selenium-based superconductor. So I'm Takashi Shibauchi from University of Tokyo. This work has been done in collaboration with many people listed here, but many players are underlined, like Shida, Mukasa, and Imajo in the University of Tokyo. And I acknowledge contribution from Okay, so let me start with the general introduction on the quantum point and unconventional conductivity. And this is a general phase diagram, temperature versus thermal control G. And one can actually suppress the ordered phase like this, and you may have the phase transition along the zero temperature line, which is called the quantum critical point of QCP. And above this QCP, you have the deviations from the Fermi-Ricci properties. And more importantly, you can often find this superconducting dome around the QCP. So there are a lot of discussion about the origin of this superconducting dome, which may be related to the quantum fluctuations associated with this QCP of the order. And this kind of discussion is being widely used to explain the spin fluctuation superconductivity. And here is an example of very terminal systems in which you have the antiferromagnetic code, and near the quantum critical point of the antiferromagnetism, you may have so this magnetic fluctuation mechanism has been widely accepted in many strongly correlated systems. However, today I'd like to pose a question. What about the case if we have a non-magnetic and the non-magnetic quantum critical? And importantly, we discuss the effect of the nematic order And my question to address here is, can nematic fluctuation associated with the nematic QCP promote disease conductivity? So if you look at the theoretical proposals, actually you can find the superconductivity which can be mediated by the nematic or orbital functions. And here are two examples. One from the Kontani-san in Nagoya University, who found this superconducting dome near the orbital ordering. And here is another one from Steve Kiverson, and they found this superconducting dome with the very exotic scattering near this nematic QCP. So these are the very good proposals from theory, but this nematic fluctuation induced superconductivity has not been established experimentally. So the effect of the nematic QCP has been discussed most widely in iron-based superconductors. And here is an example of the barium 122 case, in which you can induce superconductivity either by hole doping or electron doping or isovalent substitution. And here's an example of this isovalent substitution case, and in which you can find a clear nematic transition which is marked by TS, but below which you can also find the antiferromagnetic transition called TS. Okay? So there are several growing evidence for the presence of the QCP near this superconducting dome. However, in this QCP, it has a kind of dual nature between the nematic QCP and the magnetic QCP. So in that case, it is quite difficult to pinpoint the impact of the pure nematicity on superconductivity. So to this end, I think it is important to look at the iron selenium, which is known to have a pure nematic order, below which you don't have any magnetic order. And then you can actually try to suppress this nematic order in several ways. And here is an example of the hydrostatic pressure, P. And if you apply pressure, one can actually reduce the nematic transition temperature. But then before coming to this nematic QCP, you can also find the pressure-induced magnetic order like this, which shows a very interesting dome-like feature. Then here is another way to suppress the nematicity, which is the isovalent substitution. So you can substitute selenium with the isovalent sulfur. Then you can actually suppress the nematic ordering completely by about the 17% substitution. And then here is an important point that we don't have any magnetic ordering in a wide range of systems. So I think this is the first case that you have a pure nematic QCP system. And the evidence for the QCP has been obtained from the largely enhanced nematics. And so, this is a very interesting system. And another important point is that we can obtain the high quality single crystal in this series by the so-called chemical vapor transfer. And here is an example of the STM imaging, and in which you can find the position of sulfur atoms. And from this, one can conclude that, we have a very uniform distribution of, meaning that we have a very uniform. And also, look at the high field measurement, we can observe the quantum oscillation in a wide range of X, meaning that we can also have a clean crystal. So these results indicate that it is quite a very good system to explore the intrinsic physics in this nematic QCP. And if you look at the transport in this QCP, one can actually find that the T-linear resistivity down to very low temperature when you suppress conductivity by high magnetic field, indicating that we have actually non-permeated property near this peak. And we can also take a look at the thermodynamic properties. And here is a set of data showing the temperature dependence of the electronic specific heat divided by temperature. And from these measurements, one can construct the thermodynamic phase diagram. And here is the pneumatic transition temperature. And then, so this is 2 times DC, which shows a jump near this QP. And if you look at this SC2 region, inside the pneumatic phase, you may see this broad peak-like feature. And this may be related to the spin fluctuation, because if you look at the 1/T1T in the NMR measurements, you can see that actually near the 10% you see the enhancement of the spin fluctuation, which seems to be associated with speed in the S2. However, the most interestingly, if you look at the temperature dependence of C/T inside the pneumatic phase and outside the pneumatic phase, we see a big difference. And if you look at this SC1 region, one can see the very unusual strong superconducting fluctuations. And at low temperatures, you can find a very large residual density of states. So this difference strongly indicates that the nature of between this SC1 and SC2 are quite different. And this difference indicates that we have 2 different superconducting states. Unfortunately, today I don't have enough time to discuss the natures of these 2 phases, but the presence of 2 different superconducting states across the pneumatic QCP make it difficult to discuss the effect of pneumatic fluctuation, the impact of pneumatic fluctuation on the superconducting near this QCP. So we need another system to look for it. And here is another try. So we can use the tellurium as an isovalent substitution. And here is the iron selenium tellurium phase diagram, which has been studied for a long time. But here is the very important experimental issue, which is for phase separation. And if you look at the low tellurium side, we have this problem. So, which is difficult to discuss the impact of pneumaticity in this system. However, very recently, we have succeeded in growing the very high quality single phase, single crystals around this region. And by using these crystals, we can now discuss the correlation between pneumaticity and superconductivity. First of all, we can use the temperature dependence of resistivity and also synchrotron X-ray diffraction. We can map the pneumatic transition temperature as a function of tellurium composition, and you can see that the pneumatic order can be suppressed, in a monotonic way, and one can completely suppress pneumaticity around 50% substitution. Then we want to try to quantify the pneumatic fluctuation. So basically, we can use the so-called elastoresistivity measurement, which is actually known to be a very good probe for pneumatic fluctuation in this system. So basically, you can use the piezo device in which you can apply voltage to induce the anisotropic strain, and then you can measure the resistivity tensor, and from which one can analyze to extract the pneumatic susceptibility INet. And here is a set of data of the temperature-dependent pneumatic susceptibility, and TS, one can try to get the data by using the simple Curie bicycle. And here the T naught is a wise temperature, which can be very good. And the T naught is corresponding to the bare nematic transition temperature of the electron system if we have no coupling between the electron lattice. But in reality, T naught is actually lower than the temperature, because in the presence of coupling between the electrons and lattice, the actual nematic thermodynamic transition becomes higher than it. By the thematic measures of this stability, one can end up with this kind of phase diagram. And in the left-hand side, I plot the sulfur substitution case. And on the right-hand side, we have beryllium substitution. And first of all, these yellow lines corresponding to the nematic transition temperature, and these red points are the wise temperature, which is determined from the nematic susceptibility. And the colors indicate the magnitude of it. And you can find that the sign change occurs at certain points in this phase diagram, both in the sulfur case and beryllium case. And when the T naught becomes 0, it means that your susceptibility diverges towards 0 temperature. So this indicates the quantum criticality. However, as I mentioned, that we have the coupling between the electron systems and the lattice, and theory indicates that actually thermodynamic nematic transition temperature is shifted up from the bare nematic. So in such a case, nematic quantum critical point in the thermodynamic point of view is shifted to the right. So from this consideration, we can conclude that we have evidence for the nematic quantum critical point here and here, which is shifted from the quantum critical point of the bare nematic. So to conclude, I have actually two kinds of nematic QCP in this phase diagram, combining sulfur case and beryllium, which can be compared with the TC evolution in this phase. So as I mentioned before, in the sulfur case, we have a completely different superconducting states, SC1 and SC2. But then if you go to the beryllium side, this SC2 seems to be extended like this. Then you have a minimum around 30%, and then you have another superconductor, which we call this 3. Okay, so first of all, this SC2 has also shows the dome-like feature, but as I mentioned before, this peak in the TC in the sulfur case is strongly correlated with the spin fluctuation, which is evidenced by the 1/T1T enhancement near here. However, if you look at the NMR results in this SC3 region, you essentially see no significant spin fluctuation. So here is a temperature dependence of 1/T1T, which shows basically standard Colin behavior. So this means that there is no significant spin fluctuation in SC3 superconducting dome. But as I mentioned before, from the nematic susceptibility measurements, we have the nematic QCP inside this superconducting dome. So this clearly suggests that this SC3 is strongly correlated with the nematic fluctuation animated from the nematic QCP. So to gain further information, we can actually apply strong magnetic field. So here is a kind of set of data taken at ISFP if we have a pulsed magnet up to 6 Tesla, we can try to analyze the upper critical field HC2 as a function of temperature. And here is one summary about it, showing that this evolution, this phase diagram, as a function of field. And you can see in the HC1 and HC2, one can suppress conductivity quite easy in a magnetic field. But if you look at SC3, those superconducting seem to be quite robust high magnetic field. If you look at the 45 Tesla data, for example, you still have this superconducting dome near this nematic peak. So one can also look at the temperature dependence of H2, and this is the low tellurium doping site around here, and in this panel showing that high tellurium concentration site, and in the high tellurium side we can see that this flattening behavior of the HC2 at low temperatures, which is associated with the Pauli limited behavior of the upper critical field. And from analyzing this data, we can actually estimate the so-called Pauli limiting field, H Pauli. And here is a plot showing that H Pauli divided by TC, which is, roughly speaking, is a measure of the superconducting gap delta divided by TC, which you can tell how strong your pairing is. Okay, and as you can see, this value H Pauli divided by TC shows an enhancement toward this nematic QCP. So this enhancement strongly indicates that we have some mechanism to enhance pairing strength, which is found near this QCP. So from these results, we can conclude that the nematic fluctuations emanating from the QCP and here can enhance the pairing strength of the field robust superconductivity. And I think this is the first demonstration that pure nematic fluctuation, which is non-magnetic, can actually promote the field robust superconductivity. Okay, so let me summarize my thought. So we have studied these iron selenium based superconductors. One is sulfur and the other is tellurium substitution case, and both exhibit purely non-magnetic nematic QCP. And if you look at the TC evolution in the sulfur case, it has a broad maximum inside the nematic phase, which may be related to the antiferromagnetic fluctuation. In contrast, in the tellurium case, we have a strong dome structure near the nematic QCP, evidencing enhanced superconducting pairing due to nematic fluctuation. Thank you very much for your attention.
Thank you very much, Takasaka. That was a very interesting presentation. Really, really interesting work. Do we have any questions, please, from the audience?
Hello, hi. Can I ask a question again?
Please do.
Yeah. So yeah, it's very interesting data. I'm quite intrigued. I didn't quite understand the selenium, selenium doping and the tellurium doping. They have such a drastic difference in terms of the interplay of the nematicity and the superconductivity. I guess they're isovalent doping, right?
That's right.
How to understand that? Okay, I kind of roughly get the point that the difference between the doping is the one thing is related to probably the short range spin fluctuation. The other could be nematic fluctuation. But just purely from the the doping point of view, I don't know how to kind of to capture such a drastic difference just purely chemically. One is selenium, the other is tellurium, but they have so many different let's say effects on the big picture.
Yeah. So first of all, this iron selenium is a very exotic system, and there is one can have a lot of interaction, spin, which is associated with degrees of freedom and orbital degrees of freedom and other things. And the difference between the sulfur and tellurium substitution is that the sulfur corresponds to the actually positive chemical pressure, and the tellurium is actually negative chemical pressure because of the difference in the size of the atoms. But the details of the physics, why we have such a difference on the effect of superconductivity, is still not well understood, and I think this is just experimental observation right now. That we have spin fluctuation here, but no spin fluctuation here, and we have two kinds of different superconductivity. So that's the experimental observation, and I think I hope that this observation will stimulate the theoretical studies, which can somehow identify why we have such a big difference. Thank you.
Okay, thank you.
Thank you very much. I think we still have time for an additional question if anyone would like to ask anything.
I have one question.
Mm-hmm.
Please go ahead.
Okay, this is beautiful work, very interesting. However, the interpretation should consider also the fact that iron, selenium, sulfur, and iron, selenium, tellurium, changing concentration, relative concentration, they go through electronic topological transition that are quite relevant and provide a simple interpretation of the superconducting dome. Have you considered this possibility?
Okay, yeah, very good question. Actually, if you look at the electron structure along the gamma Z line, there is a band crossing appearing, in this tellurium case. And as Antonio said, that we have evidence for topological superconductivity near this, high tellurium doping site. So, so it is possible that this kind of, non-topological to topological change in the electron structure may affect the superconductivity. But, as I mentioned before, it is very recent to have the series of, to obtain this series of single crystals along this side. So this is just a starting point to see how this electron structure evolves as a function of tellurium composition, for example. And then, I think further studies are needed to settle this issue in the near future. And I think it is a very interesting point. What's the impact of the, this electron structure in this superconductivity as well? Thank you very much.
Thank you very much, Takasaka. I think that's all we have time for in terms of questions. So let's thank our speaker one final time. And that brings this session to a close. So many thanks, everyone.
Thank you very much.
We have a coffee break now. Thank you. Thank you, Takada.
So good morning, everyone, and a great many thanks to the organisers for giving me this opportunity to talk about my group's recent results on europium sulfide niobium superconducting heterostructures. So the title of my talk is Absolute Spin Valve and Supercurrent Diode Effect in nearly nanometer thick S-wave superconductor on a ferromagnetic insulator. The bulk of the presentation will be on the absolute spin valve effect, and I'll show some preliminary diode effects near the end, which are very preliminary. I'd also like to just point out that most of the experimental work I'm going to be talking about today was undertaken by the Hisa Masuki, who is a third-year PhD student in my group, and also a number of other supporters like Alexander Buzdin from the University of Bordeaux and Sébastien Bergeret, who are assisting in various aspects of this project with theory. And experimentalist Leslie Cohen, who's doing some very interesting point contact and rare spectroscopy, Herman Sudero, who's doing scanning tunneling microscopy, and a series of different types of experiments which are being done at the Hebrew University of Jerusalem, mainly related to the diode effect. So let's imagine you have a superconductor ferromagnet interface in which the superconductor is S-wave spin singlet, meaning you have standard BCS pairs with anti-parallel aligned spin Cooper pairs. And the ferromagnet, for a moment, let's assume that's a simple transition metal ferromagnet with SD band ferromagnetism. So at the Fermi surface of such a material, you would expect a spin splitting between the up and down spin bands. And assuming you have good electron transparency at the superconductor ferromagnet interface, via a process of Andreev reflection, I would expect superconductivity to penetrate the ferromagnet. And it would penetrate over a length scale of the coherence length, which due to the large energy splitting at Fermi energy, would translate to a penetration length within the ferromagnet of only a few nanometers. It would also show an oscillatory dependence superimposed on an exponential decay due to the momentum mismatch between the spin up and spin down electrons of a pair. And because of the exchange field acting on the superconducting state within the ferromagnet, you would expect both spin zero singlets, but also spin zero triplet states within that ferromagnetic layer. Equally, the ferromagnetic state would also penetrate via a splitting of the superconducting quasi-particle density of states. And assuming you have a low Z number in that superconducting material, take, for example, aluminium, then I'd expect that spin splitting within the superconductor to easily penetrate over a singlet coherence length. So in aluminium, that might be hundreds of nanometers potentially. In niobium, in principle, it might be a few tens of nanometers. But if you want to measure accurately the so-called inverse proximity effect, in this case, I mean signatures of ferromagnetism within the superconducting density of states, it's far better to use a ferromagnetic insulator over a transition metal. Why? Because if you use an insulator, you block the proximity effect within the ferromagnet itself, and then through a process of specular reflection and tunnel coupling between the superconductivity and the strongly ferromagnetic F orbital bands within the ferromagnetic insulator, you can then induce a fairly strong spin splitting within the superconductor. Now, in the case of niobium, which does actually have quite strong spin orbit coupling, I'd expect that spin splitting in principle to be very limited to the interface. So this is an old story, at least theoretically. So this was first started by a series of papers published in the 1960s by Pierre de Gennes, a French physicist, whom you all know, of course. And it wasn't really until much later that experiments on spin splitting within superconductors on ferromagnetic insulators or indeed transition metal conducting ferromagnets were actually conducted. Most of that work started with the experiments by Pedro Merzabay and Mudira at the Francis Bitter Laboratory at the MIT in Boston. And their experiments started with europium sulfide, which is a typical Heisenberg ferromagnet. It's got an energy gap of about 1.7 electron volts and a ferromagnetic Curie temperature of approximately 17 Kelvin, although in a thin film geometry that can nevertheless be slightly suppressed. It also has well-defined in-plane magnetic easy axes. In our case, that's isotropic in-plane magnetic anisotropy. And it also has in-plane stray fields. You don't get these unwanted outer plane block domain walls, which of course would therefore generate a suppression of the superconducting transition as well. So we don't get those in our films. Okay, so as I said, a number of experiments on spin splitting have been done in the past by Pedro Merzabay and Madeira, but what I'm showing here is an example of a more recent experiment by Francesco Giazzotto's group at the University of Pisa. And what they've made here is a very well-defined tunnel contact. At the bottom, you have europium sulfide. It's about 5 nanometers thick. These films were in fact grown by Madeira's group at the MIT, but processed into devices in Pisa. The aluminium at the bottom, which is where you're measuring the quasi-particle excitations, is then sitting below a tunnel barrier of aluminium oxide. And on top of that is a top contact of superconducting aluminium. So what you can see now on the right is differential voltage differential current as a function of bias voltage. And if you look at the black curve in the first instance, so that's a sample which is in a coercive field state, so it's in the virgin state, plenty of domain walls, you can still nevertheless see some splitting in the density of states. But if you magnetize the europium sulfide, you then get much uniform splitting in the quasi-particle density of states. And if you apply theory, you can calculate an estimate of the exchange splitting within the aluminium, which is of the order of a few Tesla. It could be in principle up to around 10 Tesla, which is quite extraordinary actually, without much of a suppression of the TC either. And that's partly because obviously the aluminium is sitting on an insulator, so you don't have this proximity effect within the ferromagnet. And they also performed this interesting experiment. This was actually done at the Francis Bitter Laboratory, Madeira's group. They systematically investigated the splitting in the quasi-particle density of states in aluminium on europium sulfide as a function of a sprinkled layer of gold sitting in between the aluminium and the europium sulfide. So the idea here was to see what would happen as you introduce some layer of spin orbit coupled material, conductor ferromagnet insulator interface. So again, if you look at zero gold thickness, then you can see this spin splitting. I presume they're in a micromagnetic state with domain walls because the splitting is not very uniform. But nevertheless, as you introduce the gold, you can see that the splitting progressively disappears. So by the time you get to a discontinuous layer, sprinkling of gold of about 0.6 nanometers, then you can't even see the splitting in the density of states anymore. So the assumption there is that the presence of gold has somehow suppressed the spin splitting, presumably by some spin-dependent scattering process. So instead of using aluminium, we've chosen to use niobium, and that seems counterintuitive in many ways, since I've already said that niobium has spin-orbit coupling, so you wouldn't expect the exchange splitting to be very robust within niobium. Anyway, this was what you would expect, at least from quasi-classical theory or general theory of superconductivity, but we thought we'd give it a try anyway, because it has a much higher TC than aluminium. So there are some obvious benefits from a transport measurement point of view. And the first interesting result actually is the fact that when you grow niobium onto europium sulfide, you get a very robust superconducting transition, albeit suppressed, but with a transition width of only around 50 to 100 millikelvin, even down to a thickness of about 1.6 nanometers. So this gives us an interesting opportunity, because if we think the spin splitting in niobium is simply limited to the interface, that doesn't matter, because we can grow the niobium incredibly thin, much thinner than 10 nanometers, which is what you would normally be depositing niobium on a transition metal ferromagnet. And so if you just make a direct comparison of growing niobium with silicon dioxide, you can see that we're seeing a significant increase in TC. In the case of silicon dioxide, of course, there's some oxidation at the interface. But if I were to grow niobium on, for example, cobalt, nickel iron, or other ferromagnetic transition metal materials, then I'd certainly not get such a slow suppression of the superconducting TC as you go down to such thin layers. Now, before I discuss the superconducting behavior of the niobium on europium sulfide, I just want to show you some interesting data in the normal states. This is a plot of in-plane resistance versus in-plane magnetic field at 10 Kelvin. And what you can see there is a rise in the electrical conductivity of the niobium occurring at the coercive field of the europium sulfide. So you get these very well-defined dips in resistance at exactly the coercive field of the europium sulfide. Now, we don't exactly understand the origin of this behavior, but what we can see is if you assume it's a magnetoresistance-like response, then that magnetoresistance-like response decreases as 1 over the thickness of the niobium, meaning if it is of a normal state exchange splitting origin within the niobium, and you get this rapid decay as a function of niobium thickness, where there's no spin, no magnetoresistance-like response above the Curie temperature of europium sulfide. So an obvious couple of questions to ask, I think, would be, is this magnetoresistance-like behavior spin Hall related or AMR? So if you fabricate a Hall bar, as Felix Casanova's group did on europium sulfide platinum, and you vary the direction of the applied field from being parallel to your current in that Hall bar to orthogonal and outer plane, if it were a spin Hall magnetoresistance effect, then I wouldn't expect any change of resistance with angle gamma, whereas if it was an AMR effect, I'd expect a modulation as shown in the plot on the right. But what we see here is certainly a modulation of the resistance, but it's clearly inverted with respect to the AMR. So it doesn't look to me like this is spin MR or AMR. An alternative experiment you could do is apply the magnetic field continuously perpendicular to the driving current, but circulating it through an angle beta. Now, in this case, you would expect MR to show the response in the middle here. In fact, this is quite similar to what we see, but since we didn't see any evidence for AMR with angle gamma, then I don't think you can conclude from this result that it's necessarily a spin Hall MR response either. So at the moment, our assumption, although we still need to do some theory in order to understand this magnetoresistance-like response in niobium, is that there is, even in the normal state, some magnetism, spin-dependent magnetism induced within the niobium layer. And that spin-dependent scattering process is somehow minimized at the coercive field, which is also very counterintuitive. I'd expect that the coercive field spin-dependent scattering to be maximized, meaning you'll get a rise of resistance and therefore a decrease in electrical conductivity. I'm not suggesting for a moment that we could explain our results as being related to a chiral edge state generated at the coercive field of the europium sulfide. It's interesting to see that a similar result to ours was in fact reported by, again, Jagadish Madura's group, but this time it was a topological insulator deposited directly onto europium sulfide. And what they showed is that the coercive field, you get this drop in resistance, which translates to a rise in electrical conductivity. And what they're suggesting is this is related to the fact that the strong spin-orbit coupling within the topological insulator induces an outer plane anisotropy within the domain region of the europium sulfide due to Kramer's degeneracy. And that should, in principle, induce chiral edge states, which will have a higher conductivity. So as I said, I'm not suggesting this is the explanation for our normal state magnetoresistance behavior in niobium, but nevertheless, it is intriguing because niobium does in fact have quite strong, albeit isotropic spin-orbit coupling, although we have interfaces here. And of course, we're also using europium sulfide. Okay, on to the spin switch result. So we've been fabricating devices with top and bottom layers of the ferromagnetic insulator europium sulfide. They have mismatching thicknesses of 10 or 20 nanometers, and that's so that we can ensure that there is a mismatch in coercive switching field between the top and bottom europium sulfide layers. And we have fabricated a series of spin valve structures with different niobium thickness from as little as about 2 nanometers to around 20 nanometers. Now, when the europium sulfide magnetizations are parallel, I'd expect an additional suppression due to the presence of an additive exchange field acting on the niobium superconductivity. In the case in which the europium sulfide magnetization is anti-parallel, I would expect some recovery of the superconducting transition temperature due to a net cancellation effect of the magnetic exchange field acting on the niobium superconducting state, meaning TC, or superconducting transition for anti-parallel magnetizations, should be larger than the TC for parallel magnetizations. So that's not a novel phenomena. That's been investigated for nearly 2 decades. But what's quite clear in most of the literature you read is the differences in TC between anti-parallel and parallel tend to be quite small, and they tend to be of the order 10 to 100 millikelvin. So this is some magnetometry data measured at 5 Kelvin. So this is in-plane magnetic moment versus magnetic moment versus in-plane magnetic field. We get a fairly bulk magnetization of about 600 EMU centimeter cubed. And you can easily see that there is indeed a nice area over which the magnetizations of the europium sulfide switch from parallel to anti-parallel. We then measured the in-plane resistance as a function of magnetic field, and what we see is infinite magnetoresistance. So if you look in the parallel state, you're clearly in the normal state, and then when you get to the anti-parallel state, you get a full switch into the superconducting state. So this is an absolute spin valve effect, meaning you're able to switch between normal and superconducting states, depending on the magnetic state of the device. If you look on the bottom, what I'm plotting here is an effective magnetoresistance ratio as a function of temperature. And in the high temperature region, you're seeing this normal state magnetoresistance-like phenomena. So what I'm actually plotting here is the absolute value of magnetoresistance. As a function of decreasing temperature, you can see it approximately linearly increases, although this is a logarithmic scale, but then clearly exponentially rises as you go through the superconducting transition, meaning below about 4 Kelvin for this particular device, you're dominated by the exchange proximity effect acting on the thin film niobium. So in this particular device I'm now showing, the niobium is only 4 nanometers thick, and at 3 Kelvin you get full switching between resistive and superconducting states. This is another device we fabricated, which has a niobium thickness of only 3.5 nanometers. And again, you get this full switching between superconducting and resistive states by switching between parallel and anti-parallel magnetic configurations. Now, if you apply a magnetic field in the parallel state and then switch off that field, you remain in this non-volatile parallel magnetic configuration. So you can then measure resistance as a function of temperature, which is what I'm plotting on the bottom. So you can see that the resistance in the parallel state remains fairly stable. There's a slight reduction at lower temperature, which might be related to the fact that you're going towards the superconducting transition, even in the parallel state. Although I suspect over the temperature range plotted, that's just a lowering of the resistance due to a decrease in temperature. And in the anti-parallel state, you get a very well-defined switch to the superconducting state with full superconductivity achieved just below 4.9 Kelvin. So what we can say from this plot is that the difference in TC between anti-parallel and parallel is at least larger than 200 millikelvin, which in a metallic ferromagnetic insulator system is in fact significant. In oxide systems, similar results have been achieved, and indeed at much higher temperatures, but not in systems involving simple metallic S-wave superconductors. So this is a further result we got more recently. So we've been playing quite carefully with the growth conditions of the niobium on the europium sulfide. The key from our current experiments is to grow the niobium actually quite slowly rather than faster. We've been reducing the power of the the electron beam evaporation of the niobium on the europium sulfide. And now we can achieve a difference in parallel and anti-parallel of over 1.8 Kelvin. Perhaps the delta TC itself is not so much the significant factor here, but rather the ratio of the change of TC over the TC of the sample itself, which is in this specific sample 50%. So I think that's the most significant switch effect ever seen in a superconducting spin valve device. We also looked at what happens if you apply an outer plane magnetic field rather than an in-plane magnetic field. And even in these samples, we get very interesting switching phenomena. So what I'm showing here is the magnetization versus outer plane magnetic field. And what you can immediately see from the data is even at 0.2 Tesla, we're not fully saturating europium sulfides. We're about a third of the saturation moment. So even with a 200 millitesla outer plane magnetic field, we're not parallel, but we have some collinear parallel magnetic state. And if you then reduce the applied field, you do get some increased inhomogeneous magnetic state around what might be a coercive light field in the outer plane configuration. And if you then continue to apply a negative magnetic field, you get a non-collinear parallel state in the opposite magnetic field direction. So let's have a look at what resistance versus outer plane magnetic field looks like. So if we start in the quasi-parallel, non-collinear parallel magnetic state, and we reduce the applied field to 0, we can see that you go back to a superconducting state, and that's because you're suppressing the orbital suppression of the superconductivity. So there's no orbital destruction of superconductivity. As you increase your negative applied field, you see a progressive rise in resistance. Again, that's due to now orbital effects suppressing the superconductivity of the niobium. But when you hit this coercive-like region in the outer plane field configuration, where you get this non-collinear configuration of europium sulfide magnetic moments, you then get re-entrant superconductivity, which remains quasi-robust over a fairly decent field range, which actually corresponds to that coercive-like regime you could see in the magnetic moment versus magnetic field, so in this region here. And then eventually, as you go back to a more collinear magnetization state, there's a sudden jump in resistance before you go back to a fully normal state. So this is very unusual. I've not actually seen this sort of behavior before in spin valve devices. And of course, it's an outer plane configuration, which is far more complicated because now you have to consider the net effect of outer plane stray fields also suppressing the superconductivity. Nevertheless, you do get this re-entrant superconducting behavior, which is an interesting observation in its own right. And if you measure resistance versus outer plane magnetic field, so if you can set up a quasi-collinear parallel magnetic state and measure the resistance versus temperature, you get a transition which is slightly shy of 3.6 Kelvin. If you then set up a quasi-anti-parallel magnetic configuration, outer plane magnetic field, you get a superconducting transition of more than 3.8 Kelvin. So even in the outer plane configuration, you get robust switching between quasi-parallel and quasi-anti-parallel magnetic states with a delta TC of about 300 millikelvin. So yes, that's quite significant, but it's much lower than what we were seeing in the in-plane magnetic configuration, where you can get up to about 1.8 Kelvin. Okay, so now I want to switch subject and discuss the superconducting diode effect, which we've been trying to look for in these films. So I should stress that this is extremely preliminary data. So by all means, don't mind being critical of it. So I just want to raise this interesting paper that was published in 2020. So this was a niobium, tellurium, vanadium superlattice structure in which you have both broken inversion symmetry, and the only way you can get broken time reversal symmetry is by applying a magnetic field. So there's no magnetic layers within this superlattice structure. And what they show in this paper is if your magnetic field is perpendicular to your current, then in one direction of current you get superconducting flow, in the opposite you get normal state flow. So this is showing a really strong superconducting diode effect in these Hall-bar-like devices I'm showing on the bottom right. And on the top here, I'm showing some of their really nice data. So on the left, you can see resistance versus temperature, showing the superconducting transition with a current of plus 0.1 milliamps. And if they switch the current between plus 6.6 and minus 6.6, you can see this really nice switching between normal state and superconducting state current flow. And they continuously switch to show that this result is robust. So we were wondering if we would observe something similar in our devices. In this particular case, it's a niobium 8 nanometer europium sulfide, I apologize, I should say europium sulfide bilayer. So in terms of broken inversion symmetry, if we have that in our structure, it would purely be due to the presence of interfaces, because both the niobium and the europium sulfide have very similar crystal structures, while they're both FCC, slightly different lattice constants. And in this structure, we do, of course, have broken time reversal symmetry, which means in principle to switch the sign of the superconducting diode effect, we no longer have to apply a magnetic field. We can simply measure, we can set up a magnetic state, switch off the applied field, and then we should get the diode effect. So that's what we're looking for in these devices. So this particular Hall-bar structure has a transition temperature of slightly shy of 5.5 Kelvin, and it's fairly sharp. So it's a robust, well-made structure, I would say. Now at this stage, this is a typical sort of current voltage characteristic data we get. Now this is really complicated, and I'm not sure this is really being very well discussed in the literature, but obviously what we see here is retrapping current. So this sort of data is in fact very difficult to interpret. So you need to be extremely careful, and I will couch some of my comments with concern, but we don't have a good control of either the micromagnetic state or the retrapping currents in our devices. But what you can clearly see in this data is, yes, there's retrapping currents, but there's also an asymmetry between the critical current and the retrapping current between negative and positive currents, which might suggest there is a small diode effect present in these devices. So to try and understand the results, we can do a simple little model of that IV characteristics by taking into account the differential between the positive and negative difference between the critical current and the retrapping currents, and we can define that as a delta IC, or a delta change of critical current, which might be related to a diode effect, minus the retrapping effect, which might, well, which certainly does exist within these devices. Now, the main result I really want to show you is captured here. So what I'm now plotting is the difference in the asymmetry, the asymmetry in the critical current minus the retrapping current as a function of temperature. And what you can clearly see is that this difference decreases as a function of increasing temperature. Now, this particular device has a TC of about 5.4 Kelvin. Now, if this were simply an asymmetry effect in the retrapping current due to the presence of thermal heating phenomena, then I would expect that this asymmetry would increase rather than decrease. So it doesn't, to me, look like that this behavior I'm plotting here can be simply explained on the basis of heating in our devices, nor indeed some complicated retrapping phenomena, unless it's related to the micromagnetic state of our devices, which is, for reasons I wouldn't understand at this stage, dependent on temperature over such a narrow temperature window. It's also important to note that if we drive the magnetization parallel to the applied current, then this asymmetry in the retrapping current disappears. So this is an effect which necessarily requires the magnetization to be orthogonal to the current, which is exactly what you would expect if this were an effect due to broken inversion symmetry and time reversal symmetry breaking due to the presence of an exchange field within the niobium layer itself. So this is very preliminary data, but I thought it was interesting to at least show. This is something we're constantly working on now to try and understand better. And also we're performing detailed STM and scanning magnetic force microscopy to try and understand better the configuration of the magnetic structure for a magnetic field in particular, perpendicular to the applied current, because I suspect it is quite complicated even in these nanowire devices, because we are, by definition, of course, of the shape of a Hall bar, introducing some asymmetry, or some anisotropy due to shape. So to summarize, we've shown evidence for strong proximity exchange fields in niobium, not only in the superconducting, but also the normal state. We see clear evidence for an absolute spin valve effect in niobium europium sulfide, which is novel, with significantly large values of delta TC over TC, which exceed 50% of the superconducting transition. And if you want to create some sort of device in which you can switch the resistance between parallel and anti-parallel, not obviously as a function of temperature, but a fixed temperature below TC, that's exactly the sorts of delta TC over TC values you would need. Also, we see this re-entrant superconductivity out of plane, which I believe is quite novel and certainly not seen before in a strongly ferromagnetic system. And finally, we see some preliminary evidence for the superconducting diode effect. So many thanks indeed. Happy to take questions.
May I ask a question?
Yes, please do, Claudia.
Do you have any strategy for trying to improve the temperatures or of these devices or anything, or to control them? And anything in that direction would be quite interesting.
You mean in terms of the spin valve behavior we see? Well, we have a parallel stream of experiments with oxide materials. So we published a paper 3 years ago now on yttrium-bearing copper oxide on praseodymium serum copper oxide. So you can get these spin valve effects up to around 20 Kelvin in that system. And it's true, but in this system, you also get quite significant delta TCs of around 1 Kelvin. But these are much more complicated material systems to work with. I think if you're going to play with metals, then niobium is a fairly well understood material. And I think if you're going to use this sort of logic in superconducting electronics anyway, then 4 Kelvin operation temperatures are not a problem.
Thank you very much.
Okay, so there are other questions. Otherwise, we thank you very much.
Thank you very much.
Our next talk is Huhtinen from Helsinki.
Yes, thank you.
You can go.
We have a problem with echo, I think. Yes, now it's solved. Thank you for the presentation. So I work in Päivi Törmä's group at Aalto University. And I would like to thank the organizers for giving me the opportunity to show off some of our recent results on flat band superconductivity. Yes, so first I will present some results we have on the superfluid weight in flat bands and how it should actually be computed in mean field theory for multiband models, and how these new equations impact the relationship of flat band superconductivity to quantum geometry. And then I will touch on some results we have on non-isolated flat bands, and in the end of the talk, I will also go over some DMFT results we have for the normal state behavior of flat bands. Now, as an introduction, flat bands, as the name suggests, are completely flat. That means there is no dispersion in K-space. And these kinds of bands can occur in some simple models like the Lieb lattice, which can be, for example, realized in ultra-cold atom experiments. And recently, they have also attracted a lot of attention because they occur, for example, in magic angle twisted bilayer graphene. And why these bands are interesting is that since there is no kinetic energy for particles on a flat band, even small interactions dominate all processes. So flat bands can host various exotic phenomena. And one thing that's a consequence of this domination of the interaction over all other energy scales is that the critical temperature in BCS theory actually is much larger for flat bands at low interactions. So for a dispersive band, the critical temperature is actually exponentially suppressed at low interactions. But for a flat band where the density of states at the Fermi surface is infinite, it's actually proportional to the interaction. So first, I will present some results we have on the superfluid weight. And these are all found in this paper. We have an archive that was actually accepted this week in Physical Review B. And this was done in collaboration with Jonah Herzog-Arvai and Andre Princeton University. So the superfluid weight can be defined as the change in free energy due to a change in the momentum of the Cooper pairs. So we can actually relate it to this second derivative of the grand potential when we add a phase to our order parameters. And why this quantity is important in superconductivity is that BCS theory really tells us only about the formation of Cooper pairs, but it does not tell us if we can actually have dissipationalist transport. For that, we need a non-zero superfluid weight. Another thing is that in 2 dimensions, a better estimate than the BCS temperature for the superconducting transition is actually the BKT temperature. And this is related also to the superfluid weight. And a non-zero BKT temperature requires a non-zero superfluid weight. Now, for a parabolic band, the superfluid weight is just the density divided by the effective mass of the particles. And on a flat band, single particles actually get localized, so they have an infinite effective mass. And this would say that the superfluid weight on a flat band is always 0. So this would say that we can have a formation of Cooper pairs at a high temperature, but we can't actually have a superconductor because the superfluid weight is 0. But it was actually shown in this work by Sebastiano Peotta that the superfluid weight on a flat band can be non-zero because of a so-called geometric contribution to the superfluid weight. And this geometric contribution is essentially an interband contribution. So the conventional superfluid weight is just intraband contributions, and this is indeed 0 for a flat band, but the interband contributions can be non-zero. If we look at the Hubbard model with just on-site attractive interactions and do a mean field approximation, we can actually relate the superfluid weight of flat bands with time reversal symmetry and uniform pairing to the quantum metric, which is this quantity that is related to the block functions of the flat band. And this quantity is 0 for a single flat band if we have only a flat band in the system, but it can actually be non-zero if we have other bands. And so this means that we can have a non-zero superfluid weight even on a flat band if it has non-trivial quantum geometry. And of course, this is an important equation because it means that we can potentially use this, that the flat bands have a higher critical temperature than dispersive bands and actually have a superconductor. And on top of this, we now have a single particle quantity that can predict the superfluid weight. So we could, for example, try to look for ways to increase the quantum metric to try to increase the superfluid weight and potentially increase the superconducting transition temperature. So if we look more closely now at this equation, one way actually that we can increase the quantum metric is to just keep the hopping parameters in our lattice the same. So we don't change the time binding parameters, but we just change the orbital positions in this lattice. And this can actually increase the quantum metric. And if we allow for these sites to even go outside of the unit cell, it will make a very strange looking system. But as a thought experiment, we could make the quantum metric as large as we want and potentially make the superfluid weight as large as we want and potentially make the BKT temperature arbitrarily large. So this seems very promising, but unfortunately is also wrong. Because the thing is that the superfluid weight is actually not affected by these transformations. This is just a conventional Fourier transformation, and it does not change the free energy. So it doesn't change the superfluid weight, but it does change the quantum metric very drastically. So clearly now we have a problem with this equation, because on the right-hand side, we have something that we can make arbitrarily large with a transformation that does not change the left-hand side. So what went wrong here is actually the computation of the superfluid weight. Now, how we can derive this equation is that we start from the definition of the superfluid weight, which is this second derivative of the order parameter. And in mean field theory, it's important to remember that also the pairing gap depends on this wave vector Q. So in principle, using this equation directly would require us to solve also the gap at non-zero wave vector Q. So for non-zero momentum of the Cooper pairs. But then we can actually replace it with a partial derivative if we make the assumptions that I have written below. And this partial derivative is related to the quantum metric. So this gives us the relation between the quantum metric and the superfluid weight. And the third equality here is completely right, and the first equality is also right. But the problem here is the second equality, where we replace this total derivative by the partial derivative. Because in the partial derivative, we actually don't take into account the dependence of these pairing fields on the wave vector Q. And the two assumptions that we made here was symmetry, which is okay because we work in systems with TRS. But the second is that we made a transformation that made the order parameters real. And this is the problematic assumption. And to see why, we can express this total derivative as the partial derivative and then these additional terms that depend on the derivatives of the imaginary parts of the gaps. And of course, if we make the gaps completely real, these derivatives are zero, and we can indeed replace the total derivative by the partial one. And this transformation is possible. The problem with this transformation is that the left-hand side of the equation is conserved, But then these terms on the right-hand side are not actually individually conserved. So that means that if we want to replace the total derivative by the partial derivative by making this transformation, we actually need to know already when we replace this total derivative by the partial derivative that this transformation has been made. So that means that we need to know actually what these derivatives are before we do this replacement, which means in practice that we need to solve for these derivatives. So we cannot in practice usually just replace the total derivative with the partial one, and the superfluid weight is not directly this partial derivative. Now, if someone in the audience has computed these things, this can seem like a daunting task because solving the gap at non-zero Q can be a heavy computation. But it turns out this can also be solved from the ground state at Q equals 0 from this system of equations. So we really need only the knowledge of the state at Q equals 0, but we do need to take into account these additional terms that have been disregarded in previous literature. And as a side note, if we use the usual definition of the superfluid weight in linear response theory and use those equations in mean field theory, we will actually also get a partial derivative and not this total one, so it will give the wrong result. This is explained in our paper, and we give accurate equations in linear response theory. Now, to see how important these terms are that have been disregarded in most of the previous literature, we can look at the superfluid weight that we would get from using just this partial derivative or equivalently the linear response result and compare it to what you should actually get if you take all of the terms into account. So here I have shown the wrong result with the blue dots for the Lieb lattice and the correct result with the red dots. And here we study the Lieb lattice with nearest neighbor hoppings, and we stagger the hoppings by having them equal to 1 plus delta inside the unit cell and 1 minus delta between unit cells. And the effect this has is that it opens a gap between the flat band and dispersive bands that's proportional to this parameter delta. Now, delta equals 0. If we use this simplified equation for the superfluid weight, we get the correct result if we place these A and C sites in the middle of the distance between the B sites of two neighboring unit cells. But if we pick any other positions for these orbital positions, we actually overestimate the superfluid weight. And then when we increase this staggering parameter, this position where we would get the correct result actually shifts away from 0.5. And when we go to the extreme limit, delta equals 1, when the lattice becomes completely disconnected, and in principle, it's impossible to have a superconductor, the correct result is 0. But if we pick the wrong orbital positions, we can actually predict quite high non-zero superfluid weight. So at worst, using these inaccurate equations can lead to qualitatively wrong results where we predict a superconductor where it's actually impossible. So these are really essential to take into account. Now, of course, since these have been disregarded in this relation to the quantum metric, we can ask if the superfluid weight on flat bands is actually related at all to the quantum metric. Well, it turns out it is, but we just need to be more careful than previously. So we know that the superfluid weight is related to this partial derivative, but we need to add these additional terms. And we know that the partial derivative is related to the quantum metric. Now, in a system with TRS, there does exist a choice of orbital positions for which these additional terms are 0. So there does exist a set of orbital positions for which the superfluid weight is given by the quantum metric. The problem is we need to know which one. Here it's actually useful to notice that this matrix A is actually the Hessian matrix of the grand canonical potential. And since the grand canonical potential is minimized for the gaps in the ground state, it means that it's positive semi-definite. So that means that for the diagonal components of the superfluid weight, these additional terms are actually always negative. So that means that we will always overestimate the superfluid weight with this partial derivative equation, which means that the quantum metric always overestimates the actual superfluid weight. And there is this one point where they are equal. So this one point where they are equal is actually a minimum over all the possible choices of orbital positions. So that means that the quantum metric related to the superfluid weight in a flat band is actually the one that has the smallest possible trace. And a similar result was found for the mass of Cooper pairs in this paper that we published. And most of this work was done by Jonah Herzog-Arbeitman. Now, to summarize when we actually need to use these terms, in general, it's going to be needed whenever we have a system that has multiple bands. So this holds for simple lattice models like the Lieb or Kagome lattices, and it holds also for more complex systems like Moire materials, for example. There is a possibility that the spatial symmetries actually guarantee that we don't need these additional terms. For example, in the Lieb lattice, we noticed that this A equals 0.5 choice gives the correct result even with this partial derivative. And this we can see if we look at the system when we pick the orbital positions at 1/2 minus x or 1/2 plus x. And you will notice that this system is the exact same up to an overall rotation. So that means that these have the same partial derivative. And we know that the correct value for the superfluid weight occurs at a minimum, and this is a symmetric function of x. So x equals 0 will be the correct choice. So A equals 1/2 gives the correct positions. But then if you don't have enough symmetries in the system, it may be that you cannot find this correct position with any easy way like this. And the big lesson to be learned here, I think, is that when we relate the quantum metric to physical quantities, we should be careful about which quantum metric we relate. So this quantum metric has been related to other quantities, such as the effective mass of two-body bound states or conductivity or the properties of Bose-Einstein condensates. And in all of these cases, we should think about which is the quantum metric that we are actually talking about. So now to apply these new equations we derived, I will look at the Lieb lattice and the superfluid weight in the Lieb lattice. And here you can see the total superfluid weight as well as the geometric contribution to the superfluid weight. And this geometric contribution is really dominant at low interactions because we are on a flat band, so there is no intra-band contribution to the superfluid weight. And then when we go to higher interactions, because the dispersive bands also have a role, we start getting also a conventional part, but the geometric contribution is always dominant. And we also notice that this prediction from the minimal quantum metric agrees very well with our prediction of the superfluid weight whenever we are on an isolated flat band. So indeed, this minimal quantum metric is related to the superfluid weight when we are on an isolated flat band. And the last thing is that the superfluid weight is actually the largest when we take delta equals 0, which is the non-isolated flat band. So this would indicate that to get the highest possible critical temperature, it's actually good to have a band touching with a dispersive band. To verify that this also reflects on the BKT temperature, we solved it in the Lieb lattice again and also on the square lattice. And the square lattice, you can see that at low interactions, it becomes exponentially suppressed, which is the same behavior as the BCS temperature. And then the BKT temperature on the flat band is roughly proportional to U. So that means that at low interactions, flat bands are better than a dispersive band if we want to increase the BKT temperature. And also we find that the BKT temperature, just like the superfluid weight, is actually the largest when we go to the limit of non-isolated flat bands. So this would indicate that if we wanted to use this to, for example, engineer materials with the highest possible TC, it would actually be good to have a flat band that has a band touching with dispersive bands. Now we will move on to the non-Fermi liquid behavior we found in the normal state of the flat bands. So here again, I will study the Lieb lattice with nearest neighbor hoppings. And an attractive interaction in the Hubbard model. And for this part of the talk, it will be important to notice that the flat band states on the Lie lattice actually occupy only the A and C sites, and they don't occupy this B site at all. And this means that if we see any flat band effects, we would expect to see them mainly on the A and C sites. And to study the normal state, we used dynamical mean field theory, where we used the unit cell as our cluster, which means that all the correlations in the cluster, which is the 3-site unit cell, are taken into account exactly. So what we found is that the spin susceptibility starts to decrease with temperature at some point, and this we can track back to the local contributions to the spin susceptibility from the A and C sites, which are the flat band sites. And this drop in these local contributions happens at the temperature that's roughly proportional to the interaction, which reflects this fact that there's no kinetic energy on the flat band, so the interaction is the only energy scale, really. And this we can understand as the formation of a spin gap because of the formation of pairs in the normal state above the critical temperature. And to verify that we have this kind of pseudo-gap behavior that has also been predicted in Monte Carlo studies, we can look at this Green's function in the middle of the imaginary time axis, which approximates the spectral function at energy 0. And here we see that when we increase the interaction, this peak at mu equals 0, where we expect delta peak because there's a flat band, actually gets suppressed. So we indeed have some kind of pseudo-gap behavior that becomes more pronounced when we increase the interaction. And then when we go to lower interactions, this is actually where the very unique properties of the flat band start to become more prominent, because we know that for 0 interactions, the flat band should actually be an insulator at t equals 0. And this is because the single particles become localized in this flat band state, and they cannot move because of destructive interference. So we know that it should approach this insulator limit. And what we found is that when we decrease the interaction, we actually have a crossover to this kind of insulating behavior, which in DMFT we can look at with the imaginary part of the self-energy, which is related in the Fermi liquid theory to the effective mass of quasi-particles. And so for Fermi liquid, we expect to have a nice linear behavior of this imaginary part of the self-energy. And this is what we observe for the B site, where the flat bands do not exist. But then where the flat band states actually occupy the sites, we see that we start to develop divergence at omega equals 0 in this self-energy. And we checked that at u equals minus 0.5, for example, this scaling is t to the minus 1/2. So there is indeed a divergence of this imaginary part at the lowest Matsubara frequency, which indicates insulating behavior in DMFT. And we don't know where this factor of 1/2 comes from, but we do know it is different from, for example, Mott insulators, where we would get something that scales as the inverse of the temperature. So in the flat band, we have a crossover from a state with insulating characteristics at very low interactions to a pseudo-gap state at higher interactions. So in summary, when we relate the quantum metric to physical quantities, we should really take care in verifying that the quantum metric is indeed conserved under transformations that are supposed to conserve this quantity. And as we saw with our new equations for the superfluid weight, the highest critical temperature for flat band can actually be found for non-isolated flat bands. So that means that if you want to find the highest possible critical temperature, we don't need to isolate the flat bands, which can be beneficial for experiments. And finally, the normal state is also influenced by the unique properties of the flat band. And with this, I end my talk, and thank you for listening.
Thank you very much. Your beautiful talk, very stimulating. Is open for discussion. We have a question from Jotzu.
Hello, thank you for this very interesting talk. I had a quick question. I remember there was this result that if you have a topologically non-trivial band, the Chern number gives you a lower bound on the superfluid weight. Does that result still survive your more advanced analysis now?
Yes, that result actually survives because the Chern number is a lower bound for any positions we pick. So that means that it's a lower bound also for the minimal quantum metric.
Okay, very interesting. And the quick follow-up question, if I make a flat band by applying periodic driving, so I do a kind of Floquet engineering approach to making the band flat, should I think that I might still have a non-zero quantum metric because I have Floquet side bands, or is it just going to be a trivial zero tunneling flat band?
This I actually do not know. I would have to look a bit more into it. I have not looked at these Floquet systems.
Okay, thank you very much.
Thank you very much. There are other questions. So we thank the speaker. Thank you very much.
Thank you.
Next speaker is Professor Maialle from Brazil, from Mexico. Okay, you can come.
Hello. My name is Marcelo Maialle, and I'm from State University of Campinas, Brazil. And the outline I'm going to talk today is simulation that we have done for a nanostructure, which we call constricted nanoribbon superlattice. The first part of my talk, I will address our results for this nanostructure when using materials parameter for my album, the selenite. And the highlight here is that we have found a gapless superconducting state, which is sustained by multiple channel interactions. The second part of my talk is still solving the same system, but now for materials parameters for nanolayer of a superconducting material that is multi-band, namely in this case, magnesium diboride. The highlight here is that we have found, let's say, an unusual effect, which we call remote Feshbach resonance between mini-bands. Before we start, let's acknowledge my collaborators, Professor Marcos Degani at Unicamp, and also Wojciech Pasek, which is the postdoc who has done most of the work, and he has a talk after this one. And also we have the collaboration of Dr. Marcio de Andrade at Naval Information Center at San Diego. And we have been funded by the Office of Naval Research. Well, let's talk about the system that we are solving. It is a nanostructure. It is a planar one, so it doesn't have a thick in the z direction. It is very long in the longitudinal direction, and it has a finite size in the transverse direction. So you can call this, let's say, a nanoribbon. And we have a constriction in this nanoribbon, which is periodically placed along the nanoribbon. And it is important to realize that this constriction is asymmetric. So this helps to mix the degree of freedoms along the nanoribbon and transverse to the nanoribbon. Okay, we are going to use periodic body conditions for the longitudinal motion and hard wall boundary condition for the transverse confinement. The most natural question is why this constricted nanoribbon? Of course, we do not expect having this grown by experimentalists. For us, it is just a versatile playground to study superconductivity. Okay, why? Because it is planar, it is quasi one-dimensional, so we have a set of subbands. It has a periodicity along the nano ribbon, so this gives us mini band dispersions. So we have here a system with several bands, and so you can play with the interaction between these bands. Okay, and of course we also have geometric control. By changing the geometry of the system, we can play with the properties of it. And of course, it is computationally cheap for us because we only needed to solve a two-dimensional problem within the unit itself. Okay, of course, we are motivated by previous work, for instance, in superlattice, for instance, in steps and single constrictions, and more recently in arrays of Jotzu junctions, which were built by ion damage. Well, the method that we use is to solve the Bouguereau-Boff-Digenis equation, which is here. We explicitly factorate here a plane wave with a quasi-momentum along the nanowire, the nano ribbon, and this quasi-momentum will show up in all the dispersion relations that I show in this presentation. We also introduce a phase difference per unit cell, and this phase difference will allow us to calculate supercurrent. And it is important to note here that the phase difference shows up for the hole and for the electron with a different sign, a plus or minus sign. And the order parameter that enters in the off-diagonal term here is the term that will mix different states. Notice here that we can have mix for different Qs, that is for different states along belonging to the same mini band, but you can also have coupling between different mini bands. And we are using the Anderson approximation, meaning that we write everything in terms of the single particle wave functions. So this is pretty much a standard procedure. Okay. Before showing up the results, I think it's better to show two cartoons that explains the simple physics that we are going to see. For instance, here I have an example of a mini band which has a cosine shape being crossed by the Fermi level, and with that you have the whole contrapart. So these two mini bands are degenerated in 2 points in this dispersion. It is in these points that superconductivity mixing is strongest. It is where the superconducting gap is formed. When we introduce the phase difference, what happens, as I told you, the electron and hole dispersions shift relative to each other. And what that has, the effect that it has is basically decreasing the gap and eventually vanishing the gap. Okay, so here are the results. In the left column, I show the dispersions of the single particle for different constriction of the nanoribbon. For instance, here, for very slight constricted nanoribbon, you can see a set of parabolas. For instance, here we have a parabola here, and you have a second parabola in here being reflected at the edge of the Brillouin zone. And why you have two parabolas here? Because of the system is finite along the transverse direction. So we have quantized states in transverse directions. When we increase the constriction, what you see is that these dispersive parabolas becoming more flat bands, meaning that the electronic states are being more localized within the unit cell. Well, we have decided to study superconductivity here by varying the Fermi energy. And on the right column here, I have the results for the superconductivity as a function of the Fermi energy. And what you see here is the average order parameter as a function of the Fermi energy. And what you see is that the order parameter follows very closely the density of states of the mini bands. This is an expected result. And here in the middle, by the dashed line, we see that when we apply a phase difference, and the superconductivity is suppressed. Okay? This is also expected. A little bit more about the phase difference effects. In this case, I have, I'm showing here 3 minibands, and miniband 1, 2, 3, with increasing bandwidth. Okay, so if you look at miniband 1, which is a narrow bandwidth, and you calculate the gap as a function of the phase difference, you see that you have a maximum gap for 0 and plus or minus pi of phase difference. And you have a maximum and a minimum of when the phase difference is plus or minus pi over 2. For the other minibands, what you see is that the gap disappears for phase difference closer to pi over 4. I mean, this is expected because these minibands have a larger bandwidth, and if you have a larger bandwidth, these crossing points here can move further up and further down, and the gap can be destroyed. Okay, so this is expected. We have used these results to calculate the current, the supercurrent through the nanoribbon, using the wave functions that we calculate for each of the phase difference. And when you do this, we have this phase current relationship, which for the case of miniband number 1 is a sine. This is typical for Josephson junctions. Okay. However, when you have a larger miniband, when you have no gap, you have no supercurrent, and that has an effect of a limitation on the critical current of let's say, a device made of this nanoribbon. And so far, the results are very much expected. And here we have a kind of unexpected case in which we look at this miniband number 3 in the case of very small constriction. And you can see here that you have two sets of parabolas, and they intercepting here, and this miniband number 3, when you apply a phase difference, what you see is that you can have superconductivity, that is, you can have another parameter, but the gap is closed. Okay, so this is a gapless, let's say, a gapless superconducting state. To investigate the reason behind of this occurrence, you first notice that this miniband number 3 doesn't look like a cosine. It has a double frequency. Even more, if you take any state close to Q equals 0, the state has a parity that is odd, even along the transverse direction. But if you take a state close to the border of the Brillouin zone, the symmetry of the state changes. Okay. When you apply a phase difference to this miniband number 3, what you see is again that shift for the electron in a whole wave function. And what occurs here is that we no longer have only 2 points, crossing points of the minibands. You have 6 crossing points of the minibands. It is in those points that superconductivity is stronger. And you can see in point number 1, point labeled A, that the superconductivity is the strongest. In point B, the superconductivity is weaker, and the gap is closing. There is a closed gap here. Okay, and we then investigate how these crossing points are interacting with each other. So, for instance, we turn off manually in our calculation the interaction of this point A, with the other minibands. Okay, when you do this, superconductivity vanishes completely, meaning that you are seeing here superconductivity, and the superconductivity is being sustained by the interaction of all these points. We can say all these channels, superconducting channels. So that's the first part of my talk for niobium diselenide. This has been already published, and this serves for us as a motivation to investigate multiple channels, coupling of multiple channels. So the next part of my talk, I'm going to change the materials, and I'm going to use a material that is already a multi-band material. So we have chosen to to investigate magnesium diboride, which is known to have a pi band closer to the gamma point, and a sigma band close to the gamma point, and a pi band at the edge of the Brillouin zone. Okay, this is a multi-gap structure, and we're going to use this material to simulate our nanoribbon. Okay, of course, our calculation needs effective mass. So we have borrowed the dispersions from ab initio calculation for fuel layer of magnesium diboride. So you have fit this dispersion by parabolas, and from that we get a set of mini bands. Actually, a set of sub-bands here. In this talk, I'm going to say only the results about the very lowest energy sub-bands here, which I call sigma 1 lower. In the next talk, you're going to hear about the other mini bands and how they are coupled together. Okay. So here is the result for the sigma 1 lower mini band. These are the mini band dispersions, and you see here a gap forming for mini band number 2. It is important to note to mention that in this case the Fermi energy is not varied. We take it from the ab initio calculation. Okay, and you see then the gap being formed at mini band number 2, and this is the Debye window. Inside of the Debye window, all the other mini bands are being affected by superconductivity. But what called our attention is that mini band number 4 has a very strong shift. Okay, so we want to investigate why this mini band, which is very close to the edge of the Debye window, is interacting strongly with mini band number 2. Okay, so we decided to make here a study by varying the strength of the superconductivity coupling. Okay, how strong is the superconductivity coupling? This is for us a free parameter. Of course, if you have a small value for this parameter, the gap is closed. There is no gap here, and there is also no average order parameter. So there is no superconductivity. When you start increasing this parameter, you see the gap opens, and at the same time, you have the appearance of the order parameter. Okay, so now to investigate the role of this mini band number 4, why it is being shifted so strongly, we have again turned off the interaction of this mini band number 4 with the other mini band. So we isolated this mini band from our calculation. And the result that you get is given here by this dashed line. So there is a suppression in the superconductivity when you discard, let's say, mini band number 4. When you include it again, you have this enhancement of the superconductivity. More than that, looking at the order parameter within the unit cell, you can see here it has a symmetry. And if you look at this symmetry, for instance, in the case that there is no mini band number 4, okay, you see that this symmetry of the order parameter is similar to the symmetry of the mini band that is crossing the Fermi level. So the mini band, the order parameter has the symmetry of the mini band that is crossing the Fermi level. However, when we include back mini band number 4, you see that the order parameter changes symmetries, and if you look for this symmetry, we will see that this symmetry is related to the symmetry of mini band number 4. So in this case, not only mini band number 4 is enhancing superconductivity, but it's dominating the symmetry of the order parameter. Okay, so with these two things together, enhancement of superconductivity and change of symmetry, we call this effect as a remote Feshbach-Fano resonance between mini bands. Why remote? Because these two mini bands are not overlapping energetically. Okay, in fact, they are mini band number 4 is almost at the edge of the Debye window. Okay, and it is still has the ingredient of fresh Bafano resonance, because this miniband is a flat miniband. This miniband number 4 is a flat miniband number 2 is a dispersive miniband. Okay, and this also has an effect on the phase difference. For instance, when we disconsider miniband number 4 and apply a phase difference, what you see here by the green arrows is that the superconductivity is strongly suppressed. We need more J0 to get superconductivity. Okay? However, when we include back miniband number 4 in our calculation, we still have a suppression of the superconductivity by the phase difference. However, the suppression is weaker. Okay? We can understand that because this miniband number 4, which is dominating the superconductivity, it is flat. So it has a weak dependence on the quasi-momentum. And we know that the phase difference, what it does, shift the minibands relative, the lateral hole minibands relative to each other. So this shift is not as important for miniband number 4 as it is for miniband number 2. Okay, so this is another effect of this remote Pesch-Bafano resonance. So as a summary, I think we have shown that this system shows a very interesting interaction between minibands. Miniband number 4, which is at the edge of the bio window, is enhancing the gap and enhancing the order parameter. It is also dominating the symmetry of the order parameter, and it has the effect of weakens the phase dependence of the superconductivity. We call this remote funnel resonance between minibands, and this is accepted to appear in physical E. I guess with that, I thank you for attention. Congratulations to the organizer for this conference. Thank you. I'm open for questions. I guess it will work for bigger dimensions. For instance, I'll give an example here of this magnesium diboride monolayers. Each of these lines are for one layer. So when you put more and more layer, actually you put more and more subbands. Okay, so far I showed you the result for only one miniband. You're gonna hear now, next talk, the result for other minibands, and you can put more and more and more. Okay, so this is a work in progress, putting all the others minibands, subbands. Well, we have done this, but I mean, within the Boglu-Bobdidjan's equation, I guess you can do it. It enters in here. The Hamiltonian will be bigger, but I mean, it can be done in principle. Question? Okay. Thank you.
So, hello to everyone. My name is Pasek, and I'm going to present the second part of the presentation given by Professor Maialle. So, when he talked about what was already published, I will give a brief overview about our work in progress. So, the other authors of our work are, of course, Professor Maialle and Professor Degani from our group at FCA Campi in Brazil. And we also have a collaboration with Dr. De Andrades from USA. And our work, as previously mentioned, was funded by the Office of the Naval Research Group. So I will not waste many of your time introducing the system we work in, because it was given by Professor Maialle, but I will just remember that we work in the envelope model put on top of the Bogomolov-Degen's equations. So our aim here is to establish a model that will be able to describe the nanostructure scale effects of the quantum confinement of the superconductivity as opposed to the atomistic scale effects. And it will be able to include electrically active systems for which we, as was already mentioned, needs the phase difference included in the model. So firstly, please let me explain a little bit about the terminology that I will be using during this presentation. So the bands, subbands, and mini-bands. On the left-hand side, you can see the dispersion relation of the bulk magnesium diboride. So as probably everybody knows, the Fermi surface in this material is consists of a pair of sigma bands and a pi band. Now, when we move from the bulk magnesium diboride to the same material, but which has, for example, 6 monolayer of thickness, where each of the bands is splits into a series of the what we call subbands. So we can see a multitude of sigma subbands near the gamma point and some pi subbands in the maybe here. A multiple of sigma subbands near the gamma point and the pi subbands here. Now, it's important to point out that this kind of splitting has nothing to do with our nanostructure yet. It is only due to the finite thickness of the material. Now, when we put on the top of this the quantum confinement of our constricted superlattice nanostructure, and the periodicity of the superlattice, we will get in the end effect the splitting of each of those submaterial subbands into a series of mini bands, which each set corresponds to a given subband. Okay, so after this introduction, let me just discuss a little bit the general idea of the model. So this is the version of the model that was discussed by Professor Maialle. So for each of the subbands, we have a series of mini bands. In each of the mini bands, a mixing between the electron-like and hole-like parts could happen. And this mixing contributes to, but also is provoked by the order parameter, so the condensate corresponding to a given subband, so in this case, subband A. But also it can introduce mixing and be sustained by mixing. That's a two-way relation, but each other mini band belonging to a given subband, and not presented on this diagram, but also needs to be mentioned at each other Q point in the superlattice Brillouin zone. Now, the same happens with subband B, but at this level of the modeling, they are not, let's say, coupled together. However, the results that I will be showing during this presentation correspond to the model where the mixing between a mini band belonging to one of the subbands can also sustain or be provoked by the order parameter in different subband. So this is like a inter-subband coupling, and in order to differentiate between those two mechanisms, we introduce on top of J0 parameter, as in work of Professor Maialle, we also introduce J1 parameter, which is corresponding now for the inter-subband coupling. Okay, and one final thing of introduction is in the introduction is to talk about the phase difference and its relation to the supercurrent. So let's consider Josephson junction. As everybody knows, the relation between the supercurrent flowing through the Josephson junction and the phase difference, that is the difference between the phases on the two sides of the Josephson junction, is given in most typical cases by this sine-like function. So the IC parameter here is the critical current. Now, we consider our system of constricted non-ribbon superlattice as nothing else as a periodic chain of strongly coupled Josephson junctions. So we introduce the phase difference per one periodic cell of the superlattice, and in practice it amounts to nothing else that this shift in terms of the Q of the superlattice wave number that Professor Maialle was talking about. Okay, so moving to the results. So it will be, I guess it will be beneficial to first present some preliminary approach to the system. So let's consider a system that takes into account two subbands, sigma 1 lower and sigma 2 lower. And here we can see the gap in the bottom and the mixing corresponding to the system. So here we present two versions of the model. The dashed lines correspond to the system where the subbands sigma 1 and sigma 2 lower are uncoupled, while the solid lines correspond to the system where the coupling is J1 is proportional to J0. Now, the dark red line corresponds to the sigma 1, and the yellow, I mean, the green line corresponds to sigma 2. Okay. Now, in order to understand what is going on in the diagram on the left hand side, one needs to start analyzing the set of the normal state, so not superconducting yet, mini bands of the system. And the one corresponding to sigma 1 lower is shown here. So as you can see, the one of the mini bands crosses the Fermi level, as is the usual situation in the metal-like structures. However, for sigma 2 lower, we have a qualitatively different situation. That is, the Fermi level is not crossed by any of the mini bands. However, one of the mini bands is pretty much close, but there still exists this insulating gap in the system. So a system without any coupling has an insulating like character. So having this in mind, it should not be a surprise that for a very small values of the coupling parameter J0, the gap is closed for sigma 1 lower, the metallic-like, but it stays always open for sigma 2 because here we encounter this insulating type gap. Okay, now when we move with J0 to a stronger regime of J0, at some points, of course, the gap will open, or additional gap will open in this case, and in the same moment, the mixing, electron hole mixing starts to appear in the system. Now, generally looking at this picture, we can see that introducing the inter-subband coupling leads to the enhancements of the superconductivity. Please compare the solid lines to the dashed lines. Now, there is also important fact of coordination of the superconductivity. For example, the place where the values of the J0 when the gap starts to open in both of the subbands is not coordinated for the uncoupled system, obviously. However, it very quickly gets coordinated as we increase the value of J1, that is the coupling of the value of the coupling between the subbands. Also, maybe one thing that could be interesting is the crossing between the gaps which happens here, which means that the minimal gap of the overall system of two subbands switches its character from sigma 1 lower here to sigma 2 lower here. Now, those were only the preliminary results. However, our aim here is to obtain the phase map of the system, meaning that we would like to analyze the same quantities as in the previous picture, that is the gaps and the mixing for both of the subbands in the system. And we will identify quantitatively different states of the system and the phase boundaries between them. So here is what I consider the main results presented during this talk. So those are results for sigma 1, sigma 2, the same system as before. However, here we vary those parameters, J0, so intra-band coupling, and J1, so inter-band coupling, as two independent parameters. Now there is a lot of pictures here. So let me say that in the top row we can see the maps corresponding to one of the subbands, sigma 1 lower. The middle row shows the gap corresponding to sigma 2 lower, while in the bottom band, in the bottom row, we can see the phase map of the system. Now, about the phase difference, in the left column, we can see the results corresponding to the situation when there is no phase difference in the system. In the middle, to pi over 4, and here we have the phi equal to pi over 2. Okay, so first thing to point out is that in most of the cases, there is a quasi-diagonal, quasi-linear diagonal character of those isolines in gaps in most of the cases. This is a signature of the linear constructive interference between the condensates corresponding to sigma 1 and sigma 2. By linear interference, I mean specifically that while the gap should be, in this case, in principle, a function of two parameters, J0 and J1 independently, you can approximately represent this as a function of one argument, which be a linear combination of two, that is J0 plus C, some scaling factor, times J1. And this C scaling factor is a positive number in most of the cases, which means that we have a constructive interference between the condensates. Right, so let's focus first on the results corresponding to the situation when we have no phase difference. If it is not a surprise that if J0 and J1 should go to 0, of course, we will have no superconductivity in the system. And in fact, system starts with the phase we call N, which is a metal state for sigma 1 and insulating like state for sigma 2. Then, when we increase the value of the couplings, we cross this green line. This green line corresponds to the opening of the minimal gap for sigma 1, and then the system enters into phase S1, which is corresponding to the situation where you have open gap and you have coupling mixing within the subband 1, but there is nothing for subband 2. It stays insulating. At some point, you will cross this black line here, which corresponds to the opening of the gap in the other subband in sigma 2, and then you will enter this phase which is called S12, which corresponds to the situation when you have both mixing and open gaps in both of the subbands, and the minimal gap of the whole system is the one corresponding to sigma 1. As you remember, I showed you before the point when the gaps are can cross and the character of the minimal gap is switched. This corresponds to this blue line here, and in fact, this phase S21 corresponds to the situation when in both subbands we have superconductivity and mixing, but the minimal gap is the one corresponding to sigma 2 instead. Okay, so after discussing that, we should ask ourselves the question, what is the impact of the introducing non-zero phase difference in the system? And first thing to point out is that below the cyan line here in the results for the gaps of both subbands, the diagonality of the lines have swept to opposite one, which means that we are still in this linear interference regime. However, now, because of the swept diagonality, we don't have constructive, but we have destructive interference between the condensates. And in fact, this is the origin of the new phase S*12, which is pointed out here, which signifies that we, in this state, if we increase the interband coupling, instead of increasing, you will have a decrease in superconductivity. The other difference introduced by the non-zero phase difference is shown here in the origin part of the superconductivity, which you can see here in magnification. So here there is a curious situation, because starting from a normal state, we will cross the black line, which corresponding to the opening of the sigma 2 gap. However, one should maybe expect in this situation that it will the system will enter phase which would be called S2. So one of the gaps is already closed, and you already open, and you have mixing, but there is no superconductivity, no mixing in the other one. And in fact, it happens, but in only for a very, very small value of J1 interband coupling below this orange line. This orange line represents the mixing, not the opening of the gap, but the mixing that is showing in sigma 1. And you can see that maybe this is something interesting. It is not aligned in the majority of this phase map. It is not aligned with the green line, that is the opening of the gap with within the same subband. It is aligned with the black line. So the mixing is aligned to the opening of the gap, but in the other for the other subband, in the other condensate. This signifies that the system enters into pseudo gap state, in which the superconductivity is generated in the subband and by the condensate, which has the gap open and mixing generated, non-zero mixing generated, and then through this non-zero J1, non-zero coupling, the mixing is kind of injected into the other subband, but not so much as to open the gap. So the gap still is closed, but you have injected mixing, so we enter into pseudo gap state. Now, of course, if you increase the value of the coupling parameters, you will land into S12, so you will get superconductivity in both of the bands and the gap open. Now, moving from pi over 4 to pi over 2, you will see that you can see that the order, the sequence of the phase on the phase diagrams is the same. Phases in the phase diagram is exactly the same. So qualitatively, you have the same result. However, quantitatively, the values of the gaps and the values of the required J0 parameters is changed, so that the superconductivity is diminished even before, even in a larger scale. And this is, of course, because there is a bigger mismatch between the Q positions between the electron and hole. Now, one last thing to point out on this slide is that even very small value of the J1, so even very small inter-subband coupling is efficiently organizing or locking the phase boundaries between the two different condensates, two different subbands, as you can see here. And even for very small J1, they start to run in parallel. This is, of course, expected because now you have coupling between the subbands, but maybe the interesting part here is that in case of non-zero phase difference, you remember we have this pseudo gap state. And because of those two, this coordination, those two lines begin to run closer and in parallel to each other, which signifies that interband coupling JZ decreases the pseudo gap effect in our system. Okay, so those were the most important results. Now I very quickly want to just point out some additional remarks. So we also have calculated the results for the sigma 1, sigma 2 upper, so the other pair of the sigma subbands. But as of now, we only have the results for no phase difference. And if you compare those results with the one from the previous subband pair, you will get some important observations, or maybe curiosities. So, for example, this deviation from the diagonality of the isolines is one of the things. Another thing that there is much more swapping between the minimal gap between sigma 1 and 2. And the third one is that this coordination between the phase boundaries of two subbands is nearly instantaneous. Very small J1 is sufficient for this. Of course, one one can understand easily this change in qualitative change in behavior while looking on the normal miniband set for each of the subbands. Now we don't have this insulating case, but in case of two sigmas, you will have Fermi level crossed by the one of the minibands. Here you have another miniband lying very close. Now here you have two minibands crossing the Fermi level. So not exactly the same, but very similar character. If the superconductivity in both of the subbands, even without any coupling, has a very similar character, then of course there should be stronger interaction between them. As in when you compare the situation with when one is quasi-metallic-like and the other is insulating-like. Okay. Oh, we also have, as more as a curiosity, have calculated the situation when you have J0, the coupling strength J0 and J1 of two different opposite signs. So this would correspond to the situation which was considered in this work in Innocenti 2010, when kind of two condensates are from the beginning set to work as opposite to each other, and we should see some negative, the destructive interference between them, even when there is no phase difference introduced to the system. And in fact, this is what we can see for positive and for negative values of the inter-subband coupling parameter. In general, you have the mirror image of its other part. So this would correspond to the situation when the system is not reacting to the values of J0, J1, but only to the absolute values of that, the magnitudes. The phase is not important. But this is not the case in this region, the region of big J0 and small J1, when those isolines for a positive side continue in a smooth way to the negative side. And here we again obtain this S star special phase when we have destructive instead of constructive interference between the condensates. And the very last remark is that we also have studied the impact of the remote Feshbach-Fano resonance, which was previously described by Professor Maialle in our system. So basically, I can sum it up that there is no qualitative impact on the phase diagram. The phase map is the same qualitatively. However, there is very strong quantitative impact. That is, the remote Feshbach-Fano resonance introduces very strong enhancement of the superconductivity. Okay, which leads me to my conclusion that which is on a very general level, that the new and interesting physics is waiting to be explored in the magnesium diboride several monolayer superlattices, and they are consequences of the interplay of the following factors. First, we have three levels: band, subband, and miniband of possible coupling mechanism, and the second part is the interplay of that with the phase difference imposed on the system. And with that, I will thank you for your attention.
So thank you very much for this very interesting talk. The paper is open for discussion. There are some questions. Can you describe some possible technical possibility to apply to realize your geometry in real materials?
Well, as the model is in this moment, not yet. However, Professor Maialle was presenting that one of our motivations was this array of Josephson's junctions, which are in fact realized in magnesium diboride by bombarding with the focus ion beam, right? So it introduces damage, and then you have the modulation that you need to create the constricted superlattice. Now, this is not done, in fact, for several monolayer material, but a thicker one because of the technical limitations. However, generalizing our model to this kind of system, which is in fact has been produced very reliably produce and with great precision of defining the geometry of the superlattice is very much possible. And in fact, it is what we are considering to do to be the next step.
Thank you very much. So we thank all the speakers of this session, and we have now the lunch break. Thank you very much.
Hello, everybody. We are starting the last session of this conference. Before starting with the next speaker, I would like to announce that the coffee break will be postponed to 5 p.m. So now we start with the Bob Joseph. Bobby, can you share your presentation?
Yes. Okay. I guess
Yes, you're seeing it, but it is not in the presentation mode.
Yeah, okay.
Yes.
Okay.
Good. You can start.
Okay. Good afternoon, everybody. It's let me thank the organizers for inviting me to be here with this interesting conference. I really miss to be there in presence there in Frascati. However, I guess I can give my message here and eventually have discussions with you guys. Okay. Title of my talk is Role of Crystal Lattice in Pressure-Induced Electronic Transitions. So basically, I would like to discuss a few examples of the works we are doing for last few years. This is one of the main theme which I am involved. So I'm from Electra Synchrotron, where we have a high pressure diffraction beamline where these works are being carried out. Basically, I will talk today about three systems. One is a quasi-Scottrite type single crystal system. The chemical formula is here. It is scandium 5, rhodium 6, tin 18. The second system is lanthanum gold antimony 2 charge density wave system. The third system is the classical two-dimensional dichalcogenide titanium tellurium 2. So all these systems somehow have a connection to the superconductivity, and that is where I am interested in discussing these results in this conference. So as I told you, I work in Electra Synchrotron, where we have a nice international collaboration existing between India and Italy in the maintenance and development of a high pressure diffraction beamline. This is a real nice international collaboration. I thought it may be also a nice occasion to give a few slides on this activity. So this beamline is a relatively new beamline, one of the new beamlines in Electra. It started operational in 2016. This is a rather simple beamline which is dedicated to high pressure diffraction studies. So we are a fixed wavelength beamline. We are working at 25 keV, which is good for high pressure diffraction. The good thing is we have a superconducting Wigler source. This is the unique superconducting Wigler source in Electra, which is shared with another macromolecular beamline XRD2. So we are a high flux beamline, and it is rather simple to operate. In the initial days, we had a moderate start. We had a rather low end detector MAR 345. Although the performance were good, but it is not the best detector considering the development in the detector technology these days. So very recently, in connection with the upgrade program of Electra, by the way, Electra is going to have an upgrade. So it's going to be a new ring with increased performance in its thing. So in this connection, we got a new Pilatus 3S6M detector, which really changed the game. So we have now this new detector, which is commissioned very recently. And the detector is working very well. It's doing very good. So this detector was very important for us because even before the arrival of this detector, we have developed high pressure single crystal diffraction experiments with the old MAR 345 detector in connection with the Department of Geoscience from University of Milan because they had a big interest in developing single crystal setup for studying the minerals under pressure. So this development was there, and it was the right time to replace the detector, which has much readout time, with a brand new detector. So the new detector not only helps the single crystal diffraction, but it also helps in powder diffraction, of course, due to the large single photon counting and large counts it can accumulate. So we have this detector fully commissioned and it is running now. So the beamline is really user-friendly. We have a standard Ruby fluorescence for the pressure determination. All these things are controllable from outside. We recently added a high temperature setup to the beamline, which is permitting us to do both the simultaneous high temperature and high pressure experiments. Here is the schematic view of the setup. This is a resistive heating based setup which will permit us to go to easily to 800 Kelvin and then do the high pressure studies. So this is the actual setup in the beamline and a zoom view of the beamline. We also have developed in-house the cryogenic loading systems for the pressure transmitting medium. So we can use oxygen, argon, nitrogen, all these cryo systems as the pressure transmitting medium, which is again advantageous to the several experiments. We also got a low temperature setup where we can go to down to 20 K using a closed cycle helium cryostat. And then we can do powder diffraction measurements up to 20 GPa, which is the limit of the cell available with the system. So here is the photograph of the cryostat mounted at the beamline. It's a bit bulky, but its performance is found to be good, and there is it's also fully commissioned. So just to complement with the diffraction studies, we also got from our partner institute, Indian Institute of Science, a micro Raman setup, which is a Rainy show class for Raman spectrometer. Which can be coupled with a diamond and wheel cell to do high pressure Raman measurements. Then in a way we can couple Raman and diffraction measurements to have simultaneous measurements of high pressure diffraction as well as high pressure Raman studies. So all these instruments we are really planning to arrange suitably in a high pressure lab, which we hope to have it in very soon, very immediate future. So let me come to the interesting scientific talks, scientific topic of my talk. So I would like to first discuss about the pressure enhanced superconductivity in cage type quasi-scutite single crystal compounds. So I will show results from only this scandium based compound, where the scandium is the rattling atom sitting in the cage of tin atoms. We have started this field where we have at least studied 3 types of interesting systems, and we have quite interesting results, maybe which will permit us to discuss further about these kind of systems. Then I will discuss about a classical charge density wave system, which is a ternary antimonide again. This is lanthanum gold antimony too. So what results we have from there, and then I will go to this titanium telluride too. So coming to the first system, this is the scandium based scutite systems, where the scandium is the rattling atom. So we did systematic high pressure diffraction studies. Here are the results. And we also realized that the system is having nice to Raman modes, and which was never studied from the Raman point of view. It is a metallic system, and the signal was very weak, but there is a good signal which is strictly connected to the rattling atom in the system, and we can follow the pressure dependence of the system. So this study is done in collaboration with a Indian high pressure group, which is interested in the superconducting systems. In particular, there is Govind Linganan, who was with us for 6 months' time through a ICTP based trail program. So here are the results. In CHPR Tiruchirappalli, the center where this boy came from, so they could study the pressure dependence of the superconducting transition temperature. So we see there is an increase in the transition temperature with pressure up to the maximum pressure they could study, that is up to 2.5 GPa. Although the increment is less, but it's a consistent regular increase in the pressure. If you look at the structure, the structural properties are very regular. There is a regular volume compression, which can be easily well described by a second order Birch-Morgan equation of state. And if you look at the Raman bands, so we analyze the Raman, the two modes which we see as 3 components. So we see all the 3 components, they have a regular pressure dependent increase. So this means if this is a phonon based superconducting mechanism, we can even have a further increase in the superconductivity by going even further in the system. And then it is interesting to look at several of these kind of systems where good high quality single crystals are available, to see what is a universal behavior in these kind of systems and how it is related to the rattling atoms, the disorder there, and those kind of things. So this is a field where we are continuing our work, and I would really like to have feedbacks from the experts in this meeting. So let me come to the second system. This is a classical charge density wave system, gold antimonide. So this is, the structure is shown here. You have the close resemblance of this structure with the iron-based pigments, which was something one of the interest for us to study this system. So we have studied the system again systematically under pressure. Of course, our pressure range of interest is within 10 GPa, where we can characterize the system very well and complement with other measurements. So then we looked at the transport properties of the systems. We can see there is a clear charge density wave transition, which is around 80 Kelvin at 0 GPa. And this, with increasing pressure, this charge density wave transition decreases to lower and lower temperature, and it gets completely suppressed, or at least we couldn't detect any evidence of such transition above 2.5 GPa. So if you extrapolate, it seems to follow a linear dependence. If you extrapolate, the transition is completely suppressed at 3.2 GPa. Now we look at the structural data. So here again, if you look at the unit cell volume as a function of pressure, there is a regular change. There seems to be no role of the structure in whatever suppressing the charge density wave transition. But if you look more carefully at the pressure dependence of the in-plane and out-of-plane lattice parameters, we can clearly identify 2 pressure regimes. One is the high pressure regime, where the CDW transition is fully suppressed. And there is another low pressure regime where the CDW transition is existing. And they are separated as 2 regimes with linear pressure dependence for the in-plane and out-of-plane lattice parameters. So this was interesting. Then there were several of similar systems where there is a lot of literature also available. And then we realize one of the main issue here is the stoichiometry of the sample. So there are various reports on where the which is the critical pressure where the charge density transition can be fully suppressed. And all these details seems to depends very clearly on the stoichiometry of the sample. And it was quite surprising. Even a system like LAUSB2, where the control over the stoichiometry is not so precise for several groups, where there can be AU1 minus X SB2, and the gold vacancy can play an important role on those kind of things. So let me come to the third system, which is again quite interesting from the electronic transitions in it, because this is predicted to be having several topological transitions under pressure. So we know what is a topological insulator. The topological insulator is a insulator in its bulk, but it supports spin-dependent conducting states in the boundaries. And these systems, since pressure can really act on the spin orbit coupling, as a function of pressure, you can modify the system, which can lead to several topological states. And such things are studied from first principle point of view. In this particular system, there was an earlier study which predicted several such transitions. So this was one of the interests where we started this system. So this is a study we did with a group from Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore. So the main people involved is Rajaji Vincent and Chandrabas Narayana. They are from this institute. So this was part of the thesis work of Rajaji. So as I told you, there is with increasing pressure, you can induce a structural phase transition, which was not the real interest in this study. So our interest was to look at the pressure dependence where there is no real symmetry changing structural phase transitions. So we looked at the system, and then we carefully looked at the in-plane, out-of-plane to in-plane lattice parameter variation as a function of pressure. We can see there are at least two places where this dependence shows a change. If we look at the volume, which is the classical way of looking at the pressure dependence data, it is again a smooth curve, which can be clearly well described by a classical equation of state. But if you look at the phonon modes, particularly the lifetime of the phonon modes, the full width at the half maximum of the phonon modes, you can see anomalies which are closely matching with the changes which we have seen in the C/A ratios. So combining these results together with the earlier predicted topological transitions, we can kind of take these anomalies as evidence for the occurrence of such topological transitions. But the system was more interesting because we also looked into this system from the superconducting point of view. This superconductivity study was done with another group, which is from Bhapa Atomic Research Center in Mumbai. So where they have a very good transport measurement system under pressure, where they can follow even at very high, up to very high pressure, the samples under pressure. So the system is semi-metallic, but with pressure you can decrease the resistivity, and eventually above 5 GPa you can induce a superconducting transition. And the superconducting transition is robust. You can see the magnetic field dependence of the superconducting transition temperature, and we can extract more information. But the more surprising result in this particular case was the system is found to retrain the superconducting state even in the pressure release. When you release the pressure and you reach a very low pressure of 0.5 GPa, there is a weak charge density wave which is reappearing, but it again retains the superconducting state. So this was very interesting and very peculiar. So we were excited about it to really see whether we can gain a sample which is becoming superconductor only under pressure, but then it retains superconductivity. So this was quite interesting result where we are also trying to do further measurements, and it seems this kind of a phenomena can occur also in few of the other similar systems. So I am almost at the end. So since I also show you the beamline, so let me tell you that we would like to welcome you also to the beamline. If you are interested, there is the next deadline after the summer, 15th September. And eventually, if there are troubles in travel, so we may also be able to carry out some of the measurements in so-called sample mail-in mode. So thank you for your kind attention, and I'm open to questions.
We are open for questions. Anybody in the audience, online? Well, if not, let's thank the speaker again.
Thank you.
Thank you, Bob. Well, the next speaker is Gregor Jotzu. He's going to talk about light-induced superconductivity in organic materials.
Okay, I guess I won't have to. All right, well, thank you very much for the invitation. It's a particular pleasure actually to present my results specifically at the Superstripes conference, because in science, you're always standing on the shoulder of giants. I think, I hope you will see that in this particular work is actually based on a lot of the work of members of the Superstripes conference. So I'm glad that there's a chance to present it over here. So I will tell you about light-induced superconductivity, and making a material superconducting with light is part of a kind of more general effort of having materials with tunable properties. And we have seen many nice examples of that in the conference so far, for example, using structuring, using pressure, using strong electric or magnetic fields. The approach that I'm most interested in is using light to control the properties of materials. And because it's just after lunch and you still have to digest, let me give you a little illustration. Imagine that someone gives you a musical instrument, you don't know what it is, you want to find out more about it. Well, you could just turn on the light, have a look at it, you already learn a lot about it, it's very much in the linear response limit. You could go to the other extreme, take a hammer and smash it. And that's actually also very useful because you get the full spectrum at once. But my aim is to be somewhere in between, so to drive materials strongly enough that their properties somewhat change, but to also be very controlled about how exactly I drive them. So that brings me to my talk, which is talking about light-induced superconductivity in organic materials. And in particular, I will tell you about the discovery of metastable superconductivity in these systems, tell you a bit more about the riddles concerning the microscopic mechanism, and finally give you some outlook on the current efforts on doing ultrafast magnetometry on these systems. But before I go to the actual dynamics, let me tell you just something about superconductivity in organic materials, in particular in fullerenes. Now, luckily, we've had a wonderful talk by Cosmas Presidis yesterday already, so you should know all about it. So just a quick recap. So we have a lattice structure. In this case, it's FCC, where in each unit cell we have a buckyball and then 3 alkali atoms. I always still find it surprising this structure can even exist, but it seems to be the case. And this material can become superconducting at low temperatures. And the current understanding is that the pairing blue is given by local distortions, a dynamically Lian-Teller distortion of the buckyball. And you get this very interesting phase diagram that we've seen yesterday, where as a function of the lattice constant, if it's too large, you get the Mott insulator, but in between, you have a strong dependence of the superconducting critical temperature on this lattice constant, and you can explore this interesting metal to Mott insulator crossover at higher temperatures. Now, I will just tell you about experiments on K3C60 at this moment, which sits over here in the phase diagram and has a critical temperature of 20 Kelvin. Now, there are many ways to look at superconductivity in the system, and people have used many of the available methods. What I'm going to show you is data using the optical reflectivity of the material. And you can see very clearly that if I go from just above TC to well below TC, the reflectivity in the low energy sector goes up. It goes up to 1 and gives a very clear signature. And that also directly tells me that if I want to probe this material optically, I have to focus on this terahertz range. Now, if you can have a full spectrum here, you can do a Kramers-Kronig transformation and actually get the complex optical properties, which can express as a conductivity. Now, if you look at the real part of this conductivity, so that's the dissipative or ohmic part, then you see that below TC, at low energies, this is 0 because I don't have any dissipation when I'm cold enough. And then the value shoots up at a specific value, which actually corresponds to the optical gap. So sigma 1 is a nice way to see the gap in the system. Sigma 2, you see that you have a divergence, and this really just tells me that my electrons are now obeying Newton's equation and not scattering. This prefactor, though, is also proportional to the superfluid density. So I can get kind of 2 key parameters of this material out of this type of measurements, at least when it's a nice S-wave superconductor, as it is in this particular case. So what happens when we drive this material with light? How exactly do we drive it? We start with the material at 100 Kelvin, so that's 5 times TC, well above TC. And then we hit it with a laser at around 7 micrometers wavelength. This laser can have variable durations, and we then probe the system with a terahertz pulse. It's important that we now use a pulse because we want to have time resolution, of course. Now, let's first of all just look at the reflectivity itself. What you see here is it's somewhat arbitrary. It's the peak of the terahertz pulse. It's basically a weighted average of the low frequency reflectivity. But we see something interesting. So as we vary the duration of the pump pulse, we see that the reflectivity goes up and then goes down again on the time scale roughly corresponding to the pump pulse itself. But after that, it doesn't actually go down to 0, but rather stays flat for quite a while. In fact, it's sort of on a time scale of several nanoseconds that we get some sort of metastable change in reflectivity. Now, this observation in itself doesn't tell us so much yet. We have to be frequency resolved and quantitative, but we can do that. And if we do that, we see that the frequency, that at low frequencies, the reflectivity of the sample actually seems to go to 1 as we pump it. And that's 10 picoseconds after the pump pulse is gone. Now, we are measuring terahertz reflectivity, and the way we do it is to do electro-optic sampling. So we're directly probing the electric field of the reflected light. And if you're not familiar with this technique, essentially think of this material as having a strong Pockels effect. And this Pockels effect changes the refractive index of the material in one direction, and that gives rise to polarization, rotation, or ellipticity that we then probe, and we then scan the delay between 2, and that way get the full electric field of the pulse. Now, if we do that, we actually have access to the full optical, to the full complex reflectivity of the material. And that again lets us get the optical conductivity of the material. which we see that in sigma 1, there seems to be a gap opening. And in sigma 2, we see this kind of divergence. And interestingly, actually, if you look at the values, they're very close to what you get by cooling, which, you know, it's in itself not necessarily expected. I mean, you might have a very different superfluid density. But from the optical properties, this material looks like a superconductor, definitely. If I wait even longer, let's say 100 picoseconds later, it does stay the same. And as mentioned, this is sort of a nanosecond range phenomenon. So still pretty fascinated that this somehow happens. Now, because we are in this nanosecond time scale, we can also do a somewhat more conventional transport measurement. Now, we can't really do a nice, you know, quasi-DC 4-point measurement here yet, but what we've done is to put contacts on the sample. Then we use a 4-point measurement to determine the contact resistance. And then using nanosecond pulses, we can probe the resistance and just subtract the contact resistance of the sample. That's still a bit of an approximation, but at least if we look at the results here, we do see a resistance which seems to go down to 0 with big error bars, one has to say, but it seems compatible. And what's important about this is that this is now on a gigahertz frequency scale, because so far the data I've shown you was cutting off at about half a terahertz. That's as far as we can go without terahertz probing setup. But even in the gigahertz, we seem to see a resistance that goes down and possibly to 0. So that's all very nice and interesting, but I haven't told you anything yet about what the mechanism is. And the reason why I haven't told you that is that we actually don't know. So there are a number of ideas you can think of. You could think, for example, that there's some sort of dynamic localization from the laser field, which acts as a type of negative pressure. It could be that you're actually directly driving local molecular vibrations in the system. That was the original idea for doing this experiment. It doesn't look like we have a sharp phonon resonance, but it could be broadened for other reasons. It could be a more complex mechanism where you're actually directly coupling to the Hubbard U in a way that then changes the exchange energy. There are a whole number of theories. I don't have time now to go into all the details. And also as an experimentalist, I feel that my sort of job is to do more experiments and find out as much data as possible that can be used to eventually distinguish between different possible theories. And one very exciting thing to do in this context is to actually look at this phase diagram that I've shown you so far. Now, at the moment, we just have K3C60 here, but what we can do is to apply pressure to go, at least go left in this phase diagram. So how do we do that? As we've seen a few times now, you can apply pressure by using two diamonds and pushing them together. And then you can measure what the pressure inside is by looking at the fluorescence of ruby, or for example, samarium-doped strontium tetraborate, which we've also used. There is a bit of an issue if you want to do terahertz reflectivity, in the sense that your wavelength is big, so you can't have a very small spot, right? So that means that you need to have a diamond anvil cell with a pretty big diameter at the sample side, which restricts somewhat the pressures you can apply, so we can only go to 3 GPa. Fortunately, these fullerized are pretty soft, so by applying just 3 GPa, you can halve the critical temperature. So we're in a bit of a sweet spot where we can still do our terahertz measurements, but apply enough pressure that something interesting is supposed to happen. So we do that. I'm not going to show you a million spectra now, but rather what we did was to at each pressure fit a Drude model to our system and see what happens to the extrapolated DC conductivity. Now, in equilibrium, when we don't pump, we see what you would expect for a metal, as in you apply pressure to increase the tunneling in the system, and that makes it somewhat more metallic, makes it a somewhat better conductor. On the other hand, the light-induced state is strongly suppressed by pressure, and we see this very clearly. Now, what does that mean? You can interpret that in two different ways. One thing is to say that, okay, my light-induced state somehow has the same slope of pressure dependence as the static state. So as you apply pressure, you're reducing the density of states at the Fermi energy, and that's what suppresses superconductivity. Or you could say that you need to somehow be somewhat close to the Mott insulator to even get this effect to begin with. You can't really distinguish these two in a sense, because you always apply the pressure first and then pump the material. Now, recently we've actually, gotten more evidence that maybe the proximity to the Mott insulator is crucial, because we've looked at the second family of organic superconductors, the so-called kappa ET X sols. It's a very long chemical formula, but essentially this is a organic superconductor, TC of somewhere between 10, 15 Kelvin and so on, which also has this interesting metal Mott insulator phase diagram. And we have, and you can find the results in this paper, probed 3 different compositions of this material. And we indeed only found light-induced superconductivity in this material, which lies in the metal Mott insulator crossover, not on the very metallic side, not on the Mott insulating side. So now there was a hypothesis by Tomo Uemura, who was also presented on Monday, I think, that maybe this whole phenomenon has something to do with the presence of pre-existing Cooper pairs. In particular, you probably all know Uemura's plot, where it's found that in many superconductors, the critical temperature, many, let's say, high TC or unconventional superconductors, the critical temperature actually scales with the Fermi energy in the system. So in a sense, scales with the superfluid density, which would indicate that the material becomes normal, non-superconducting when you heat up, not because Cooper pairs break up, but rather because you destroy long-range phase coherence in the sample. And Amir and Kivelson have developed a theory for that, which essentially says that, okay, even if Cooper pairs were to remain stable, if it gets too hot, higher than the coherence temperature, which depends on the superfluid density, you lose superconductivity. Now, for conventional superconductors such as lead, for example, this coherence temperature can be 1,000 times higher than TC, so it not expected to have any impact on this thing becoming non-superconductors. But in many cuprates and also actually in fullerides and kappa salts, these temperatures can actually be fairly close. So to some degree, it's still debated if and where this kind of phase coherent superconducting regime can appear, but at least from the numbers, it's realistic that this could play a role. So is light-induced superconductivity maybe some sort of synchronization of pre-existing local superconducting regions? To understand that a bit better, you need to look at the materials which are have light-induced superconductivity, and the cuprates do belong to that class. And there have been indications that there can be maybe fluctuating superconductivity above TC by measurements of the Nernst effect. And I will tell you in a second what this Nernst effect is. In the kappa salts, there had also been such measurements which indicated that superconductivity might show a fluctuating regime above TC. However, in the fullerides, this was not the case. For some reason, these measurements had not been done yet. So we teamed up with Munsun Nam and Arjang Ardavan from Oxford to measure this effect in K3C16. Now, if you don't know the Nernst effect, here's a 10-second introduction. So you take a material, you apply a strong magnetic field, and then you apply a temperature gradient in one direction, and you measure the voltage in the third direction. For quasi-particles, you can roughly think of that as a combination of the Seebeck effect and the Hall effect. So you thermally drive particles in a direction, and then they get deflected by the magnetic field. And indeed, we also see in K3C60 that at high temperatures, you have the kind of Seebeck effect, the kind of quasi-particle-like Nernst effect that you expect. One advantage about this Nernst effect, though, is that it's actually pretty small, especially compared to what you can get below TC in a superconductor. Why does a superconductor give you a Nernst effect? So if you have a type 2 superconductor with vortices inside, these vortices can carry entropy, so they would follow the thermal gradient. As they follow the thermal gradient, they're going to bring magnetic flux into this loop, which means that you're building up a voltage in here. So let's have a look at the strength of this Nernst signal as a function of temperature and magnetic field. And here the dotted line is the HC2, basically. So that's where, from resistive measurements, we see superconductivity break down as a function of magnetic field and temperature. And you see that there's a very strong Nernst effect, just below TC, which eventually disappears again. The reason why it disappears for very low temperatures is that this vortex lattice kind of freezes, so it doesn't give you a Nernst signal anymore. But what we're most interested in is that indeed this Nernst signal below TC doesn't directly disappear at the phase transition, but it seems to continue somewhat. So let's look at that into a bit more detail. So if we measure the Nernst effect here very carefully, it's quite a small thing. You see at high temperatures, we have a quasi-particle signal where the red line is what you would expect based on independent measurements of the Seebeck and Hall effects. And this is the measured signal in which you can see that already around 80 Kelvin starts to deviate from the quasi-particle signal and starts to also develop a field dependence, which is seen as a kind of smoking gun for this being related to superconductivity rather than to some more complicated quasi-particle effect. So we see an onset of the Nernst effect at around 80 Kelvin. And one thing to point out, independently of this whole story with light-induced superconductivity, is that as far as I'm aware, this sort of superconducting like Nernst effect well above TC has so far only been seen in very thin films, thinner than the coherence length, or in sort of layered materials such as the cuprates. So maybe this is interesting in its own right. Now, we've done a whole analysis on this signal to understand whether it could be explained by Gaussian fluctuations and so on. So Nernst experts, I'm happy to give more details on that. But for the moment, let me just stay with this somewhat hand-waving empirical picture that we have interestingly seen that both in the kappa-salt organic materials and in K3C60, the existence of light-induced superconductivity and the detection of superconducting fluctuations of whatever type they may be above TC seems to somehow correlate. Now, it would be very exciting, of course, to explore this side of the phase diagram here to see what happens with both of the effects, the Nernst effect and the light-induced effect. So going back to this diagram proposed by Uemura, we've now added 2 points. One of them is the light-induced effect in the kappa salts, and the other one is the Nernst effect in the alkali doped fullerenes. So this may hint at not a full microscopic picture of what is happening, but maybe it's some important ingredient for the phenomenon of light-induced superconductivity. Definitely, we now know we have a quantity telling us about the presence of pre-existing short or long-lived Cooper pairs above TC, and hopefully people who know more about theory than me will now try to figure out exactly what this tells us. Again, in 3D, there's a bit of a limit of theoretical predictions for the Nernst effect, so it would be interesting to find out more. All right, so let me briefly summarize what we know about light-induced superconductivity at this stage. So we've seen that it can last for nanoseconds in K3C60. It's suppressed by pressure and seems to have an interesting relationship with the Nernst effect. What I didn't show you, remember at the very beginning, we saw that there was some kind of overshoot of reflectivity for short times, which depended on the duration of the pulse. Now, we teamed up with Dan Podolsky, Eugene Damler, and other co-workers to figure out the theory of that. And a possible explanation is that actually you get a bit of amplification at short times, and that may be due to an oscillation of the Higgs mode in the material, which gives you a parametric amplification in the system. And in a sense, maybe what you expect, because if you suddenly make something superconductor and you think in this kind of Mexican hat picture, you might expect oscillations of the order parameter. So that's an interesting phenomenon as well. And it kind of also gives you a bit of a speed limit on how fast you can get into the superconducting phase, which seems to be around 2 picoseconds. Now, one thing is missing. We've seen that already in the discussion about the hydrides, and that's that if you look at superconductivity, there are 2 things you want to look at. One of them is a drop of resistance, and the other one is actually a Meissner effect. I couldn't find a historical picture of that. The original paper just has text, but here's a measurement from our squid of indium, and you see very beautifully that below a certain temperature, you expel magnetic flux. Now, can we measure that in our system? Obviously, this is all happening very fast, so we can't just stick it in a squid, even if we could put the laser in there. So we've developed a different method, and that's a way to do ultra-fast magnetometry. So what's the basic idea here? If we take a magnetic field applied to a sample, and I've drawn the sample pretty badly on purpose to show that the sample can be kind of anything, right? And then on top of that, we put the material with a strong Faraday effect. And then we shoot a laser through this material, make it reflect from the bottom side, and measure its polarization rotation. That is actually a way to detect the magnetic field up here. And by the continuity of Maxwell's equations, we know that that should be the magnetic field inside the sample, right? But importantly, though, our laser pulse never actually touches the sample itself. It just measures the field right above. So this is different than MOC. And this doesn't require the material itself to have a magneto-optical Kerr effect, etc. We don't heat the material. So there are some nice things about that. And for a superconductor, that is the way that we can do it. We couldn't do it with usual MOC in the near infrared. So, some specs of this method, it's an absolute B field measurement. It doesn't depend on the Verde constant of the material we investigate. It works at low and high temperatures and also at weak and strong fields, so that's very good for us. Spatial resolution could be better, but we can get down to 1 micrometers. We've managed to push it to less than 30 nanotesla, which we're very happy about. But most importantly, and that's kind of the unique point about this way of measuring, is that we can get less than a picosecond time resolution, but also measured down at DC. So we have really kind of a full spectrum. So just to show you one quick illustration of a static measurement of a YBCO film, as we scan the laser across the film, our detector material is up here, and we see that at high temperatures, the field is just flat. And when this thing becomes superconducting, there's zero field on top of the sample, as you expect, but overshoots on the side, and as you move away again, returns to the external field. With this, we're very happy to look at field expulsion from the material. Now, we've learned that field expulsion and field exclusion are different phenomena, and we want to be able to explore both. We want to do field cooling and zero field cooling. So let me just, for the very end of my talk, show you how we want to do that. So imagine the following. You make a ring out of a high temperature superconductor, some sort of thin film that you can buy. And then inside you put the sample, right? Now apply an external magnetic field. You would expect that by Lenz's law, there will be a current circulating that will keep the flux inside this hole zero. And depending on the geometry, that also means that the field is pretty close to zero as well. Now, because it's a supercurrent, this will just keep flowing. But now I come with a high energy laser and destroy the superconductivity in this ring. And that actually lets the magnetic field flush in very quickly. In fact, we can get down to about 10 picoseconds timescale with this. So that's a very beautiful method to actually apply a changing magnetic field to a short-lived transient state. But you can also do a lot of other fun things. So for example, if you take such a ring and just hit one small part of it, you actually get these funky oscillations, which I think you can understand as a sort of light-induced split ring resonator. But we're looking forward to, beyond applying this to measure the Meissner effect and also field exclusion from light-induced superconductors, to also possibly apply this technique to many other materials, such as, of course, quantum magnets. But we might even dream and think of measuring edge states in light-induced topological systems. So with this, let me thank all the collaborators involved in this work, especially the team in Hamburg. 2 young PhD students who are very talented and working on setting up these magnetometry experiments, our collaborators in Oxford, the people who have provided samples for us, and also, of course, our theory collaborators. And finally, let me thank all of you for your attention.
We have time for questions.
No, we don't have direct control over that. Yeah, I mean, that would be interesting to look at, to indeed see whether we are maybe directly coupling to certain vibrations. Yeah, but right now we don't have that control. Yeah, so that's a very good question. I didn't show the data here. So in principle, where we drive is close to resonance with the T1U vibrations on the buckyball, which could be nonlinearly coupled to the Hg modes that are thought to be responsible for superconductivity. However, we then saw that if you go actually quite far away from that resonance, further than, let's say, the bandwidth of the laser and so on, you still seem to see the effect. Now, we have very recent measurements that suggest that if you actually go much lower in energy, so something like 4 times lower energy driving, there seems to be actually some sort of fairly broad resonance. That resonance seems to roughly correspond to the energy of the inverted Hund's coupling, but there are also other phonon modes there. That's really one of the reasons why we can't really say what the microscopic mechanism is at this point. There's certainly not a sharp phonon resonance, but we can also not exclude that phonons are somehow involved. That's what I can say. Yes, yeah. there we see it actually even stronger, yes. But we also did, we did some measurements with the CO2 laser, which was very narrow, but pretty narrow band, which was a 10 micron, so somewhat lower in energy, but certainly we were not resonant anymore. And there we also saw the effect. And now we went to 11 terahertz, and there we see the effect more strongly. Then it goes down again for even lower frequencies. Yeah, yes, that's very different. So in this kappa salt material, there's a clear phonon resonance. And you can also see that if you drive, let's say, at another phonon, there's one specific phonon, there are two phonons, which if you drive them, you get the effect, but there are others where you don't. So that is quite different. Also different from, for example, in YBCO, where also there are phonon resonance seen. Yeah, there's well, I mean, YBC also is also a bit more complicated because then there's also an effect at 800 nanometers. But at least when you're in the low frequency regime, you have to pump at 15 micron, and as soon as you move off resonance from that, you see that the effect disappears. Yeah, definitely you don't. So this is a bit unique for the fullerenes. Thank you very much.
Well, let's move to the next speaker, Campi, talking about the scale-free oxygen ordering in cuprate superconductors.
Okay, good afternoon. In this talk, I would like to give you an approach, an experimental and a methodological approach to investigate the complexity in matter and in quantum matter. So, this is the layout of my presentation. First, I will give a short introduction, explain and defining the complex materials. As a second point, I'll speak about methods and methodology, consisting of space-resolved synchrotron techniques, jointly to statistical, physical, and spatial statistical analysis of big data set. Finally, shortly, I'll give you also some results of this methodology and some possible and new application of this study. Well, let's start with complex materials. Complex materials are all materials where the electronic and atomic structure change point to point at a multi-scale level. I report here some explicative example ranging from cement and steel, where the inhomogeneity at a micron scale determine the mechanical and thermal property of the materials, and going down to myelin and bone tissue in biological system, but in biology, where inhomogeneity and multi-composition at different scales give rise to the biological functionality in these materials. Finally, at a smaller scale, at atomic scale, we find perovskite with a complex atomic arrangement that allow them to explore the several conformation with several energetic conformation. And in this system, we can find different ordering at a short scale length, such as defect orbitals, spin, and charge density wave order in the lattice. Well, we have studied a little bit all this system, several of this system, but of course in this conference we'll focus on the quantum matter, and in particular in the cuprate, where the oxygen mobile dopants give rise to a variety of phase in the samples with the phase separation at a different scale. The main technique that we use is the X-ray diffraction. And when we study this system by X-ray diffraction, what we note that the perfect order, the perfect order of crystallography is usually not kept, not considered, not occurring in nature, because usually we observe modulation due to the manipulation of atoms in the lattice, and so on short-range order due to little domain ordered in a different way with the average, and then correlated disorder when atom move or displace in preferential direction. When we have when we study this particular material with diffraction, in the diffraction pattern, we don't see more any Bragg peak spot as in the first picture on the bottom on the left, but we can observe different intriguing feature given by superlattice peaks or weak broad peaks and streaks. Well, these particular features are due, I have mentioned, to the organization of charge orbital defects and spin at small scale in the lattice. And this gives rise to two main characteristics in the sample. The first one is an energy landscape by which we have different states, energetic states near between them, so that it is very easy to pass from one state to the other with the small stimula. And in fact, these energy differences are of the order of millielectron volt. That's less than the covalent energy, but similar to phononic energy. And the second feature occurring in this complex system is the formation of pattern, spatial pattern, Well, okay, here we are. Now we'll see the methods to study, to approach the complexity, this type of complexity in material. And our methodology is based on scanning the synchrotron radiation technique with a spatial resolution ranging from micron down to 100 nanometer, so at different scales. And these data, the collected data by this technique, are analyzed by spatial and physical statistics to these data sets that are very, very big, as we'll see. The first step, so, is the diffraction, the standard diffraction of our sample. This is a diffractometer on the Electra beamline at Trieste, and in this step of experimental method, we have to know the crystal, so we have to orient it in such a way that we can measure its reflection. But usually, when we can measure the Bragg reflections, that are the stronger reflection indicating the average structure of the sample, we find usually many features beyond the Bragg peak, and this feature consists of streaks or weak superlattice, and so on. These are three families of superconducting, and as can we see, in every family we observe always the presence, the occurrence of the diffuse scattering, that is weak scattering between the strong peak scattering, peak Bragg. The other important technological feature that allow us to study this system is the focusing optics in the modern, in the new synchrotron sources, because they allow us to make beams of 50 nanometers. So by using this scanning technique, we can discriminate very difference on the structure of atomic and electron structure in this material. This is a typical setup of reflection X-ray diffraction scanning, and I would like to underline this calculation here, because they show how making a mesh with 1 millimeter by 1 millimeter, keeping a step of scanning of 100 nanometer, we collected million and million of frames. So for study 1 millimeter square of matter, we need to analyze millions and millions of frames, and this poses a real problem of data storage, first of all, and then also data analysis. So we have to deal with this new methodology to carry out analysis in this system. At the first step we used is the pattern recognition, using algorithm based on machine learning or neural network systems. In this way, we can discriminate over millions and millions of frames, different shape of Bragg peak, for example, and then on the base of the different shape, we can construct different maps and study the first step of the phase separation. The second step of the analysis is to do statistical and spatial analysis that involves correlations, involves clustering, involves connectivity, aggregation, dispersion, tessellation, all the theory of the spatial statistics, because in this way we can characterize the texture and the way in which these phases are correlated and interacting. Well, this is the methodology. Just give some results focusing on the oxygen mobile interstitials used to dope the cuprate superconductor. Well, because we know that the quantity of the oxygen oxygen dopants affect the superconducting temperatures. But now it is also known that the arrangement of the oxygen affects also the transport and the superconducting properties. This is the simplest case, I guess, of our study, and is the lanthanum cuprate. And here we can see in the diffraction pattern the strong Bragg peak, surrounded by a lot of satellite due to the order of the oxygen dopants from a side, and from the other side by charge density wave. We have studied these two short orbital phases and realized that this phase can be manipulated by weak stimuli, in particular with a few degrees of temperature and few photons fly and few photons flux on the sample. In the central figure, you can see two hysteresis The first performed with low flux, and the second performed with high flux. Of course, we have different dynamics in this procedure, but the important things and that we can select a multitude of states in our conformation, in our system. And the next step of the study is to understand what happened in two different conformations of the system. And okay, here maybe I can jump this, also this. And we have here two typical states, two different states that I call N and M, obtained by different annealing procedure by flux illumination and temperature annealing. These lead to different organization of oxygen in the sample. These two different organizations can be characterized and studied by typical tool of the statistical physics. Here we see two cases. The first case is the probability density function, and the second is the GDR function, that is the spatial correlations. And what we found was that this arrangement is described by scale-free arrangement. So it seemed that scale-free arrangement with a large extent of the distance of power law promote a better superconductivity. So the texture of oxygens, not only the content, but also the texture of oxygens in this material can affect, can determine the transport properties. Well, the same thing we did in another system, in mercury cuprate. Also, in this case, we could measure both the oxygen content. In this case, we have no superlattice, but we have streaks connecting different Bragg peaks, and this corresponded to wires of oxygen dopants in the lattice. And also in this case, we found a spatial distribution of both oxygen and the charge density waves described by power law and scale-free behavior. So also in this case, we get this sign that the power law and the particular probability distribution can promote, can favor the transport and the superconducting and the coherence at low temperature in this system. The other things that we found is that the oxygen charge density waves occupy different region in space, so they are spatially anti-correlated. And when this spatial anti-correlation occurs, we can say that an interface develops between the two phases. And in the last figure here is indicated by Y pathway, the interface separating the charge density wave and oxygen interstitial, and it can be expected to be also the pathway in which superconducting and supercurrent flow in this material at low temperature under TC. Well, that's just last thing we did is to check if really this oxygen arrangement is scale-free. And to do this, we use two beam sides. The first on micron, 1 micron per 1 micron, and the second a factor 10 smaller. And the map on the right corresponded to the white rectangle in the first map. And in both this map, we measured a probability density function described by a power law that is connected with the scale-free, clear scale-free arrangement of of oxygen. Another thing we note here is that when we go down at nanoscale, we are able to distinguish percolation pathway. Percolation pathway in between the oxygen and the charge density waves that is related to interfaces that I mentioned before. So let me conclude with briefly with two new applications in which we are working now. The first one is the Eurofusion for nuclear fusion, where we have to insert in this case IBCO film nano defects because at this scale these defects pin the magnetic vortex and increase the density of current or the critical current. In this way, we can obtain more current traveling in tapes, for example. And what we realized is that also in this case, is not only the quantity of nano defects you insert in the film that affect the JC, but also the arrangement of this together with other features such as strain and oxygen staging. And this is the analysis we are doing now, where you can see in this case, we use the grazing incidence X-ray. You can see how the diffuse scattering between the 103 Bragg peak changed as a function of the content of the nano defect, that in this case is bit zeta. And the diffuse scattering changed from a streak to two superlattice. A different topology develops in this sample as a function of the quantity of defects. And also in the last figure, we see the oxygen ordering studied very well by Zimmerman, also by our group, that are connected with strain modulation. So the system in this case is quite interesting because can relate the modulation of strain with oxygen ordering and with vortex spinning, useful for technological application. Well, briefly, the last application is nano-electronic device. Here, maybe you recognize Nicola Poccia, and best wishes to him for his fight with COVID. I know he's winning sharply. And in this lab, in this beautiful lab, is make artificial van der Waals heterostructure at atomic layer. And the first we have characterized these atomic layers always by nano X-ray diffraction, showing that the bulk and the 2D layers have a different granularity, inducing different electronic properties of the sample. And this is stuff from Nicola, but I just wanted to show this type of technique that is powerful to study also very, very thin, very, very small sample. Okay, I thank Antonio Bianconi, Nicola Poccia, Alessandro Ricci, and Michela Fratini that are component my long-standing co-worker. Thanks.
Any question?
I made one, sorry, from the internet.
Excuse me?
Can I formulate a question, please? Claudio here.
Yeah, yes, go ahead.
So I missed a little the conclusion on the diffuse scattering from YBCO. Could you please show again the slides you were using.
The last? The last?
Yeah, at the very end. Yes, it was one of the last one. You came in a little broken, and it was difficult for me to understand what you were saying. But you showed very, very interesting thing on diffuse scattering on YBCO.
Okay. Non vedo il mouse. I can see the mouse here. Ah, ecco. Dove sta questa diagramma? This one.
Yes, exactly. Yes.
Yes. What is the question, please?
So the question was, I missed a little bit what you were saying because you came in very broken. Sorry. So I missed if you said that there is any systematic, anything or whatever you were saying. I completely missed it. Sorry.
Ah, okay. So this is. Huh? Yes, these are X-ray grazing incidence pattern, X-ray pattern, where because we are studying films, no, thin films, and in these patterns I'm showing here, we see different pattern with different content of nano defects, B zeta O. Okay, 5%, 7%, 10%. Depending on this content of the facts, you measure a different diffuse scattering between Bragg peak. You can see that here you have a streak, and here you have two superlattice in this case. So depending on the amount of nano defects inserted, added in the material, the strain modulated in different way. Okay, here you can see the profiles, and you see the streaks, for example, red or black, with the green that are the superlattice here. These superlattice are different of, are a way to study, to characterize the organization of nano defects in this material, and are connected to the pinning center for magnetic vortex, increasing the current. Okay?
Is okay?
I see. Yeah, thank you. Thank you very much.
Any other
Thank
question?
you. Okay, thanks.
Any other question? If not, let's thank the speaker again.
Thank you.
Our next speaker is Alessandra Lanzara, from exciton to topological excitons and their fingerprints on the electronic band structure.
All right, good afternoon, everyone. Thank you, Antonio. Thank you, Claudio, for organizing the conference. And thank you, everyone here, for staying until the end of the conference. So I will present today some very recent work in my group, searching for topological exciton in topological insulators. Here, okay. So we all know about the importance of generating electron holes in a variety of material, and this has been a subject of scientific interest, both in terms of basic science, understanding the role of electron holes, eventually pairing, condensation, formation of exciton, as well as in a variety of applications, starting from photovoltaics, where the generation of, I think this moved too much. Every time I move the mouse, it changes the slide. I don't know. So I'm not going to have a pointer, I'm sorry. For the one in the audience, I will use the laser. For the one at home, it just every time you move it, changes the slide. But for the pointer. See, when you start to move this, it changes.
Oh, it's showing here.
Yeah, sure, but
You want to move it.
when you move this one, see, it changes the slide.
When I move it, it doesn't change the slide. It changes the slides. Oh, I don't understand. You want to change the slide?
No, I don't want you to change the slide. I'm saying,
Nope. Touch there.
yeah, but yeah, I'm not touching it. It will change.
Yeah. Well, if you go here, you can go first back.
Yeah, but the problem is not going first back and forth. The problem is having a way of pointing for. Now it's okay, but.
Would you help us please?
But it's okay, we'll manage without a pointer, laser pointer, that's fine.
You can do it.
I think I'll do without, I will just say right, left, and so on. Il problema è che la gente a casa non lo vede questo. Con Zoom questo non lo vedono. It's okay. I'll do in this way.
We can do it.
For whoever is here will save this later. All right, okay, sorry for the interruption. So going back, there are a variety of applications where we worry about the electron hole pairs, and in particular about the way this propagate in the material, and these are the basic for systems like photovoltaics, photocatalysis. So the recombination rate and the time on which these pairs live and moves is very important. And this is becoming even more important if we start to think about the next generation for energy harvesting. And one thing that is becoming clear is, in addition to the charge, somehow we can involve also the spin degrees of freedom. Will open a much larger platform for application, where, especially in the case in which we can start to leverage spin-orbit coupling, we are going to reduce the possible scattering channel and perhaps enhance the lifetime of these electron hole pairs. So a material in which people have been looking a lot are obviously topological insulator, and these are been studied not only in the sense of electron hole pairs from a theoretical point of view, but in general because of the beauty of spin-orbit coupling, the presence of the surface state which are topologically protected, and the fact that you have a chiral Fermi surface where backscattering is not allowed. So you have a system where it's perfectly ideal to realize a spin current and to realize all those things that are not possible when you just think about the charge. So these are just an example of the things that I'm going to be leveraging on the talk for topological insulator, either 3D or 2D. The common thing is that you have a bulk that is insulating, and you have a surface where you developed this protected, topologically protected metallic state. So in a way, you have a system where you have a coexistence of bulk, which is insulating, and surface, which is metallic. Now, if we start to think about the generation of electron hole pairs in this system, you immediately realize that there is much larger variety than what we are used to see in the case of semiconductor. So if we start from the bottom left, one simple way of generating electron hole pairs, and therefore generating exciton in this material, is actually nothing fancy. It's just the standard way you do in a semiconductor. We forget about the surface, we forget about the surface state, and you generate this exciton pair or this electron hole pair in the bulk. And so you end up with this bulk semiconducting excitons. Another way of doing it instead is creating a so-called metallic exciton. Now, these metallic excitons are very interesting and fascinating because they somehow all the properties of this topological state. So you are inducing on the surface, which is metallic, you are creating an electronal pairs. And now these electronal pairs, because it's generated here in this topologically protected state, bears all the information about the spin that are for the topological state. Now, this is an exciting possibility, but one of the problem, if we think about leveraging this type of exciton, is that these are metallic exciton, and as we know, they tend to live for very, very short amount of time, just few femtoseconds. And therefore, this is one of the reasons why usually metallic exciton are not so interesting in terms of application. But there is another very exciting possibility that has been not explored so far, both from a theoretical and experimental point of view, which is what if we generate the so-called spatially indirect exciton. So now these exciton are kind of leveraging the real properties of topological insulator. So you are pretty much forming an electronal pairs between the bulk and the surface. So now this new bound state has in a way the property of the topological surface state. So all the beauty of this metallic exciton, but because it's a spatially indirect exciton, now this exciton tend to have a much longer lifetime, so in a way behave more as a semiconducting type of electronal pairs. So now somehow you have combined the beauty of both worlds. And the big question is, do this type of exciton exist? We know there has been a lot of study about semiconducting type of exciton, not so much in the context of topological insulator in the bulk, but there is plenty of literature for semiconducting exciton. There has been a theoretical paper and the first experimental observation of this metallic exciton. What about this situation? Can it actually exist? And is it possible at all? So what we would like to do is to search for this type of spatially indirect electronal pairs, try to realize what are the conditions under which we can actually generate them and realize them. And the rest of my talk will be toward the realization of this type of exciton. Now, the first thing in order to do this is how do we measure them? Well, there is plenty of literature, and mostly the way we have learned so much about electronal pairs from the plasma state all the way to the exciton state is mainly with photon in, photon out spectroscopy. Optical spectroscopy is pretty much dominated in the study of exciton in semiconductor. There is a lot of study also on photoluminescence, and we know that depending from the type of band structure that you can have a more localized or more delocalized type of exciton. Obviously, in our case, we are doing with a system semiconducting, so we are looking more at 1 year type of exciton. Now, so optical spectroscopy is great to detect the exciton. You can look at the different exciton line and get this information. But these two techniques tend mostly be bulk type of technique. Photoluminescence can get some information about the surface, but it's more complicated. So the question is, how can we detect an exciton that is some sort of hybrid situation between a bulk and the surface type of exciton? And so this is the outline of the talk. And the first thing I'm trying to do, I would like to apply a technique, which is a momentum resolved technique, which is very sensitive to the surface and has been great in actually proving the existence of topological insulator. This is for the emission spectroscopy. So the first question we need to ask is, if there are exciton in the material, in general, what are the fingerprint of exciton in momentum space? Because the way we are used to think about exciton, mainly coming from this type of probe, is always been in the real space. And so usually we don't really get information in the momentum space. We get information about the exciton energy, the binding energy, and that's pretty much what we know about exciton. But exciton are complex many-body quasi-particles that have also some property in momentum space. After all, they are generated out of a particular band structure of the material. So the first question I'll try to answer is, if there is an exciton formation, what are the fingerprints in momentum space? The second thing is, well, there is this many-body particle. Has any renormalization effect in the band structure? What are the consequences of the fact that you generate this exciton? And then if there is a critical density for the formation of excitons. And once I've learned all of this, then we will adventure, try to see if we can actually really realize this topological type of exciton. So in order for the first three parts, in order to explore them, I'm gonna go back to something that we know and has been studied for some time, and these are semiconducting type of exciton. But what we will do here, we will do mainly using photoemission spectroscopy, and we will do it not so much in the equilibrium way where you pump with light and then emit electron, but in the so-called pump and probe way. So what we do is we pump the system, we generate pretty much, we emit electrons, so we generate a hole, and then we come in with the probe and we measure this hole. And these are just the typical photoemission pressure, energy versus momentum. You see here things moving slightly up and down. This is just as a function of time. So as the band structure is changing when you go through this pump and probe type of process. So the material I'm going to start with are transition metal dichalcogenide. In particular, I'm going to look at the monolayer TMD material, and I'm going to choose the molybdenite. This is a band gap that is very much approachable with in-house type of tool. We will use a high harmonic generation system to look at this material, and these are systems that when you look at them in the monolayer case, they have a direct gap. Obviously, you can generate also the so-called dark exciton in this case in the bulk, but this is going to be more complex. So let me just start here to see what we can learn about exciton formation. So this represents an experiment done in equilibrium. So equilibrium with photoemission, you only measure occupied state. So the Fermi level is here at 0. So we only see here it's pretty much half of the band gap, and somewhere up here is the conduction band. So in order to observe state above the Fermi level, we have to go in the so-called pump and probe mode that I told you before. So we first come in, we excite electrons, so we occupy the conduction band, which is usually unoccupied, and then we come with the probe and we visualize it. So equilibrium, you just look at the occupied valence band. In the pump and probe way, you can look also at the conduction. Here you get the minimum of the conduction band. So pretty much when you do all of this, you see, well, when you do a pump and probe experiment, you have the appearance of the conduction band dispersion. You see that there is a small shift down, and you see that, well, let's not actually worry about point gamma now for the part. So what if we start to look actually more close to the bottom of the conduction band? Because the bottom of the conduction band, if we go back here and we think about this excitonic type of excitation, the exciton should have a binding energy that is slightly smaller than the band gap. That's what we have learned from optical spectroscopy. So if we go here and we look slightly along the conduction band, we see that there is kind of a very broad peak, so it's very hard to say anything. So what we do, we redo the experiment, but we do it now with an energy that is resonant with the exciton binding energy. And when you do this, you start to realize that you have this tiny peak here. You can take the difference between the spectra, and you realize that this part here that you see, this localized spectra, is nothing else than a signature of the exciton. A simple way in which you can understand this is that when you are pumping the electron up, so you are leaving a hole, there is a hole in the valence band that pairs with the electron in the conduction band, and so these two pretty much are decreasing by a little bit the energy of the electron in the conduction band, and that generate this signature here, which is the signature of the exciton. Now, from the spatial distribution in momentum, you can get information about the radius of the exciton, which is comparable with what is being observed with the optical type of probe. So what this first study showed are two things. Number one, that actually you can measure exciton, and you see them as a localized spectral intensity in the band structure. Number two, that from the distribution, you can get information about the wave function of the exciton and the spatial extension of this exciton. So this was actually a first study that was done a few years ago from our group in collaboration with the group of Robert Candle, and it sparkled a lot of many more results that are available in the literature looking at exciton in a variety of different transition metal dichalcogenide, or in general in a variety of semiconducting material. What we want to do now is to go a little bit further from this study and say, well, we have realized this exciton state, but in a way, yes, it's really nice that we can observe here, but this information that I just gave you here is something that we already knew for 20 years. We just do optical spectroscopy experiment, we can get this information. Is there something more that we can learn when we start now to think about the exciton in momentum space? And so the first thing that is always interesting, exciton is a many-body cis quasi-particle. So the question is, are there any repercussion or any consequence when the exciton inform to the band structure? And just to give you a sense about this, why we care about it, it's because we generally know that many body interactions are the way we shape, we engineer, and we tailor properties in material. And that, for example, if you think about electron-phonon coupling, we know how is it that we heard also in the previous talk, how is it important for superconductivity. Perhaps you can tune this many body interaction to enhance superconducting state. Same thing for the electron-electron interaction. This is in a case of graphene. Well, we have seen that in some condition you can actually really enhance the electron-electron interaction so much that in the past 5 years we have started to see all this very exotic and quantum phase developing also in a very simple system like graphene. And then you can push also the electron-plasma interaction, and this is also a consequence. And each one of these many body interaction is a very unique signature in the band structure, giving rise to a change of the effective mass, here a change of the high energy Dirac velocity, or even here the opening so-called of a band gap. So there are very specific signatures. So the question is, what happens when you form an exciton? Is an exciton by itself also generating a change? And why do we care? Because excitons are so much, these electronal pairs are so much widely used that if we actually can start to leverage them in a different way than we have done so far, so thinking in terms of exciton as a means to change the band structure, then we really open up a new chapter in the way we can think and leverage the exciton formation for application. So here, let me go back. So I show you before we can excite and we can form the exciton. So let's take a look at the band structure. So what you're looking here, I'm taking, this is the conduction band, the valence band. Now I'm focusing on this part, so I'm not enhancing the exciton signal that is much, much weaker than these two. And so what you can do, well, the minimum and the maximum here are a measure of the band gap. So you can measure the band gap in equilibrium. This is as a function of time, and I don't know why the time, because the time appeared down here. So this is a function of time. So anything a negative time or 0 is before the pump hit the sample. So if you want this one here, represent your equilibrium gap. And then as a function of the time, you are exciting the system, you are creating the exciton pair, and then the exciton will decay, and then you can follow the band gap. And so what we see here that we go, when we measure here in this position, we go, there is an increase of the band gap and then a decrease. Okay, you can say, well, maybe this increase of the band gap, I could measure it with optical spectroscopy. I'll show you that actually this is by itself is a very new result. But for a moment, let's go one step further down. So when you go a step further down, so in the valence band and conduction band, let's measure the distance between these two. And so the question is the gap opening up and changing as a function of time following the formation of exciton in a rigid way, or there is something else going on? So when you start to look now at the distance between these 2 points here, so at this particular momentum, you actually see that there is a completely opposite change with respect to the gap. So what this is telling you that the distance between these 2 points is increasing, but the distance between these 2 points is decreasing. So to summarize this, you can do it here in this spectra here. You can say, well, if the dashed line was my equilibrium state, so the valence and the conduction band, following the exciton formation, what is happening is that this distance is increasing, but this part is decreasing. So all that is happening is a change and increase of the band gap, which is measured here at the maximum and minimum, but there is also an increase of the effective mass. In a very similar way to what we have seen with phonons. When you have for electron-phonon interaction, you create a change and increase of the effective mass. So somehow the exciton are actually changing the effective mass of the conduction and valence band. And this is by itself very interesting, but even only the increase of the gap is very exciting and new, because so far, actually, this is just to summarize by how much the effective mass is changing. So far, actually what we have known for all semiconductor is that when you look at the band gap following a pump and probe excitation type of process, all the study in the literature show you that the band gap is decreasing. And what we found here is the opposite, that the band gap is increasing. So the big question is, are we probing something different, or are we actually in a different regime? And the way we can control our experiment is allowing us to look for something new. And when I say something new, perhaps what we are actually looking here, we are in a regime where we are in a transition, we are getting a signature of the exciton mode transition. And the exciton mode transition is nothing else than a transition going from a state where you have many more electron hole pairs, so you are pretty much, if you want, almost like in an electron plasma situation, to a case where you have a very few electron hole pair that they are strongly bound one with the other. So the next question is there a critical density where the exciton actually form? And what happens when you go to the right and to the left of this critical density? We are going to find out that it's all obviously a matter of density of electron hole pairs. So these are the two regimes. The first regime is where the excitons are weakly bounded. So one way of thinking about it, you are coming in with your laser, you are exciting electrons, leaving hole behind, so you are creating electron hole pairs. And if the intensity is a lot, you are creating a lot of these electron hole pairs. And eventually these electron hole pairs start to be weakly bound, and you are creating like a situation where you have like a plasma. Or in other words, if you want, you start just to populate, you have a lot of electrons and a lot of holes. Okay. The other situation is where the density on which you are creating these pairs is very small. It's by 1 order of magnitude smaller. And so when you create a very few, now you really have this very strongly bound state. So if you want, you're in a more interesting type of regime. And so the transition between the two actually has been studied for a long time theoretically, is what is called the exciton mode transition. And so if you would do the two things, you would expect that you see, if you would go between the two regimes pretty much signify the change in the band gap that I showed you before. If you are in this regime, which has been measured for a long time, is where the band gap would decrease. And now the band gap is decreasing because pretty much these electrons, the way you can think about this, these objects are less bound one to the other, so the binding energy is smaller, so the shift or the binding energy, the electron is smaller, so pretty much you are closer, if you want, in an intuitive way to the conduction band. And in this case here, you have a more localized object that you have created. So let's see if there is another way. I show you the band gap. Is there another way where I can really tell you, yes, I'm going through this exciton mode transition? And the other way we can do it, I'm showing you, this is the the valence band. And here I'm enhancing by a lot the intensity, and here this is as a function of time. So the moment the fan fit and so on. So I want to point your attention here. When you start to look here, you see that there is first some parabola going up, and then perhaps there is something going down. And to make your life easy, I can just take a snapshot of a different time. So this is pretty much at equilibrium. Now, after 500 femtoseconds, you see that there is some excitonic state going up, and then there is this parabola that is facing downward. And in between are the data I showed you before, where you just have with this very localized intensity. So what you are doing pretty much, this is your exciton state, and here in this regime here, you are in the plasma state, and here is in a more bounded state. So together with our collaborator, the group of Steve Louis, he has done some first principle calculation, and indeed they have observed that the transition from a plasma state to an exciton mode state is characterized exactly by the creation of this so-called satellite band. In a way, you can think of this as in the case of a polaronic type of band here, and then you go through the exciton transition, which gives rise to this very localized state. So now we know that in order to be in this situation, we need to have a particular density to observe this many body state that is of interest for us. So now let's go. We have learned that there are so many, and there are many more interesting things that happen when you start to think about exciton in momentum state. But let's go to the most fundamental question that I wanted to ask at the beginning. Can we actually use topology to drive this new excitonic state? Can we leverage everything we have learned with photoemission and use photoemission now to look for this surface type of exciton? And going back to what I told you before, there are these three situations. These three situations, now if we think in terms of them in momentum space, they simply evolve in this situation here. So when you do the pump and probe experiment, here you will have a hole in the conduction valence band and the electron in the conduction band. In this case, the electronal pair will be localized in the surface state. The third most interesting situation for this spatially indirect exciton, the way you can realize them is if you can create a hole in the valence band, electron on the topological surface state in the proximity of the conduction band. So you immediately realize that to have this situation, you need to design your material in such a way that your topological state, topological protected state, end up and hybridize at one particular point with the conduction band. And actually, there are topological insulators that do this. People have studied it and have shown that the hybridization point is still bearing the properties of the surface topological state. So the hybridization point is by itself behaving as a surface state. So if we can realize this situation here, perhaps we can search for exciton there. And so we searched among various materials, and we found that actually the bismuth telluride is a perfect candidate for this situation, because you have the valence band. Now this is your topological surface state, and this is the so-called hybridization point. So if this idea is correct, then we should somewhere close here, we should have some exciton signature when we are in the perfect regime for density to create this state here. So here are the data that I'm going to show you. This is the equilibrium data. And now this is part of the valence band, this piece that you see here. So we are limited in momentum in this window here. This is the topological surface state. When you excite the system, now you can start to see as a function of time, this is you start to populate the surface state. So you see the surface state, and then you populate more. And now you realize that after 40 picoseconds, the surface state has completely decayed back to equilibrium, but you are left with an object that is very localized and actually lasts for many picoseconds. So this here is below the conduction band. This is our signature of an exciton state. So obviously this exciton state is formed exactly here at this hybridization point. And we have done all the checks to prove that this is indeed a surface exciton state. But as I told you before, this is very interesting because it's a spatially indirect exciton, because this exciton is formed by electron that is on the surface, or at least in this hybrid the surface state, and the holes that is in the bulk. And the lifetime is actually, so it's kind of a metallic state, but its lifetime is much, much longer. And then you can look at the evolution of this exciton state to get information on the lifetime. And you can also look at the temperature dependence. So you can figure out what is actually the temperature at which this exciton state is formed. And we find that it is around 100 Kelvin, 110 Kelvin. And that's how long these states survive. And then you can get estimation about the lifetime of this exciton. So these open up a very exciting potential look into the future, because you have created this state. And so the first real question that we want to answer is there any spin character associated with this state? We say that this state is formed, this excitonic state, it's formed at the crossover between a surface and a bulk. So it's a surface bulk type of exciton. But the surface state is spin polarized. It's a topologically protected state. So how much of this gets transferred into the excitonic state? And can we think now about this object as actually a spin polarized type of exciton state? So that's the first question we would like to answer to the future. The second thing is, now we have found a system where it's perhaps much easier to search for exciton condensation, because the fact that this exciton is spatially separated between the bulk and the surface actually allow, as you see here, to live for longer time. We found that it's 40 picoseconds. Usually metallic exciton lasts for very, very short amount of time, just few tenths of femtosecond. So now you have a system perhaps where you can start to search for evidence of exciton condensation. And from some preliminary data, we believe that actually this is what we are starting to see. So there are very specific characteristics, for example, this kind of Mexican F dispersion. There are very particular characteristics in momentum state that develop when this condensate is formed. So this could be an ideal system. And finally, now you can start to think about a much larger array of systems where you can engineer this different excitonic state by paying attention to this condition of hybridization between the surface and the bulk that you want to realize. And in general, as we are working more and more on this, we are realizing that exciton by themselves as a many-body system are very intriguing in the way they induce change in the band structure, and they are much more tunable and versatile than other type of many-body interaction we usually use, such as electron-phonon or electron-electron interaction, which usually require much more going there, changing the material, making the material as you want, and then you realize you have changed those interactions. And here instead, we can do it all by simply turning on and off light. So we have a material where we can leverage now the exciton in a much quicker and tunable way to drive the system in the domain in which we want to be. And so that's all for today, and I thank you for your attention. Yes, so fluence, for the highest density, I think we operated around 10 millijoule, a little bit probably below 10 millijoule. And then the tunability of our system in the lowest density regime, where we started to see this, this localized state, is of the order of probably 50 or 60 microjoule. So there is a large difference in terms of density. And I mean, I show you a few data, but it's really exciting to see how it slowly evolves as you slowly change the density. Yeah. So, well, I think there are two differences. The first one is, as I pointed out before, the doping, you are changing your material. So once you dope, you don't go back. So you change the band, but you are done. Here, you have a system where you can go back and forth. But the other difference is that with doping, the change in the band gap is mostly rigid. You could, sometimes you can, drive this in-gap state, or you have like a rigid change of the band gap. Here, you actually end up by changing the effective mass. And as I was just saying to him, depending by how you change the density, of this electronal pair you create, you can actually change the band gap by several %. So you can go from a system that has, kind of a parabolic system to by changing like 10%. So you go more and more toward a flat band system, which is exciting because you enter in a regime where you got closer to, peaking the density of state. So that's why I think it's very exciting, because there are a lot of manipulation that you can do in real time by simply, changing the density of your laser, pretty much. That's what you're doing. So the gap, you should be able, I believe so. I talked with several people who have done this study for the monolayer, and they have the type of system they use. Usually they have more difficulty in have a tunable way of doing, but in principle, yes, if you have the right laser, you should be able to do it and to see it.
I have a question. Can you see this in real time, the space filling during excitation?
Can I see what?
Space filling of K-space filling of the exciton.
Yes.
You
yes.
Yeah.
That's what I was trying to show in the movie. It was kind of fuzzy because the resolution is not the best. Already took a lot of time, but you can start to see it.
Yeah.
Yes.
If I remember well, in the 90s in quantum wells, semiconductor quantum wells, there was a red shift and a blue shift. They partially cancel each other.
Yes.
I mean, you still have this question?
We are not there yet.
Okay.
Not there yet.
Very nice.
But I believe, all these things that optics see, we should see them, and we should see them more, because now we can,
It is unbelievable how beautiful it is.
Yes.
Any other questions? Let's thank the speaker again. Now we have one more talk which was supposed to be after the coffee break. We have to see that the speaker is online.
I'm here. Hello.
Damien Pell.
Yep.
Oh, okay, Damien. You can share your screen then.
Okay. All right, there we go.
Okay, we are seeing it. Go ahead, Damien.
Okay, so I want to thank the organizers for inviting me here, and thank you all for being here at this late hour. I'm really honored to give the last talk of the conference, although I guess this wasn't really original. And I guess I have a little bit more time, given that coffee break is at 5, but I will probably not use all of it. Okay, so I will talk today about plastic deformation of a quantum material, which as such requires some explanations, but let me get to the acknowledgements first. So this is quite extensive work that is still going on. And it's mostly been done at the Center for Quantum Materials at the University of Minnesota, led by Fernandez, Layton, and Greven, when I was still a postdoc there, but also with a lot of collaborators at other places, including Argonne National Lab, Oak Ridge for scattering, and some of the Raman experiments were done in Beijing by Yuan Li's group. So for a start, I want to clarify what I mean by plastic deformation and maybe contrast it a little bit with the elastic deformation that has become quite well known and used a lot for manipulation of quantum materials. Now, plastic deformation, as is fairly obvious, amounts to irreversible deformation. So you take something, you deform it, and it stays deformed. And we mostly do this in compression. So, you take a cube-shaped piece of a crystal, you deform it somehow, and it stays deformed. But usually, this sort of thing is not really associated with single crystals, especially of ceramics, because we figure, ceramics are brittle and break easily. But this has been used a lot for thousands of years to manipulate the properties of metals. So, forging is just one example of extensive plastic deformation. And in engineering, this is still very important. The main effect of plastic deformation is the manipulation of extended defects, or in most cases, these are dislocations. So you have some sort of line defects in the material, and then when you deform it, you either create them or move them around. And this is, because of that, this is qualitatively different from elastic deformation, which is reversible and doesn't necessarily introduce any new defects. And as such, this can lead to new physics. And this is something that I will talk about. And this is basically, it opens a lot of new perspectives. But let me back up a little bit to get back to our motivation in actually doing this and how we got around to actually plastically deform a quantum material, which is not something that people usually do. So the whole story started with the question of superconducting fluctuations. In particular, in high TC cuprates, this is a well-known question, how far the fluctuations extend above TC. And there's a huge body of work on that, but most of it has some sort of normal state background issue, let's call it that. So when you don't really know if you're measuring the normal state or the superconducting fluctuations. And then some years ago, we developed an experimental probe that doesn't really have this issue, that is really only sensitive to the superconducting fluctuation part of the response, which is nonlinear susceptibility. So if you look at the ordinary magnetic susceptibility, you have a linear part, you have a second order part, which I will not discuss now, and then the smallest nonlinear part is this cubic. And it turns out that this is extremely sensitive to superconducting fluctuations, but it's also very selective. And so we got, it's a very simple technique, and then we basically took all the unconventional superconductors we could get our hands on and tried measuring this. And then what we found was somewhat surprising. So it turns out that many of these, especially oxides, so this is strontium titanate, strontium ruthenate, and cuprate, they all share this similar exponential fluctuation tail above TC. So these little arrows are TC, and this is a log linear scale. So basically a straight line means an exponential decay. And we found this in these 3 systems and then in others subsequently. So this seems to be some sort of universal phenomenon, at least in these materials. And then also very recently, we found a similar effect in structural fluctuations. So these are fluctuations of in a tetragonal crystal. These are local orthorhombic fluctuations that also show this exponential tail. So this was obtained by a completely different technique, diffuse X-ray scattering, but also in a cuprate. And then, this is just to showcase that this exponential regime is shared by the structural and the superconducting fluctuation. So this seems to be some sort of general effect. Yeah, we found it in several materials and also in a wide range of observables, and also this is published by now. And we've come to believe that the most likely explanation for this, because an exponential regime is quite unusual, and you would expect some sort of power law, but this is not what is seen. That this is basically rare region physics, that you have some sort of rare ordered puddles above the transition temperature, which are exponentially rare, and to leading order that gives this exponential dependence. So this also implies that there is some sort of ingrained inhomogeneity in the system, which also for many of these has been known for some time. And then the interesting thing is that we try to take a crystal of cuprate, and basically by coincidence, we managed to plastically deform it a little bit. So this is a typical stress strain diagram. You apply the stress and you measure how much the size of the sample changes. And you see that it is slightly irreversible. So it's deformed a little bit compared to where it started from. Now, this deformation is really very small. It's so the scale is in percent. So it's way below 0.1%. But even this very small deformation changes dramatically this fluctuation regime. So if you look at the undeformed sample and compare it to the deformed sample, there's a significant enhancement of this tail. So now this was quite a surprise, because when you deform things, you usually make them more disordered in a way. And then this enhanced disorder, which is very special disorder because it's not just point defects, as I said in the beginning, this basically enhances TC locally. So you can look at any of these temperatures and say, okay, there's a little patch that has a TC that's higher than the bulk. But with cuprates, it's very hard to deform them substantially. And this is still something we are working on, and there probably are ways to do it, but it's really not easy. So then the obvious question was, what if the deformation is considerable? And can we find a system that can really be plastically deformed a lot? And the answer is yes, of course. And this is strontium titanate, which is also extremely well known, but just a brief introduction for those who are not quite familiar with it. So the strontium titanate has a very simple perovskite structure. And if it's not doped, it's a wide gap insulator. But it's also quantum ferroelectric. So this is very interesting because it's almost a ferroelectric, but it never really reaches a transition, mostly due to quantum fluctuations. And because of this, or well, the reason for this is that there's a soft phonon mode that's pictured here, which never really goes to zero. So it remains extremely soft all the way down to zero temperature, but it never freezes. There's never a static polar distortion. And so as such, this material has been studied for a long time, but also what we are interested in is what happens when you dope it. And when you dope it, you can induce metallicity and superconductivity with extremely low carrier concentration. So STO still holds the record for the lowest carrier concentration superconductor. That's seen here in this graph. So you get superconductivity at concentrations as low as 10 to the 18th, and probably even lower than that. And then, of course, TC is not very high. It's below a Kelvin, but compared to the Fermi energy, it is quite high. So the Fermi energy here especially is of the order of kelvins. So if you look at the ratio, this is actually a very high TC superconductor. And although it's been discovered a long time ago, the pairing mechanism is still unknown. So then what was most important for us is that STO can surprisingly be plastically deformed a lot, even at room temperature. So this has been known for a long time now. People have managed to deform it up to the order of 10% at 300 K, which is really amazing. So you take a single crystal of something that's a ceramic, you put it basically in a vise, and you can deform it pretty much like clay. So you squeeze on it, it changes shape, it changes size, obviously, but it still more or less remains one piece. And this is an example of a stress strain diagram that for one of our samples, this was deformed up to 5%, a little bit more. And for this, we use these special strain cells that provide the necessary high forces to actually do this to large pieces. And the nice thing also is that STO you can buy commercially. So we had a lot of samples to play with and also large samples. So we were able to do a lot. And then, of course, the first question is what happens to the crystal, to the structure. And to find out, we went to do diffuse scattering, neutron and X-ray. This is a neutron diffuse scattering plot in a plane that's perpendicular to the deformation. And you see that the Bragg peaks, which would have been points, basically smear out into these arcs, which are called asterisms. This is also something that's known in plastically deformed metals. And the origin is that the crystal breaks up into these tilted domains. So each of these is like a smaller single crystal that's tilted. And then it's enough to have very small tilts to get these arcs. So that's the most obvious effect. But then there's also a more subtle thing. If you look close to these Bragg peaks, you see these intricate patterns and lines. And we were actually able to model these as coming from dislocation walls. So what we found is that if you arrange dislocations in these nice linear long-range ordered patterns, then you can reproduce this diffuse scattering. So the first effect of deformation is that what you get are these long-range self-organized dislocation walls. And this is already quite nice and interesting. But then the second question is, of course, what happens to this quantum paraelectricity? And to look at that, we did Raman scattering, where also there is a huge change. So basically, if you look at undeformed and deformed samples, there's a very large low energy spectral weight that appears in Raman. And it turns out that if you do the integration, it looks quantum critical. So it seems the spectral weight of this seems to diverge down to the lowest temperatures we were able to measure. So then the hypothesis is that basically when you deform this thing close to these dislocation structures, you get additional softening of this phonon mode, and locally you can get a quantum critical regime. And then finally, the most important question is what happens to the metallic state and the superconductivity. And it turns out that TC goes up quite a lot, which again is at first sight surprising for a material that's been so strongly deformed. And so it's also very anisotropic. So TC only goes up in the direction perpendicular to the stress. So this is this R perpendicular, while the other direction doesn't show much of a change. If you measure the resistivity with 4 contacts, you get this peak and minimum structure, which is basically just a geometric effect. But the bottom line is that TC goes up by roughly a factor of 2 compared to the undeformed TC, which are these lines. So this is really quite a significant enhancement. But even more than that, we were able to see possible evidence for even higher TC fluctuations or correlations. It's not quite clear what this is. And this was obtained by looking at, again, the resistivity anisotropy, which starts to appear already at very high temperatures. So this is now for different samples. It is known that STO has a quadratic temperature dependence of the resistivity. And what we saw in multiple samples is the actual resistivity drops below this quadratic line at temperatures as high as 30, 40, 50 Kelvin, depending on the doping and the strain levels and so on. So there is some evidence that there is actually a very small volume fraction of superconductivity already at temperatures that are of the order of the Fermi energy, which would really be extremely high. But as I mentioned, this is not completely solid evidence because we're not able to see any diamagnetic signals, which again can be explained if the volume fraction is small and these are one-dimensional superconducting wires, things like that. But this is still ongoing work and it's not entirely certain. But yeah, there is definitely some evidence that this happens. And then finally, we were able to qualitatively understand this through simple modeling, just assuming that TC locally is enhanced by quantum critical ferroelectric fluctuations, which has been a long-running hypothesis for STO. And then our theory colleagues basically calculated the local frequency of this polar mode in dependence on the distance from the dislocation wall. So on this figure, in the middle vertically is the dislocation wall, and then the TO mode. So the red parts are basically where it condenses, where you have local ferroelectric order. And then there is this sliver where the frequency goes to 0, and that's where you'd expect the largest TC enhancement. So there is a range of in space where you have quantum criticality necessarily, because it has to go from something that's condensed to something that has a finite frequency away from this structure. So you necessarily have to have it go through 0, and this is a nice feature of this. So it's sort of self-organized in a way. Yeah, this is still not quantitative because we don't really know how T depends on this frequency, given that the microscopics are not known at the moment. But at least qualitatively, this could explain why there are these strongly anisotropic TC enhancements. Okay, which brings me to the conclusion. So in plastically deformed STO, we have shown 3 things. Basically, the first is structural, that there are these self-organized dislocation structures or dislocation walls. The second is that around these walls, presumably, you get enhanced ferroelectric fluctuations that look quantum critical. And then this all leads to an enhancement of superconductivity, which again is likely related to these fluctuations. And also there is this possible high TC range. So to zoom out a little bit, this just makes the point that it's very important to understand and be able to manipulate homogeneity in oxides, including STO. But also this plastic deformation really opens up a lot of new perspectives, and it hasn't really been tried before a lot. So we are very curious to see what happens in other systems, and we have some insights on how to deform other materials and so on. But yeah, this is sort of just the beginning. Okay, so that's it. Thank you very much. And questions?
We have time for questions. Well, we have one here.
I can't hear it. Okay, that makes sense. Yeah.
Not yet, because I had to walk to the microphone.
Right.
So very, very interesting results, both of them. Thank you for presenting those. I had a question concerning the fluctuations, the exponential decay of fluctuations you saw in this nonlinear susceptibility signal. I was wondering what kind of scaling would you expect there from like Gaussian fluctuations like this as Lazarov-Larkin type?
Right. So generically, this gives power laws, and it's very hard to not get power laws. And it is possible to do when you, so there's been a lot of work on this. You can enforce various constraints on the fluctuation spectrum, and then you can get something that's cut off and so on. But this very nice and simple exponential regime is really not something you would expect. And we were also very confused for a long time with this. Because it really crops out a lot.
And in terms of the sort of absolute amplitude, are the fluctuations much larger than what you would expect for Gaussian fluctuations?
That's a bit hard to tell. It depends, of course, on how far you are from TC. So if you're far away from TC, they are larger. If you're close, then it's sort of, I mean, at some point, the system does become macroscopically superconducting. And you would expect that there is a conventional fluctuation regime close enough to TC. But if you're far away, then this exponential tail sort of wins. And that's the regime we were most interested in. So when you do go close to the transition, then you get power laws, of course.
Great, thank you very much.
Yeah, sure, thanks.
Any other question? Well, So if not, let's thank the speaker and all the speakers of this section. Thank you. I think now we proceed to prizes.
The tradition of science conference has been to promote younger researchers that have okay. The tradition of Superstripes conference has been to support and give a prize to the best presentation of a young researcher. We have a prize that has been established since 10 years. Okay. Is dedicated to Joseph Ashkenazi. Joseph Ashkenazi has been one of the person that started the idea to have the Stripes conferences many years ago. And he was attending the first Stripes conference and came many times. And there was a very open and organized, many open-minded scientists. And he died very early some years ago. So we decided to give the name of the Ashkenazi Prize to this excellent scientist. So we create a commission during the meeting that select the excellent researcher. Generally, there is many more excellent research that don't get the prize, but we have limited this year. We limited the number to 3 persons, and the commission has nominated 3 of them. So the director of Frascati Laboratory will come. We wait for him. There is Marcelli that represents INFN, and Terra Quantum of Vinocur supported the commission, was part of the commission, and okay, then we will give the prize in a few minutes. We wait for the director of the laboratory. We ask Alessandra Lanzara to come down to yes, to give the prize. So you can come and to say something on the tradition of stripes. You were in the first Stripes conference in '96. We had other. So we wait for Marcelli and the director of the Institute of Physics. So perhaps Alessandra can say something about stripes, the life in the stripes community.
All right. So yes, it's true that I was a student. I think I think I was doing my laurea, not even a PhD student with Antonio, when he came up with the idea of launching this series of conference called the Stripes. And I remember the first one was in Rome, in La Sapienza, and we had a huge attendance. There were so many people coming. And for me as a young student, it was so exciting. So we helped with the organization. It was a big success, so much that since then, every year, for many years, the Stripe conference kept going. And then at one point, they changed the name to Superstripe. And I actually let Antonio tell us the story why they became Superstripe.
It became Superstripes because I think it was in 2008 when Stripes was being found in iron based superconductors, and because Stripes was proposed for cuprates, but then a very clear case of Stripes was magnesium diboride. So in the time new material was showing stripes and so on. And so we say, but these kind of stripes are stripes star and stripes or something else. So since quantum mechanics is related, we started to call superstripes. And then superstripes also because it was a kind of super solid, super metals, and there is a new sector of science. It is so the idea of superstripes was born for the idea of super solids, something like that. Okay, so the Marcelli can say something now.
Yes, but we are just waiting a couple of minutes that the director is coming here from the office, and I just take the opportunity to thank the laboratory, which anytime support us in our initiative. When we have on the back our system, you see that even events unpleasant like those of yesterday can be fixed. And I also have to thank the attendees that realized that we cannot manage in a different way the situation. And I think it's also very nice to have you here, the remaining from the from the initial team that started this Superstripes event. I want to say that the support of the laboratory is not seen when we are here, but to prepare, in particular in these weeks, in this month, an event like this is not easy. We have to negotiate many things, and I just want to say that even a few months ago was impossible to use the service like the canteen. So I hope that this will not the last event in Frascati, and then who was here for the first time has the possibility to appreciate what we have done, and maybe we can continue in this direction. Regarding the awards, I think, I don't know if Antonio told, it's not always easy to select the person for the prize, so maybe there are other persons that could have, and we cannot, of course, give 100 prize. And this time, the selection has been this. So let me say that there will be for sure another times for the other young. We also negotiated to give also this year the Fibonacci prize, but for the reason of the events of this day, we decided to postpone to this event. Fabio is arrived. Fabio is our director, Fabio Bossi, director of the Laboratorio Nazionale di Frascati. I can leave the floor to Fabio for just 2 words, and then we arrange for the awards.
So good afternoon, everybody, and welcome to the Laboratorio Nazionale di Frascati. I know that there has been a little bit of excitement around this conference yesterday. I'm very sorry about that, but unfortunately, this is our times nowadays. So I thought that we could have been more presence here, but okay, fine. Let's go ahead with this. I'm very happy to and honored to have been asked to participate to this ceremony. Giving an award to young people is always very important because the youngsters are the future of our field. And so I think that we can enjoy the ceremony and go ahead with that. Thank you very much.